Electricity, like heat, only in a different way, has also a certain omnipresent character. Hardly any change can occur in the world without it being possible to demonstrate the presence of electrical phenomena. If water evaporates, if a flame burns, if two different metals, or two metals of different temperature, touch, or fire touches a solution of copper sulfate, and so on, electrical processes take place simultaneously with the more apparent physical and chemical phenomena. The more exactly we investigate natural processes of the most diverse nature, the more do we find evidence of electricity. In spite of its omnipresence, in spite of the fact that for half a century electricity has become more and more present in the industrial service of mankind, it remains precisely that form of motion the nature of which is still enveloped in the greatest obscurity. The discovery of the galvanic current is approximately 25 years younger than that of oxygen, and is at least as significant, for the theory of electricity as the latter discovery was for chemistry. Yet what a difference obtains even today between the two fields. In chemistry, thanks especially to Dalton's discovery of atomic weights, there is order, relative certainty about what has been achieved, and systematic, almost planned, attack on the territory still unconquered, comparable to the regular siege of the fortress. In the theory of electricity there is a barren lumber of ancient, doubtful experiments, neither definitely confirmed nor definitely refuted, an uncertain fumbling in the dark, uncoordinated research and experiment on the part of numerous isolated individuals, who attack the unknown territory with their scattered forces like the attack of a swarm of nomadic horsemen. It must be admitted, indeed, that in the sphere of electricity a discovery like that of Dalton, giving the whole science a central point and a firm basis for research, is still to seek. It is essentially this unsettled state of the theory of electricity, which for the time being makes it impossible to establish a comprehensive theory, that is responsible for the fact that a one-sided empiricism prevails in this sphere, an empiricism which as far as possible itself forbids thought, and which precisely for the reason not only thinks incorrectly but also is incapable of faithfully pursuing the facts or even reporting them faithfully, and which, therefore, becomes transformed into the opposite of true empiricism. If in general those natural scientists, who cannot say anything bad enough of the crazy a priori speculations of the German philosophy of nature, are to be recommended to read the theoretic physical works of the empirical school, not only of the contemporary, but even of a much later period. This holds quite especially for the theory of electricity. Let us take a work of the year 1840, An Outline of the Sciences of Heat and Electricity, by Thomas Thomson. Old Thomson was indeed an authority in his day. Moreover, he had already at his disposal a very considerable part of the work of the greatest electrician so far, Faraday. Yet his book contains at least just as crazy things as the corresponding section of the much older Hegelian philosophy of nature. The description of the electric spark, for instance, might have been translated directly from the corresponding passage in Hegel. Both enumerate all the wonders that people sought to discover in the electric spark, prior to knowledge of its real nature and manifold diversity, and which have now been shown to be mainly special cases or errors. Still better, Thomson recounts quite seriously on p. 436 disdain of clock and bolt stories, such as that, with a rising barometer and falling thermometer, glass, resin, silk, etc., become negatively electrified on immersion in mercury, but positively if instead the barometer is falling and the temperature rising, that in summer gold and several other metals become positive on warming and negative on cooling, but in winter the reverse, that with a high barometer and northerly wind they are strongly electric, positive if the temperature is rising and negative if it is falling, etc. So much for the treatment of the facts. As regards a priori speculation, Thomson favors us with the following treatment of the electric spark, derived from no lesser person than Faraday himself. The spark is a discharge, or weakening of the polarized inductive state of many electric particles by means of a peculiar action of a few of these particles occupying a very small and limited space. Faraday assumes that the few particles situated where the discharge occurs are not merely pushed apart, but assume a peculiar, highly exalted, condition for the time. That is that they have thrown on them all the surrounding forces in succession and are thus brought into a proportion of intensity of condition, perhaps equal to that of chemically combining atoms, that they then discharge the powers in the same manner as the atoms do theirs. In some way at present unknown to us and so the end of the whole, the ultimate effect is exactly as if a metallic wire had been put into the place of the discharging particles, and it does not seem impossible that the principles of action in both cases may, hereafter, prove to be the same. I have, adds Thomson, given this explanation of Faraday's in his own words, because I do not understand it clearly. This will certainly have been the experience of other persons also, quite as much as when they read in Hegel that in the electric spark, the special materiality of the charged body does not as yet enter into the process, but is determined within it only in an elementary and spiritual way, and that electricity is, the anger, the effervescence, proper to the body, its angry self, that is exhibited by every body when excited. Yet the basic thought of both Hegel and Faraday is the same. Both oppose the idea that electricity is not a state of matter but a special, distinct variety of matter. And since in the spark electricity is apparently exhibited as independent, free from any foreign material substratum, separated out and yet perceptible to the senses, they arrive at the necessity, in the state of science at the time, of having to conceive of the spark as a transient phenomenal form of force, momentarily freed from all matter. For us, of course, the riddle is solved, since we know that on the spark discharge between metal electrodes real metallic particles leap across, and hence in actual fact the special materiality of the charged body enters into the process. As is well known, electricity and magnetism, like heat and light, were at first regarded as special imponderable substances. As far as electricity is concerned, it is well known that the view soon developed that there are two opposing substances, two fluids, one positive and one negative, which in the normal state neutralize each other until they are forced apart by a so-called electric force of separation. It is then possible to charge two bodies, one with positive, the other with negative electricity. On uniting them by third conducting body equalization occurs, either suddenly or by means of a lasting current, according to circumstances. The sum-equalization appeared very simple and comprehensible, but the current offered difficulties. The simplest hypothesis, that the current in every case is a movement of either purely positive or purely negative electricity, was opposed by Fechner, and in more detail by Weber, with the view that in every circuit two equal currents of positive and negative electricity flow in opposite directions in channels lying side by side between the ponderable molecules of the bodies. Weber's detailed mathematical working out of this theory finally arrives at the result that a function, of no interest to us here, is multiplied by a magnitude Lr, the latter signifying the ratio of the unit of electricity to the milligram. The ratio to a measure of weight can naturally only be a weight ratio, hence one-side empiricism. The formula derived by Weber sufficed only within certain limits, and Helmholtz, in particular, only a few years ago calculated results that come into conflict with the principle of the conservation of energy. In opposition to Weber's hypothesis of the double current flowing in opposite directions, C. Naumann in 1871 put forward the other hypothesis that in the current only one of the two electricities, for instance the positive, moves, while the other negative one remains firmly bound up with the mass of the body. On this we may include the remark, this hypothesis could be linked up with that of Weber if Weber's supposed double current of electric masses plus minus I1/2 E flowing in opposite directions, there added a further current of neutral electricity, externally inactive, which carried with it amounts of electricity plus minus I1/2 E in the direction of the positive current. This statement is once again characteristic of one-sided empiricism. In order to bring about the flow of electricity at all, it is decomposed into positive and negative. All attempts, however, to explain the current with these two substances meet with difficulties. Both the assumption that only one of them is present in the current and that the two of them flow in opposite directions simultaneously, and finally, the third assumption also that one flows and the other is at rest. If we adopt this last assumption, how are we to explain the inexplicable idea that negative electricity, which is mobile enough in the electrostatic machine of the Leyden jar, in the current is firmly united with the mass of the body? Quite simply. Besides the positive current plus E flowing through the wire to the right, and the negative current E flowing to the left, we make yet another current, this time of neutral electricity, plus minus I1/2 E flow to the right. First we assume that the two electricities, to be able to flow at all, must be separated from one another, and then, in order to explain the phenomena that occur on the flow of the separated electricities, we assume that they can also flow unseparated. First we make a supposition to explain a particular phenomenon, and at the first difficulty encountered we make a second supposition, which directly negates the first one. What must be the sort of philosophy that these gentlemen have the right to complain of? However, alongside this view of the material nature of electricity, there soon appeared a second view, according to which it is to be regarded as a mere state of the body, a force, or, as we would say today, a special form of motion. We saw above that Hegel, and later Faraday, adhered to this view. After the discovery of the mechanical equivalent of heat had finally disposed of the idea of a special heat stuff, and heat was shown to be a molecular motion, the next step was to treat electricity also according to the new method and to attempt to determine its mechanical equivalent. This attempt was fully successful, particularly owing to the experiments of Joule, Favre, and Raoult. Not only was the mechanical and thermal equivalent of the so-called electromotive force of the galvanic current established, but also its complete equivalence with the energy liberated by chemical processes in the exciting cell or used up in the decomposition cell. This made the assumption that electricity is a special material fluid more and more untenable. The analogy, however, between heat and electricity was not perfect. The galvanic current still differed in very essential respects from the conduction of heat. It was still not possible to say what it was that moved in the electrically affected bodies. The assumption of a mere molecular vibration, as in the case of heat, seemed insufficient. In view of the enormous velocity of motion of electricity, even exceeding that of light, it remained difficult to overcome the view that there are some material substances in motion between the molecules of the body. Here the most recent theories put forward by Clerk Maxwell, Hankel, Reinhardt, and Hillard are in complete agreement with the assumption already advanced in 1836. First of all is a suggestion by Faraday that electricity is a movement of the elastic medium permeating the whole of space and hence all bodies as well, the discrete particles of which medium repel one another according to the law of the inverse square of the distance. In other words, it is a motion of ether particles, and the molecules of the body take part in this motion. As to the manner of this motion, the various theories are divergent. Those of Maxwell, Hankel, and Reinhardt, taking as their basis modern investigations of vortex motion, explain it in various ways from vortices. So that the vortex of old Descartes also once more comes into favor in an increasing number of new fields. We refrain from going more closely into the details of these theories. They differ strongly from one another and they will certainly still experience many transformations. But a decisive advance appears to lie in their common basic conception, that electricity is a motion of the particles of the luminiferous ether that penetrates all ponderable matter, this motion reacting on the molecules of the body. This conception reconciles the two earlier ones. According to it, it is true that in electrical phenomena it is something substantial that moves, something different from ponderable matter. But this substance is not electricity itself, which in fact proves rather to be a form of motion, although not a form of the immediate direct motion of ponderable matter. While, on the one hand, the ether theory shows a way of getting over the primitive clumsy idea of two opposed electrical fluids, on the other hand it gives a prospect of explaining what the real, substantial substratum of electrical motion is, what sort of a thing it is whose motion produces electrical phenomena. The ether theory has already had one decisive success. As is well known, there is at least one point where electricity directly alters the motion of light, it rotates the latter's plane of polarization. On the basis of this theory mentioned above, Clerk Maxwell calculates that the electric specific inductive capacity of a body is equal to the square of its index of refraction. Boltzmann has investigated the electric coefficients of various non-conductors, and he found that in sulfur, rosin, and paraffin, the square roots of these coefficients were respectively equal to their indices of refraction. The highest deviation, in sulfur, amounted to only 4%. Consequently, the Maxwellian ether theory in this particular has hereby been experimentally confirmed. It will, however, require a lengthy period and cost much labor before a new series of experiments will have extracted a firm kernel from these mutually contradictory hypotheses. Until then, or until the ether theory, too, is perhaps supplanted by an entirely new one, the theory of electricity finds itself in the uncomfortable position of having to employ a mode of expression which it itself admits to be false. Its whole terminology is still based on the idea of two electric fluids. It still speaks quite unashamedly of electric masses flowing in the bodies, of a division of electricities in every molecule, etc. This is a misfortune which for the most part, as already said, follows inevitably from the present transitional state of science, but which also, with a one-sided empiricism particularly prevalent in this branch of investigation, contributes not a little to preserving the existing confusion of thought. The opposition between so-called static or frictional electricity and dynamic electricity or galvanism can now be regarded as bridged over, since we have learned to produce constant currents by means of the electric machine and, conversely, by means of the galvanic current to produce so-called static electricity, to charge light in jars, etc. We shall not here touch on the subform of static electricity, nor likewise on magnetism, which is now recognized to be also a subform of electricity. A constant current can be produced in many different ways. Mechanical mass motion produces directly, by friction, in the first place only static electricity, and a constant current only with great dissipation of energy. For the major part, at least, to become transformed into electric motion, the intervention of magnetism is required, as in the well-known magneto-electric machines of Ram, Siemens, and others. Heat can be converted directly into current electricity, as especially occurs at the junction of two different metals. The energy set free by chemical action, which under ordinary circumstances appears in the form of heat, is converted under appropriate conditions into electric motion. Conversely, the latter form of motion, as soon as the requisite conditions are present, passes into any other form of motion, into mass motion, to a very small extent directly into electrodynamic attractions and repulsions, to a large extent, however, by the intervention of magnetism in the electromagnetic machine, into heat, throughout a closed circuit, unless other changes are brought about, into chemical energy, in decomposition cells and voltmeters introduced into the circuit, where the current dissociates compounds that are attacked in vain by other means. All these transformations are governed by the basic law of the quantitative equivalence of motion through all exchanges of form. Or, as Weidmann expresses it, by the law of conservation of force, the mechanical work exerted in any way for the production of the current must be equivalent to the work exerted in producing all the effects of the current. The conversion of mass motion or heat into electricity offers us no difficulties here. It has been shown that the so-called electromotive force in the first case is equal to work expended on that motion. And in the second case it is, at every junction of the thermopile directly proportional to its absolute temperature, that is to the quantity of heat present at every junction measured in absolute units. The same law has in fact been proved valid also for the electricity produced from chemical energy. But here the matter seems to be not so simple, at least for the theory now current. Let us, therefore, go into this somewhat more deeply. One of the most beautiful series of experiments on the transformations of form of motion as a result of the action of a galvanic cell is that of Favre. He put a small cell of 5 elements in a calorimeter. In a second calorimeter he put a small electromagnetic motor with the main axle and driving wheel projecting so as to be available for any kind of coupling. Each production in the cell of 1 gram of hydrogen, or solution of 326 grams of zinc, gave the following results. A cell enclosed in the calorimeter, excluding the motor, heat production 18,682 or 18,674 units of heat. B cell and motor linked in the circuit, but the motor prevented from moving. Heat in the cell 16,448, in the motor 2,219, together 18,667 units of heat. C asp, but the motor in motion without however lifting a weight. Heat in the cell 13,888, in the motor 4,769, together 18,657 units of heat. D asp, but the motor raises a weight and so performs mechanical work equals 131,24 kilogram meters. Heat in the cell 15,427, in the motor 2,947, total 18,374 units of heat. Loss in contrast to the above 18,682 equals 308 units of heat. But the mechanical work performed amounting to 131,24 kilogram meters multiplied by 1,000 and divided by the mechanical equivalent of heat equals 423,5 kilogram meters gives 309 units of heat. Hence exactly the loss mentioned above as the heat equivalent of the mechanical work performed. The equivalence of motion in all its transformations is, therefore, strikingly proved for electric motion also, within the limits of unavoidable error. And it is likewise proved that the electromotive force of the galvanic battery is nothing but chemical energy converted into electricity, and the battery itself nothing but an apparatus that converts chemical energy on its liberation into electricity. Just as a steam engine transforms the heat supplied to it into mechanical motion, without in either case a converting apparatus supplying further energy on its own account. A difficulty arises here, however, in relation to the traditional mode of conception. The latter ascribes an electric force of separation to the battery in virtue of the conditions of contact present between the fluids and metals, which force is proportional to the electromotive force, and therefore for a given battery represents a definite quantity of energy. What then is the relation of this electric force of separation, which according to the traditional mode of conception of the battery as such is inherently a source of energy even without chemical action, to the energy set free by chemical action? And if it is a source of energy independent of the latter, whence comes the energy furnished by it? This question in a more or less unclear form constitutes the point of dispute between the contact theory founded by Volta and the chemical theory of the galvanic current that arose immediately afterwards. The contact theory explained the current from the electric stresses arising in the battery on contact of the metals with one or more of the liquids, or even merely on contact of the liquids themselves, and from their neutralization or that of the opposing electricities thus generated in the circuit. The pure contact theory regarded any chemical changes that might thereby occur as quite secondary. On the other hand, as early as 1805, Ritter maintained that the current could only be formed if the excipients reacted chemically even before closing the circuit. In general, this older chemical theory is summarized by Weidmann to the effect that according to its so-called contact electricity makes its appearance only if at the same time there comes into play a real chemical action of the bodies in contact, or at any rate a disturbance of the chemical equilibrium, even if not directly bound up with chemical processes, a tendency towards chemical action between the bodies in contact. It is seen that both sides put the question of the source of energy of the current only indirectly, as indeed could hardly be otherwise at the time. Volta and his successors found it quite in order that the mere contact of heterogeneous bodies should produce a constant current, and consequently be able to perform definite work without equivalent return. Ritter and his supporters are just as little clear how the chemical action makes the battery capable of producing the current and its performance of work. But if this point has long ago been cleared up for chemical theory by Joule, Favre, Raoult, and others, the opposite is the case for the contact theory. Insofar as it is persistent, it remains essentially at the point where it started. Notions belonging to a period long outlived, a period when one had to be satisfied to ascribe a particular effect to the first available apparent cause that showed itself on the surface. Regardless of whether motion was thereby made to arise out of nothing, notions that directly contradict the principle of the conservation of energy thus continue to exist in the theory of electricity of today. And if the objectionable aspects of these ideas are shown off, weakened, watered down, castrated, glossed over, this does not improve matters at all. The confusion is bound to become only so much the worse. As we have seen, even the older chemical theory of the current declares the contact relations of the battery to be absolutely indispensable for the formation of the current. It maintains only that these contacts can never achieve a constant current without simultaneous chemical action. And even today it is still taken as a matter of course that the contact arrangements of the battery provide precisely the apparatus by means of which liberated chemical energy is transformed into electricity, and that it depends essentially on these contact arrangements whether or how much chemical energy actually passes into electric motion. Weidmann, as a one-sided empiricist, seeks to say what can be saved of the old contact theory. Let us follow what he has to say. He declares, in contrast to what was formerly believed, the effect of contact of chemically indifferent bodies, E.G.OF, metals, is neither indispensable for the theory of the pile, nor proved by the facts that derived his law from it, a law that can be derived without this assumption, and that Fechner, who confirmed this law experimentally, likewise defended the contact theory. Nevertheless, the excitation of electricity to metallic contact, according to the experiments now available at least, is not to be denied. Even though the quantitative results obtainable in this respect may always be tainted with an inevitable uncertainty owing to the impossibility of keeping absolutely clean the surfaces of the bodies in contact, it is seen that the contact theory has become very modest. It concedes that it is not at all indispensable for explaining the current, and neither proved theoretically by Ohm nor experimentally by Fechner. It even concedes then that the so-called fundamental experiments, on which alone it can still rest, can never furnish other than uncertain results in a quantitative respect, and finally it asks us merely to recognize that in general it is by contact, although only of metals, that electric motion occurs. If the contact theory remained content with this, there would not be a word to say against it. It will certainly be granted that on the contact of two metals electrical phenomena occur, in virtue of which a preparation of a frog's leg can be made to twitch, and electroscope charged, and other movements brought about. The only question that arises in the first place is, whence comes the energy required for this? To answer this question, we shall, according to Weidmann, adduce more or less the following considerations. If the heterogeneous metal plates and they are brought within a close distance of each other, they attract each other in consequence of the forces of adhesion. On mutual contact they lose the vis viva motion imparted to them by this attraction. The lost vis viva is to a large extent converted into heat. A small portion of it, however, is expended in bringing about a different distribution of the electricities previously unseparated. As we have already mentioned above, the bodies brought together become charged with equal quantities of positive and negative electricity, possibly as the result of an unequal attraction for the two electricities. The modesty of the contact theory becomes greater and greater. At first it is admitted that the powerful electric force of separation, which has later such a gigantic work to perform, in itself possesses no energy of its own, and that it cannot function if energy is not supplied to it from outside. And then it has allotted to it a more than diminutive source of energy, the vis viva of adhesion, which only comes into play at scarcely measurable distances, and which allows the bodies to travel scarcely measurable length. But it does not matter, it indisputably exists and equally undeniably vanishes on contact. But even this minute source still furnishes too much energy for our purpose. A large part is converted into heat, and only a small portion serves to evoke the electric force of separation. Now, although it is well known that cases enough occur in nature where extremely minute impulses bring about extremely powerful effects, Weidmann himself seems to feel that his hardly trickling source of energy can with difficulty suffice here, and he seeks a possible second source in the assumption of an interference of the molecular vibrations of the two metals at the surfaces of contact. Apart from other difficulties encountered here, Grove and Gachet have shown that for exciting electricity actual contact is not at all indispensable, as Weidmann himself tells us on the previous page. In short, the more we examine it, the more does the source of energy for the electric force of separation dwindle to nothing. Yet up to now we hardly know of any other source for the excitation of electricity on metallic contact. According to Naumann, the contact electromotive forces convert heat into electricity. He finds the assumption natural that the ability of these forces to produce electric motion depends on the quantity of heat present, or, in other words, that is a function of the temperature, as has also been proved experimentally by Leroux. Here too we find ourselves groping in the dark. The law of the voltaic series of metals forbids us to have recourse to the chemical processes that to a small extent are continually taking place at the contact surfaces, which are always covered by a thin layer of air and impure water, a layer as good as inseparable as far as we are concerned. An electrolyte should produce a constant current in the circuit, but the electricity of mere metallic contact, on the contrary, disappears on closing the circuit. And here we come to the real point, whether, and in what manner, the production of a constant current on the contact of chemically indifferent bodies is made possible by this electric force of separation, which Weidmann himself first of all restricted to metals, declaring it incapable of functioning without energy being supplied from outside, and then referred exclusively to a truly microscopical source of energy. The voltaic series arranges the metals in such a sequence that each one behaves as electronegative in relation to the preceding one, and as electropositive in relation to the one that follows it. Hence, if we arrange a series of pieces of metal in this order, for example zinc, tin, iron, copper, platinum, we shall be able to obtain differences of electric potential at the two ends. If, however, we arrange the series of metals to form a circuit so that the zinc and platinum are in contact, the electric stress is at once neutralized and disappears. Therefore, the production of a constant current of electricity is not possible in a closed circuit of bodies belonging to the voltaic series. Weidmann further supports this statement by the following theoretical consideration. In fact, if a constant electric current were to make its appearance in the circuit, it would produce heat in the metallic conductors themselves, and this heating could at the most be counterbalanced by cooling of the metallic junctions. In any case, it would give rise to an uneven distribution of heat. Moreover, an electromagnetic motor could be driven continuously by the current without any sort of supply from outside, and thus work would be performed, which is impossible, since on firmly joining the metals. For instance, by soldering, no further changes to compensate for this work could take place even at the contact surfaces. And not content with the theoretical and experimental proof that the contact electricity of metals by itself cannot produce any current, we shall see too that Weidmann finds himself compelled to put. Let us, therefore, try another way of passing from contact electricity to the current. Let us imagine, with Weidmann, two metals, such as a zinc rod and a copper rod, soldered together at one end, but with their free ends connected by a third body that does not act electromotively in relation to the two metals, but only conducts the opposing electricities collected on its surfaces, so that they are neutralized in it. Then the electric force of separation would always restore the previous difference of potential. Thus a constant electric current would make its appearance in the circuit, a current that would be able to perform work without any compensation, which again is impossible. Accordingly, there cannot be a body which only conducts electricity without electromotive activity in relation to the other bodies. We are no better off than before. The impossibility of creating motion again bars the way, by the contact of chemically indifferent bodies. Hence, by contact electricity as such, we shall never produce a current. Let us therefore go back again and try a third way pointed out by Weidmann. Finally, if we immerse a zinc plate and a copper plate in a liquid that contains a so-called binary compound, which therefore can be decomposed into two chemically distinct constituents that completely saturate one another, e.g., dilute hydrochloric acid, etc., then according to paragraph 27, the zinc becomes negatively charged and the copper positively. On joining the metals, these electricities neutralize one another through the place of contact, through which, therefore, a current of positive electricity flows from the copper to the zinc. Moreover, since the electric force of separation making its appearance on the contact of these two metals carries away the positive electricity in the same direction, the effects of the electric forces of separation are not abolished in a closed metallic circuit. Hence there arises a constant current of positive electricity, flowing in the closed circuit through the copper zinc junction in the direction of the latter, and through the liquid from the zinc to the copper. We shall return in a moment to the question how far the individual electric forces of separation present in the enclosed circuit freely participate in the formation of the current. The combination of conductors providing such a galvanic current we term a galvanic element, or also a galvanic battery. Thus the miracle has been accomplished. By the mere electric contact force of separation, which, according to Weidmann himself, cannot be effective without energy being supplied from outside, a constant current has been produced. And if we were offered nothing more for its explanation than the above passage from Weidmann, it would indeed be an absolute miracle. What have we learned here about the process? 1. If zinc and copper are immersed in a liquid containing a so-called binary compound, then, according to paragraph 27, the zinc becomes negatively charged and the copper positively charged. But in the whole of paragraph 27 there is no word of any binary compound. It describes only a simple voltaic element of a zinc plate and copper plate, with a piece of cloth moistened by an acid liquid interposed between them, and then investigates, without mentioning any chemical processes, the resulting static electric charges of the two metals. Hence, the so-called binary compound has been smuggled in here by the back door. 2. What this binary compound is doing here remains completely mysterious. The circumstance that it can be decomposed into two chemical constituents that fully saturate each other could at most teach us something new if it were actually to decompose. But we are not told a word about that, hence for the time being we have to assume that it does not decompose, for example in the case of paraffin. 3. When the zinc in the liquid has been negatively charged, and the copper positively charged, we bring them into contact. At once these electricities neutralize one another through the place of contact, through which therefore a current of positive electricity flows from the copper to the zinc. Again, we do not learn why only a current of positive electricity flows in the one direction, and not also a current of negative electricity in the opposite direction. We do not learn at all what becomes of the negative electricity, which, hitherto, was just as necessary as the positive. The effect of the electric force of separation consisted precisely in setting them free to oppose one another. Now it has been suddenly suppressed, as it were eliminated, and it is made to appear as if there exists only positive electricity. But then again, on p. 51, the precise opposite is said, for here the electricities unite in one current, consequently both negative and positive flow in it. Who will rescue us from this confusion? 4. Moreover, since the electric force of separation making its appearance on the contact with these two metals carries away the positive electricity in the same direction, the effects of the electric forces of separation are not abolished in a closed metallic circuit. Hence, there arises a constant current, etc. This is a bit thick, for as we shall see a few pages later, Weidmann proves to us that on the formation of a constant current, the electric force of separation at the place of contact of the metals must be inactive, that not only does a current occur even when this force, instead of carrying away the positive electricity in the same direction, acts in opposition to the direction of the current, but that in this case too it is not compensated by a definite share of the force of separation of the battery and, hence, once again is inactive. Consequently, how can Weidmann on p. 45 make an electric force of separation participate as a necessary factor in the formation of the current when on p. 52 he puts it out of action for the duration of the current, and that, moreover, by a hypothesis erected specially for this purpose? 5. Hence there arises a constant current of positive electricity flowing in the closed circuit from the copper through its place of contact with the zinc in the direction of the latter, and through the liquid from the zinc to the copper. But, in the case of such a constant electric current, heat would be produced by it in the conductors themselves, and also it would be possible for an electromagnetic motor to be driven by it and thus work performed, which, however, is impossible without supply of energy. Since Weidmann up to now has not breathed a syllable as to whether such a supply of energy occurs, or whence it comes, the constant current so far remains just as much an impossibility as in both the previously investigated cases. No one feels this more than Weidmann himself, so he finds it desirable to hurry as quickly as possible over the many ticklish points of this remarkable explanation of current formation, and instead to entertain the reader throughout several pages with all kinds of elementary anecdotes about the thermal, chemical, magnetic, and physiological effects of the still mysterious current, in the course of which by way of exception he even adopts a quite popular tone. Then he suddenly continues. We have now to investigate in what way the electric forces of separation are active in a closed circuit of two metals and a liquid, for example zinc, copper, and hydrochloric acid. We know that when the current traverses liquid, the constituents of the binary compound contained in it become separated in such a manner that one constituent is set free on the copper, and an equivalent amount of the other on the zinc, whereby the latter constituent combines with an equivalent amount of zinc to form ZnCl. We know. If we know this, we certainly do not know it from Weidmann who, as we have seen, so far has not breathed a syllable about this process. Further, if we do know anything of this process, it is that it cannot proceed in the way described by Weidmann. On the formation of a molecule of HCl from hydrogen and chlorine, an amount of energy equals 22,000 units of heat is liberated. Therefore, to break away the chlorine from its combination with hydrogen, the same quantity of energy must be supplied from outside for each molecule of HCl. Where does the battery derive this energy? Weidmann's description does not tell us, so let us look for ourselves. When chlorine combines with zinc to form zinc chloride, a considerably greater quantity of energy is liberated than is necessary to separate chlorine from hydrogen, develops 97,210 and 244,000 units of heat. With that the process in the battery becomes comprehensible. Hence it is not, as Weidmann relates, that hydrogen without more ado is liberated from the copper, and chlorine from the zinc, whereby then subsequently and accidentally the zinc and chlorine enter into combination. On the contrary, the union of the zinc with the chlorine is the essential, basic condition for the whole process, and as long as it does not take place, one would wait in vain for hydrogen on the copper. The excess of energy liberated on formation of a molecule of ZnCl over the expended on liberating two atoms of H from two molecules of HCl is converted in the battery into electric motion and provides the entire electromotive force that makes its appearance in the current circuit. Hence it is not a mysterious electric force of separation that tears asunder hydrogen and chlorine without any demonstrable source of energy. It is the total chemical process taking place in the battery that endows all the electric forces of separation and electromotive forces of the circuit with the energy necessary for their existence. For the time being, therefore, we put on record that Weidmann's second explanation of the current gives us just as little assistance as his first one, and let us proceed further with the text. This process proves that the behavior of the binary substance between the metals does not consist merely in a simple predominant attraction of its entire mass for one electricity or the other, as in the case of metals, but that in addition a special action of its constituents is exhibited. Since the constituent Cl is given off where the current of positive electricity enters the fluid, and the constituent H where the negative electricity enters, we assume that each equivalent of chlorine in the compound HCl is charged with a definite amount of negative electricity determining its attraction by the entering positive electricity. It is the electronegative constituent of the compound. Similarly, the equivalent H must be charged with positive electricity, and so represent the electropositive constituent of the compound. These charges could be produced on the combination of H and Cl in just the same way as on the contact of zinc and copper. Since the compound HCl as such is non-electric, we must assume accordingly that the atoms of the positive and negative constituents contain equal quantities of positive and negative electricity. If now a zinc plate and a copper plate are dipped in dilute hydrochloric acid, we can suppose that the zinc has a stronger attraction towards the electronegative constituent than towards the electropositive one. Consequently, the molecules of hydrochloric acid in contact with the zinc will dispose themselves so that their electronegative constituents are turned towards the zinc, and their electropositive constituents towards the copper. Owing to the constituents, when so arranged exerting their electrical attraction on the constituents of the next molecules of HCl, the whole series of molecules between the zinc and copper plates becomes arranged as in Fig 10, plus ClHClHClHClHClH. If the second metal acts on the positive hydrogen as the zinc does on the negative chlorine, it would help to promote the arrangement. If it acted in the opposite manner, only more weakly, at least the direction would remain unaltered. By the influence exerted by the negative electricity of the electronegative constituent Cl adjacent to the zinc, the electricity will so distributed in the zinc that places on it which are close to the Cl of the immediately adjacent atom of acid would become charged positively, those further away negatively. Similarly, negative electricity would accumulate in the copper next to the electropositive constituent of the adjacent atom of hydrochloric acid, and the positive electricity would be driven to the more remote parts. Next, the positive electricity in the zinc will combine with the negative electricity of the immediately adjacent atom of Cl, and the latter itself with the zinc, to form non-electric ZnCl2. The electropositive atom H, which was previously combined with this atom of Cl, will unite with the atom of Cl turned towards it belonging to the second atom of HCl, with simultaneous combination of the electricities contained in these atoms. Similarly, the H of the second atom of HCl will be combined with the Cl of the third atom, and so on, until finally an atom of H will set free on the copper, the positive electricity of which will unite with the distributed negative electricity of the copper, so that it escapes in a non-electrified condition. This process would repeat itself until the repulsive action of the electricities accumulated in the metal plates on the electricities of the hydrochloric acid constituents turned towards them balances the chemical attraction of the latter by the metals. If, however, the metal plates are joined by a conductor, the free electricities of the metal plates unite with one another, and the above-mentioned processes can recommence. In this way, a constant current of electricity comes into being. It is evident that in the course of it, a continual loss of this viva occurs, owing to the constituents of the binary compound on their migration to the metals moving to the latter with a definite velocity and then coming to rest, either with formation of a compound or by escaping in the free state. This loss of vis viva is equivalent to the quantity of heat which is set free in the visibly occurring chemical process, essentially, therefore, that produced on the solution of an equivalent of zinc in the dilute acid. This value must be the same as that of the work expended on separating the electricities. If, therefore, the electricities unite to form a current, then, during the solution of an equivalent of zinc and the giving off of an equivalent of hydrogen from the liquid, there must make its appearance in the whole circuit, whether in the form of heat or in the form of external performance of work, an amount of work that is likewise equivalent to the development of heat corresponding to this chemical process. Let us assume, we must assume, we can suppose, would be distributed, would become charged, etc., etc. sheer conjecture and subjunctives from which only three actual indicatives can be definitely extracted. Firstly, that the combination of the zinc with the chlorine is not pronounced to be the condition for the liberation of hydrogen. Secondly, as we now learn right at the end, and as it were incidentally, that the energy herewith liberated is the source, and indeed the exclusive source, of all energy required for formation of the current. And thirdly, that this explanation of the current formation is directly in contradiction to both those previously given, as the latter are themselves mutually contradictory. For the formation of a constant current, therefore, there is active wholly and solely the electric force of separation, which is derived from the unequal attraction and polarization of the atoms of the binary compound in the exciting liquid of the battery by the metal electrodes. At the place of contact of the metals, at which no further mechanical changes can occur, the electric force of separation must on the other hand be inactive. That this force, if by chance it counteracts the electromotive excitation of the metals by the liquid, is not compensated by a definite share of the force of separation at the place of contact, is proved by the above-mentioned complete proportionality of the total electric force of separation in the circuit with the above-mentioned heat equivalent of the chemical process. Hence it must be neutralized in another way. This would most simply occur on the assumption that on contact of the exciting liquid with the metals the electromotive force is produced in a double manner. On the one hand by an unequally strong attraction of the mass of the liquid as a whole towards one or the other electricity. On the other hand by the unequal attraction of the metals towards the constituents of the liquid charged with opposite electricities. Owing to the former unequal attraction towards the electricities, the liquids would fully conform to the law of the voltaic series of metals, and in a closed circuit, complete neutralization to zero of the electric forces of separation take place. Herewith the last relics of the contact theory are now happily eliminated from formation of the current, and simultaneously also the last relics of Weidmann's first explanation of current formation given on p. 45. It is finally conceded without reservation that the galvanic battery is a simple apparatus for converting liberated chemical energy into electric motion, into so-called electric force of separation and electromotive force, in exactly the same way as the steam engine is an apparatus for converting heat energy into mechanical motion. In the one case, as in the other, the apparatus provides only the conditions for liberation and further transformation of the energy, but supplies no energy on its own account. This once established, it remains for us now to make a closer examination of this third version of Weidmann's explanation of the current. How are the energy transformations in the circuit of the battery represented here? It is evident, he says, that in the battery, a continual loss of vis viva occurs, owing to the constituents of the binary compound on their migration to the metals moving to the latter with a definite velocity and then coming to rest, either with formation of the compound or by escaping in the free state. This loss is equivalent to the quantity of heat which is set free in the visibly occurring chemical process, essentially, therefore, that produced on the solution of an equivalent of zinc in the dilute acid. Firstly, if the process goes on in pure form, no heat at all is set free in the battery on solution of the zinc. The liberated energy is indeed converted directly into electricity, and only from this converted once again into heat by the resistance of the whole circuit. Secondly, vis viva is half the product of the mass and the square of the velocity. Hence the above statement would read, the energy set free on solution of an equivalent of zinc in dilute hydrochloric acid equals so many calories, is likewise equivalent to half the product of the mass of the ions and the square of the velocity with which they migrate to the metals. Expressed in this way, the sentence is obviously false. The vis viva appearing on the migration of the ions is far removed from being equivalent to the energy set free by the chemical process. But if it were to be so, no current would be possible, since there would be no energy remaining over for the current in the remainder of the circuit. Hence the further remark is introduced that the ions come to rest either with formation of a compound or by escaping in the free state. But if the loss of vis viva is to include also the energy changes taking place on these two processes, then we have indeed arrived at a deadlock. For it is precisely to these two processes taken together that we owe the whole liberated energy, so that there can be absolutely no question here of a loss of vis viva, but at most of a gain. It is therefore obvious that Weidmann himself did not mean anything definite by this sentence. Rather, the loss of vis viva represents only the deus ex machina, which is to enable him to make the fatal leap from the old contact theory to the chemical explanation of the current. In point of fact, the loss of vis viva has now performed its function and is dismissed. Henceforth, the chemical process in the battery is undisputed sway as the sole source of energy for current formation. And the only remaining anxiety of our author is as to how he can politely get rid from the current of the last relic of excitation of electricity by the contact of chemically indifferent bodies, namely, the force of separation active at the place of contact of the two metals. Reading the above explanation of current formation given by Weidmann, one could believe oneself in the presence of a specimen of the kind of apology that holy and half-credulous theologians of almost 40 years ago employed to meet the philologico-historical Bible criticism of Strauss, Wilke, Bruno Bauer, etc. The method is exactly the same, and it is bound to be so. For in both cases it is a question of saving the heritage of tradition from scientific thought. Exclusive empiricism, which at most allows thinking in the form of mathematical calculation, imagines that it operates only with undeniable facts. In reality, however, it operates predominantly with out-of-date notions, with the largely obsolete products of thought of its predecessors, and such are positive and negative electricity, the electric force of separation, the contact theory. These serve as the foundation of endless mathematical calculations in which, owing to the strictness of the mathematical formulation, the hypothetical nature of the premises gets comfortably forgotten. This kind of empiricism is as credulous towards the results of the thought of its predecessors as it is skeptical in its attitude to the results of contemporary thought. For the experimentally established facts have gradually become inseparable from the traditional interpretation associated with them. The simplest electric phenomenon is presented falsely, for example by smuggling the two electricities. This empiricism cannot any longer describe the facts correctly, because the traditional interpretation is woven into the description. In short, we have here in the field of the theory of electricity a tradition just as highly developed as in the field of theology. And since in both fields the results of recent research, the establishment of hitherto unknown or disputed facts and of the necessarily following theoretical conclusions run pitilessly counter to the old traditions, the defenders of these traditions find themselves in the direst dilemma. They have to resort to all kinds of subterfuges and untenable expedients, to the glossing over of irreconcilable contradictions, and thus finally land themselves into a medley of contradictions from which they had to escape. It is this faith in all the old theory of electricity that entangles Weidmann here in the most hopeless contradictions, simply owing to the hopeless attempt to reconcile rationally the old explanation of the current by contact force with the modern one by liberation of chemical energy. It will perhaps be objected that the above criticism of Weidmann's explanation of the current rests on juggling with words. It may be objected that, although at the beginning Weidmann expresses himself somewhat carelessly and inaccurately, still he does finally give the correct account in accord with the principle of the conservation of energy, and so sets everything right. As against this view, we give below another example, his description of the process in a battery, zinc dilute sulfuric acid copper. If, however, the two plates are joined by wire, a galvanic current arises. By the electrolytic process, one equivalent of hydrogen is given off at the copper plate from the water of the dilute sulfuric acid, this hydrogen escaping in bubbles. At the zinc there is formed one equivalent of oxygen which oxidizes the zinc to form zinc oxide, the latter becoming dissolved in the surrounding acid to form sulfuric zinc oxide. To break up water into hydrogen and oxygen requires an amount of energy of 68,924 heat units for each molecule of water. From where then comes the energy in the above cell? By the electrolytic process. And from where does the electrolytic process get it? No answer is given. But Weidmann further tells us, not once, but at least twice, that according to recent knowledge the water itself is not decomposed, but that in our case it is the sulfuric acid H, so it splits up into H on the one hand, and it is so plus O on the other hand, whereby under suitable conditions H and O can escape in gaseous form. But this alters the whole nature of the process. The H of the H so is directly replaced by the bivalent zinc, forming zinc sulfate, ZnSO. There remains over, on the one side H, on the other so plus O. The two gases escape in the proportions in which they unite to form water. The SO unites with the water of the solvent to reform H, so I sulfuric acid. The formation of ZnSO, however, develops sufficient energy not only to replace and liberate the hydrogen of the sulfuric acid, but also to leave over a considerable excess, which in our case is expended in forming the current. Hence the zinc does not wait until the electrolytic process puts free oxygen at its disposal, in order first to become oxidized and then to become dissolved in the acid. On the contrary, it enters directly into the process, which only comes into being at all by its participation of the zinc. We see here how obsolete chemical notions come to the aid of the obsolete contact notions. According to modern views, a salt is an acid in which hydrogen has been replaced by a metal. The process under investigation confirms this view. The direct replacement of the hydrogen of the acid by the zinc fully explains the energy change. The old view, adhered to by Weidmann, regards a salt as a compound of a metallic oxide with an acid, and therefore speaks of sulfuric zinc oxide instead of zinc sulfate. But to arrive at sulfuric zinc oxide in our battery of zinc and sulfuric acid, the zinc must first be oxidized. In order to oxidize the zinc fast enough, we must have free oxygen. In order to get free oxygen, we must assume, since hydrogen appears at the copper plate, that the water is decomposed. In order to decompose water, we need tremendous energy. How are we to get this? Simply by the electrolytic process, which itself cannot come into operation as long as its chemical end product, the sulfuric zinc oxide, has not begun to be formed. The child gives birth to the mother. Consequently, here again Weidmann puts the whole course of the process absolutely the wrong way around and upside down, and the reason is that he lumps together active and passive electrolysis, two directly opposite processes, simply as electrolysis. So far we have only examined the events in the battery, that is that process in which an excess of energy is set free by chemical action and is converted into electricity by the arrangements of the battery. But it is well known that this process can also be reversed. The electricity of a constant current produced in the battery from chemical energy can, in its turn, be reconverted into chemical energy in a decomposition cell inserted in the circuit. The two processes are obviously the opposites of each other. If the first is regarded as chemico-electric, then the second is electrochemical. Both can take place in the same circuit with the same substances. Thus, the voltaic pile from gas elements, the current of which is produced by the union of hydrogen and oxygen to form water, can, in a decomposition cell inserted in the circuit, furnish hydrogen and oxygen in the proportion in which they form water. The usual mode of view lumps these two opposite processes together in a single expression, electrolysis, and does not even distinguish between active and passive electrolysis, between an exciting liquid and a passive electrolyte. Thus Weidmann treats of electrolysis in general for 143 pages, and then adds at the end some remarks on electrolysis in the battery, in which, moreover, the processes in actual batteries only occupy the lesser part of the 17 pages of this section. Also in the theory of electrolysis, that follows, this contrast of battery and decomposition cell is not even mentioned, and anyone who look for some treatment of the energy changes in the circuit in the next chapter, the influence of electrolysis on the conduction resistance and the electromotive force in the circuit would be bitterly disappointed. Let us now consider the irresistible electrolytic process, which is able to separate H from O without visible supply of energy, and which plays the same role in the present section of the book as did previously the mysterious electric force of separation. Besides the primary, purely electrolytic process of separation of the ions, a quantity of secondary, purely chemical processes, quite independent of the first, take place by the action of the ions split off by the current. This action can take place on the material of the electrodes and on the bodies that are decomposed, and in the case of solutions also on the solvent. Let us return to the above-mentioned battery, zinc and copper and dilute sulfuric acid. Here, according to Weidmann's own statement, the separated ions are the H and O of the water. Consequently, for him the oxidation of the zinc and the formation of zinc is a secondary, purely chemical process, independent of the electrolytic process, in spite of the fact that it is only through it that the primary process becomes possible. Let us now examine somewhat in detail the confusion that must necessarily arise from this inversion of the true course of events. Let us consider in the first place the so-called secondary processes in the decomposition cell, of which Weidmann puts forward some examples. The electrolysis of H2SO4 dissolved in water. This breaks up into one equivalent of SO3 plus O and one equivalent of Na. The latter, however, reacts on the water solvent and splits off from it one equivalent of H, while one equivalent of sodium is formed and becomes dissolved in the surrounding water. The equation is SO plus 2HO equals O plus O plus 2 NO plus 2H. In fact, in this example, the decomposition of SO equals NO plus O could be regarded as the primary electrochemical process, and the further transformation of plus 2HO equals 2 NO plus 2H as the secondary, purely chemical one. But this secondary process is effected immediately at the electrode, where the hydrogen appears. The very considerable quantity of energy, 111,810 heat units for Na, O, H, HAC. According to Julius Thomson, the biliberated is therefore, at least for the most part, converted into electricity, and only a portion in the cell is transformed directly into heat. But the latter can also happen to the chemical energy directly or primarily liberated in the battery. The quantity of energy which has thus become available and converted into electricity, however, is to be subtracted from that which the current is to supply for continued decomposition of the NO if the conversion of sodium into hydrated oxide appeared in the first moment of the total process as a secondary process. From the second moment onwards it becomes an essential factor of the total process and so ceases to be secondary. But yet a third process takes place in this decomposition cell, so combines with HO to form HSO, sulfuric acid, provided the SO does not enter into combination with the metal of the positive electrode, in which case again energy would be liberated. But this change does not necessarily proceed immediately at the electrode, and consequently the quantity of energy thereby liberated becomes converted wholly or mainly into heat in the cell itself, and provides at most a very small portion of the electricity in the current. The only really secondary process occurring in the cell is therefore not mentioned at all by Weidmann. 2. If a solution of copper sulfate is electrolyzed between a positive copper electrode and a negative one of platinum, one equivalent of copper separates after one equivalent of water decomposes the negative platinum electrode. With simultaneous decomposition of sulfuric acid in the same current circuit, at the positive electrode, one equivalent of SO4 should make its appearance, but this combines with the copper of the electrode to form one equivalent of QSO4, which becomes dissolved in water of the electrolyzed solution. In the modern chemical mode of expression we have, therefore, to represent the process as follows: copper is deposited onto platinum. The liberated SO, which cannot exist by itself, splits up into SO plus O, the latter escaping in the free state. The SO takes up HO from the aqueous solvent and forms HSO, which again combines with the copper of the electrode to form QSO, H being set free. Accurately speaking, we have here three processes: the separation of Cu and SO plus O plus HO equals HSO plus O, HSO plus C equals H plus C. So it is natural to regard the first as primary, the two others as secondary. But if we inquire into the energy changes, we find that the first process is completely compensated by part of the third, the separation of copper from SO by the reuniting of both at the other electrode. If we leave out of account the energy required for shifting the copper from one electrode to the other, and likewise the inevitable, not accurately determinable, loss of energy in the cell by conversion into heat, we have here a case where the so-called primary process withdraws no energy from the current. The current provides energy exclusively to make possible the separation of H and O, which moreover is indirect, and this proves to be the real chemical result of the whole process, hence, for carrying out a secondary, or even tertiary, process. Nevertheless, in both the above examples, as in other cases also, it is undeniable that the distinction of primary and secondary processes is a relative justification. Thus in both cases, among other things, water also is apparently decomposed in the elements of water given off at the opposite electrodes. Since, according to the most recent experiments, absolutely pure water comes as near as possible to being an ideal non-conductor, hence also a non-electrolyte, it is important to show that in these and similar cases it is not the water that is directly electrochemically decomposed, but that the elements of water are separated from the acid, in the formation of which here it is true the water solvent must participate. 3. If one electrolyzes hydrochloric acid simultaneously in two tubes, using in one tube a zinc positive electrode and in the other tube one of copper, then in the first tube a quantity of zinc 32.53 is dissolved, in the other a quantity of copper 2x32.7. For the time being let us leave the copper out of account and consider the zinc. The decomposition of HCl is regarded here as the primary process, the solution of Zn as secondary. According to this conception, therefore, the current brings to the decomposition cell from outside the energy necessary for the separation of H and Cl, and after the separation is completed the Cl combines with the Zn, whereby quantity of energy is set free that is subtracted from that required for separating H and Cl. The current needs only therefore to supply the difference. So far everything agrees beautifully, but if we consider the two amounts of energy more closely we find that the one liberated on the formation of ZnCl is larger than that used up in separating 2HCl, consequently, that the current not only does not need to supply energy, but on the contrary receives energy. We are no longer confronted by a passive electrolyte, but by an exciting fluid, not a decomposition cell but a battery, which strengthens the current forming voltaic pile by a new element. The process which we are supposed to conceive as secondary becomes absolutely primary, becoming the source of energy of the whole process and making the latter independent of the current supplied by the voltaic pile. We see clearly here the source of the whole confusion prevailing in Weidmann's theoretical description. Weidmann's point of departure is electrolysis. Whether this is active or passive, battery or decomposition cell, is all one to him. Sawbones is sawbones, as the sergeant major said to the doctor of philosophy doing his year's military service. And since it is easier to study electrolysis in the decomposition cell than in the battery, he does, in fact, take the decomposition cell as his point of departure, and he makes the processes taking place in it, and the partly justifiable division of them into primary and secondary, the measure of the altogether reverse processes in the battery, not even noticing when his decomposition cell becomes surreptitiously transformed into a battery. Hence he is able to put forward the statement, the chemical affinity that the separated substances have for the electrodes has no influence on the electrolytic process as such, a sentence which in its absolute form, as we have seen, is totally false. Hence, further, his threefold theory of current formation, firstly, the old traditional one, by means of pure contact, secondly, that derived by means of the abstractly conceived electric force of separation, which in an inexplicable manner obtains for itself or for the electrolytic process the requisite energy for splitting apart the H and Cl in the battery and for forming a current as well, and finally, the modern chemico-electric theory which demonstrates the source of this energy in the algebraic sum of the chemical reactions in the battery. Just as he does not notice that the second explanation overthrows the first, so also he has no idea that the third in its turn overthrows the second. On the contrary, the principle of the conservation of energy is merely added in a quite superficial way to the old theory handed down from routine, just as a new geometrical theorem is appended to an earlier one. He has no inkling that this principle makes necessary a revision of the whole traditional point of view, and this is in all other fields of natural science. Hence Weidmann confines himself to noting the principle in his explanation of the current, and then calmly puts it on one side, taking it up again only right at the end of the book, in the chapter on the work performed by the current. Even in the theory of the excitation of electricity by contact, the conservation of energy plays no role at all in relation to the chief subject dealt with, and is only incidentally brought in for throwing light on subsidiary matters. It is and remains a secondary process. Let us return to the above example 3. There the same current was used to electrolyze hydrochloric acid in 2 U-tubes, but in one there was a positive electrode of zinc, in the other, the positive electrode used was of copper. According to Faraday's basic law of electrolysis, the same galvanic current decomposes in each cell equivalent quantities of electrolyte, and the quantities of the substances liberated at the 2 electrodes are also in proportion to their equivalents. In the above case, it was found that in the first tube a quantity of zinc 32.53 was dissolved, and in the other quantity of copper 2x31.7. Nevertheless, continues Weidmann, this is no proof for the equivalence of these values. They are observed only in the case of very weak currents with the formation of zinc chloride, on the one hand, and of copper chloride, on the other. In the case of denser currents, with the same amount of zinc dissolved, the quantity of dissolved copper would sink with formation of increasing quantities of chloride, up to 31.7. It is well known that zinc forms only a single compound with chlorine, zinc chloride, ZnCl. Copper on the other hand forms 2 compounds, cupric chloride, Cl, and cuprous chloride, CuCl. Hence the process is that the weak current splits off 2 copper atoms from the electrode for each 2 chlorine atoms, the 2 copper atoms remaining united by one of their 2 valencies, while their 2 free valencies unite with the 2 chlorine atoms, Cl, Cu, Cu, Cl. On the other hand, if the current becomes stronger, it splits the copper atoms apart altogether, and each one unites with 2 chlorine atoms, Cl, Cu, Cl. In the case of currents of medium strength, both compounds are formed side by side. Thus it is solely the strength of the current that determines the formation of one or the other compound, and therefore the process is essentially electrochemical, if this word has any meaning at all. Nevertheless, Weidmann declares explicitly that it is secondary, hence not electrochemical, but purely chemical. The above experiment is one performed by Renault, and is one of the whole series of similar experiments in which the same current is led in one U-tube through salt solution, positive electrode, zinc, and in another cell through a varying electrolyte with various metals as the positive electrode. The amounts of the other metals dissolved here for each equivalent of zinc diverge very considerably, and Weidmann gives the results of the whole series of experiments which, however, in point of fact, are mostly self-evident chemically and could not be otherwise. Thus, for one equivalent of zinc, only 2/3 of an equivalent of gold is dissolved in hydrochloric acid. This can only appear remarkable if, like Weidmann, one adheres to the old equivalent weights and writes ZnCl for zinc chloride, according to which both the chlorine and the zinc appear in the chloride with only a single equivalency. In reality, 2 chlorine atoms are included in 1 zinc atom, ZnCl, and as soon as we know this formula we see at once that in the above determination of equivalence, the chlorine atom is to be taken as the unit and not the zinc atom. The formula for gold chloride, however, is alkyl, from which it is at once seen that 3ZnCl contains exactly as much chlorine as 2 alkyl, and so all primary, secondary, and tertiary processes in the battery or cell are compelled to transform, for each part by weight of zinc converted into zinc chloride, neither more nor less than 2/3 of a part by weight of gold into gold chloride. This holds absolutely unless the compound alkyl also could be prepared by galvanic means, in which case 2 equivalents of gold even would have to be dissolved for 1 equivalent of zinc, when also similar variations according to the current strength could occur as in the case of copper and chlorine mentioned above. The value of Renault's researches consists in the fact that they show how Faraday's law is confirmed by facts that appear to contradict it, but what they are supposed to contribute in throwing light on secondary processes in electrolysis is not evident. Weidmann's third example led us again from the decomposition cell to the battery, and in fact the battery offers by far the greatest interest when one investigates the electrolytic processes in relation to the transformations of energy taking place. Thus we not infrequently encounter batteries in which the chemical-electric processes seem to take place in direct contradiction to the law of the conservation of energy and in opposition to chemical affinity. According to Poggendorff's measurements, the battery, zinc, concentrated salt solution, platinum, provides a current of strength 134.6. Hence we have here quite a respectable quantity of electricity, 1/3 more than the Daniell cell. What is the source of the energy appearing here as electricity? The primary process is the replacement of sodium in the chlorine compound by zinc. But in ordinary chemistry it is not zinc that replaces sodium, but vice versa, sodium replacing zinc from chlorine and other compounds. The primary process, far from being able to give the current the above quantity of energy, on the contrary requires itself a supply of energy from outside in order to come into being. Hence, with a mere primary process we are again at a standstill. Let us look, therefore, at the real process. We find that the change is not Zn plus 2 NaCl equals ZnCl plus 2Na, but Zn plus 2 NaCl plus 2 HO equals ZnCl plus 2NO plus H. In other words, the sodium is not split off in the free state of the negative electrode, but forms hydroxide as in the above example I. To calculate the energy changes taking place here, Julius Thomson's determinations provide us at least with certain important data. According to them, the energy liberated on combination is as follows. Equals 97,210, equals 15,630, making a total for dissolved zinc chloride. Equals 112,840 heat units. 2. Equals 223,620, 336,460, deducting consumption of energy on the separations. 2. Equals 193,020 heat units. 2. Equals 136,720, 329,740. The excess of liberated energy equals 6,720 heat units. This amount is obviously small for the current strength obtained, but it suffices to explain, on the one hand, the separation of the sodium from chlorine, and on the other hand, the current formation in general. We have here a striking example of the fact that the distinction of primary and secondary processes is purely relative and leaves us ad absurdum as soon as we take it absolutely. The primary electrolytic process, taken alone, not only cannot produce any current, but cannot even take place itself. It is only the secondary, ostensibly purely chemical process that makes the primary one possible and, moreover, supplies the whole surplus energy for current formation. In reality, therefore, it proves to be the primary process, and the other the secondary one. When the rigid differences in opposites, as imagined by the metaphysicians and metaphysical natural scientists, were dialectically reversed into their opposites by Hegel, it was said that he had twisted the words in their mouths. But if nature itself proceeds exactly like old Hegel, it is surely time to examine the matter more closely. With greater justification one can regard as secondary those processes which, while taking place in consequence of the chemical-electric process of the battery or the electrochemical process of the decomposition cell, do so independently and separately, occurring therefore at the same distance from the electrodes. The energy changes taking place in such secondary processes likewise do not enter into the electric process. Directly they neither withdraw energy from it nor supply energy to it. Such processes occur very frequently in the decomposition cell. We saw an instance in the example above on the formation of sulfuric acid during electrolysis of sodium sulfate. They are, however, of lesser interest here. Their occurrence in the battery, on the other hand, is of greater practical importance, for although they do not directly supply energy to, or withdraw it from, the chemical-electric process, nevertheless they alter the total available energy present in the battery and thus affect it indirectly. There belong here, besides subsequent chemical changes of the ordinary kind, the phenomena that occur when the ions are liberated at the electrodes in a different condition from that in which they usually occur in the free state, and when they pass over to the latter only after moving away from the electrodes. In such cases the ions can assume a different density or a different state of aggregation. They can also undergo considerable changes in regard to their molecular constitution, and this case is the most interesting. In all these cases, an analogous heat change corresponds to the secondary chemical or physical change of the ions taking place at a certain distance from the electrodes. Usually heat is set free, in some cases it is consumed. This heat change is, of course, restricted in the first place to the place where it occurs. The liquid in the battery or decomposition cell becomes warmer or cooler while the rest of the circuit remains unaffected. Hence this heat is called local heat. The liberated chemical energy available for conversion into electricity is, therefore, diminished or increased by the equivalent of this positive or negative local heat produced in the battery. According to Farr, in a battery with hydrogen peroxide and hydrochloric acid 2/3 of the total energy set free is consumed as local heat. The Grove cell, on the other hand, on closing the circuit became considerably cooler and therefore supplied energy from outside to the circuit by absorption of heat. Hence we see that these secondary processes also react on the primary one. We can make whatever approach we like. The distinction between primary and secondary processes remains merely a relative one and is regularly suspended in the interaction of the one with the other. If this is forgotten and such relative opposites treated as absolute, one finally gets hopelessly involved in contradictions, as we have seen above. As is well known, on the electrolytic separation of gases, the metal electrodes become covered with a thin layer of gas. In consequence, the current strength decreases until the electrodes are saturated with gas, whereupon the weakened current again becomes constant. Farth and Silberman have shown that local heat arises also in such a decomposition cell. This local heat, therefore, can only be due to the fact that the gases are not liberated at the electrodes in the state in which they usually occur, but that they are only brought into their usual state after their separation from the electrode by a further process bound up with the development of heat. But what is the state in which the gases are given off at the electrodes? It is impossible to express oneself more cautiously on this than Weidmann does. He terms it as certain, an allotropic, an active, and finally, in the case of oxygen, several times an ozonized state. In the case of hydrogen, his statements are still more mysterious. Incidentally, the view comes out that ozone and hydrogen peroxide are the forms in which this active state is realized. Our author is so keen in his pursuit of ozone that he even explains the extreme electronegative properties of certain peroxides from the fact that they possibly contain a part of the oxygen in the ozonized state. Certainly both ozone and hydrogen peroxide are formed on the so-called decomposition of water, but only in small quantities. There is no basis at all for assuming that in the case mentioned local heat is produced first of all by the origin and then by the decomposition of any large quantities of the above two compounds. We do not know the heat of formation of ozone, O, from free oxygen atoms. According to Berthelot, the heat of formation of hydrogen peroxide from HO plus O equals 21,480. The origin of this compound in any large amount would therefore give rise to a large excess of energy, which could not be evident and demonstrable. Finally, ozone and hydrogen peroxide would only take oxygen into account, but not hydrogen. Yet the latter also escapes in an active state, so much so that in the combination, potassium nitrate solution between platinum electrodes, it combines directly with the nitrogen split off from the acid to form ammonia. In point of fact, all these difficulties and doubts have no existence. The electrolytic process has no monopoly of splitting off bodies in an active state. Every chemical decomposition does the same thing. It splits off the liberated chemical elements in the first place in the form of free atoms of O, H, N, etc., which only after their liberation can unite to form molecules O, H, N, etc. And on thus uniting give off a definite, though up to now still undetermined, quantity of energy which appears as heat. But during the infinitesimal moment of time, when the atoms are free, they are the bearers of the total quantity of energy that they can take up at all. While possessed of their maximum energy, they are free to enter into any combination offered them. Hence they are in an active state, in contrast to the molecules O, H, N, which have already surrendered a part of this energy and cannot enter into combination with other elements without this quantity of energy surrendered being resupplied from outside. We have no need, therefore, to resort to ozone and hydrogen peroxide, which themselves are only products of this active state. For instance, we can undertake the above-mentioned formation of ammonia and electrolysis of potassium nitrate even without a battery, simply by chemical means, by adding to nitric acid or a nitrate solution a liquid in which hydrogen is set free by a chemical process. In both cases, the active state of the hydrogen is the same, but the interesting point about the electrolytic process is that here the transitory existence of the free atoms becomes as it were tangible. The process here is divided into two phases. The electrolysis provides free atoms at the electrodes, but their combination to form molecules occurs at some distance from the electrodes. However, infinitesimally minute this distance may be compared to measurements where masses are concerned. It suffices to prevent the energy liberated on formation of the molecules being used for the electric process, at least for the most part, and so determines its conversion into heat, the local heat in the battery. But it is owing to this that the fact is established that the elements are split off as free atoms, and for a moment have existed in the battery as free atoms. This fact, which in pure chemistry can only be established by theoretical conclusions, is here proved experimentally, insofar as this is possible without sensuous perception of the atoms and molecules themselves. Herein lies the high scientific importance of the so-called local heat of the battery. The conversion of chemical energy into electricity by means of the battery is a process about whose course we know next to nothing, and which we shall get to know in more detail only when the modus operandi of electric motion itself becomes better known. The battery is ascribed to an electric force of separation which is given for each particular battery. As we saw at the outset, Weidmann conceded that this electric force of separation is not a definite form of energy. On the contrary, it is primarily nothing more than the capacity, the property, of a battery to convert a definite quantity of liberated chemical energy into electricity in unit time. Throughout the whole course of events, this chemical energy itself never assumes the form of an electric force of separation, but, on the contrary, at once and immediately takes on the form of so-called electromotive force, that is of electric motion. If in ordinary life we speak of the force of a steam engine in the sense that it is capable in unit time of converting a definite quantity of heat into the motion of masses, this is not a reason for introducing the same confusion of ideas into scientific thought also. We might just as well speak of the varying force of a pistol, a carbine, a smoothbore gun, and a blunderbuss, because, with equal gunpowder charges and projectiles of equal weight, they shoot varying distances. But here the wrongness of the expression is quite obvious. Everyone knows that it is the ignition of the gunpowder charge that drives the bullet, and that the varying range of the weapon is only determined by the greater or lesser dissipation of energy according to the length of the barrel, the form of the projectile, and the tightness of its fitting. But it is the same for steam power and for the electric force of separation. Two steam engines, other conditions being equal, that is assuming the quantity of energy liberated in equal periods of time to be equal in both, or two galvanic batteries, of which the same thing holds good, differs regards performance at work only owing to the greater or lesser dissipation of energy. And if until now all armies have been able to develop the technique of firearms without the assumption of a special shooting force of weapons, the science of electricity has absolutely no excuse for assuming an electric force of separation analogous to this shooting force, a force which embodies absolutely no energy, and which therefore of itself cannot perform a millionth of a milligram meter of work. The same thing holds good for the second form of this force of separation, the electric force of contact of metals, mentioned by Helmholtz. It is nothing but the property of metals to convert on their contact the existing energy of another form into electricity. Hence it is likewise a force that does not contain a particle of energy. If we assume with Weidmann that the source of energy of contact electricity lies in the vis viva of the motion of adhesion, then this energy exists in the first place in the form of this mass motion, and on its vanishing becomes converted immediately into electric motion, without even for a moment assuming the form of an electric force of contact. And now we are assured in addition to the electromotive force, that is the chemical energy, reappearing as electric motion is proportional to this electric force of separation, which not only contains no energy, but owing to the very conception of it cannot contain any. This proportionality between non-energy and energy obviously belongs to the same mathematics as that in which there figures the ratio of the unit of electricity to the milligram. But the absurd form, which owes its existence only to the conception of a simple property of the mystical force, conceals a quite simple tautology. The capacity of a given battery to convert liberated chemical energy into electricity is measured by what? By the quantity of the energy reappearing in the circuit as electricity in relation to the chemical energy consumed in the battery. That is all. In order to arrive at an electric force of separation, one must take seriously the device of the two electric fluids. To convert this from its neutrality to its polarity, hence to split it apart, requires a certain expenditure of energy, the electric force of separation. Once separated, the two electricities can, on being reunited, again give off the same quantity of energy, electromotive force. But since nowadays no one, not even Weidmann, regards the two electricities as having a real existence, it means that one is writing for a defunct public if one deals at length with such a point of view. The basic error of the contact theory consists in the fact that it cannot divorce itself from the idea that contact force or electric force of separation is a source of energy, which of course was difficult when the mere capacity of an apparatus to bring about transformation of energy had been converted into a force, for indeed, a force ought precisely to be a definite form of energy. Because Weidmann cannot rid himself of his unclear notion of force, although alongside of it the modern ideas of indestructible and uncreatable energy have been forced upon him, he falls into his nonsensical explanation of the current, number one, and into all the later demonstrated contradictions. If the expression electric force of separation is directly contrary to reason, the other electromotive force is at least superfluous. We had heat engines long before we had electromotors, and yet the theory of heat has been developed quite well without any special thermomotor force. Just as the simple expression heat includes all phenomena of motion that belong to this form of energy, so also can the expression electricity in its own sphere. Moreover, very many forms of action of electricity are not at all directly motor, the magnetization of iron, chemical decomposition, conversion into heat, and finally, in every natural science, even in mechanics, it is always an advance if the word force can somehow be got rid of. We saw that Weidmann did not accept the chemical explanation of the processes in the battery without a certain reluctance. This reluctance continually attacks him, where he can blame anything on the so-called chemical theory. This is certain to occur. Thus, it is by no means established that the electromotive force is proportional to the intensity of chemical action. Certainly not in every case, but where this proportionality does not occur, it is only a proof that the battery has been badly constructed, that dissipation of energy takes place in it. For that reason, Wieman is quite right in paying no attention in his theoretical deductions to such subsidiary circumstances which falsify the purity of the process, but in simply assuring us that the electromotive force of a cell is equal to the mechanical equivalent of the chemical action taking place at a unit time with unit intensity of current. In another passage we read that further, in the acid-alkali battery, the combination of acid and alkali is not the cause of current formation follows from the experiments paragraph 61, paragraph 260, and paragraph 261, according to which in certain cases when these are present in equivalent quantities no current makes its appearance, and likewise from the experiments mentioned in paragraph 62, that on interposing a solution of potassium nitrate between the potassium hydroxide and nitric acid, the electromotive force makes its appearance in the same way as without this interposition. The question whether the combination of acid and alkali is the cause of current formation is a matter of very serious concern for our author. Put in this form it is very easy to answer. The combination of acid and alkali is first of all the cause of a salt being formed with liberation of energy. Whether this energy wholly or partly takes the form of electricity depends on the circumstances under which it is liberated. For instance, in the battery, nitric acid and potassium hydroxide between platinum electrodes, this will be at least partially the case, and it is a matter of indifference for the formation of the current whether a potassium nitrate solution is interposed between the acid and alkali or not, since this can at most delay the salt formation but not prevent it. If, however, a battery is formed like one of Wurm-Muller's, to which Wiedemann constantly refers, where the acid and alkali solution is in the middle, but a solution of their salt at both ends, and in the same concentration as the solution that is formed in the battery, then it is obvious that no current can arise, because on account of the end members, since everywhere identical bodies are formed, no ions can be produced. Hence the conversion of the liberated energy into electricity has been prevented in as direct a manner as if the circuit had not been closed. It is therefore not to be wondered at that no current is obtained. But that acid and alkali can in general produce a current is proved by the battery, carbon, sulfuric acid, potassium hydroxide, carbon, which according to Raoult has a current strength of 73. And that, with suitable arrangement of the battery, acid and alkali can provide a current strength corresponding to the large quantity of energy set free on their combination, is seen from the fact that the most powerful batteries known depend almost exclusively on the formation of alkali salts. For example, that of wheatstone, platinum, palladium chloride, potassium amalgam, current strength 230, lead peroxide, dilute sulfuric acid, potassium amalgam equals 326, manganese peroxide instead of lead peroxide equals 280. In each case, if zinc amalgam was employed instead of potassium amalgam, the current strength fell almost exactly by 100. Similarly, in the battery, manganese dioxide, potassium per manganate solution, potassium hydroxide, potassium beats obtained the current strength 302, and further, platinum, dilute sulfuric acid, potassium equals 293. 8. Joule, platinum, nitric acid, potassium hydroxide, potassium amalgam equals 302. The cause of these exceptionally strong current strengths is certainly the combination of acid and alkali, or alkali metal, and the large quantity of energy thereby liberated. A few pages further on it is again stated. It must, however, be carefully borne in mind that the equivalent and work of the whole chemical action taking place at the place of contact of the heterogeneous bodies is not to be directly regarded as a measure of the electromotive force in the circuit. When, for instance, in the acid-alkali battery of Becquerel, these two substances combine, when carbon is consumed in the battery, platinum, molten potassium nitrate, carbon, when the zinc is rapidly dissolved in an ordinary cell of copper, impure zinc, dilute sulfuric acid, with formation of local currents, then a large part of the work produced in these chemical processes is converted into heat and is thus lost for the total current circuit. All these processes are to be referred to loss of energy in the battery. They do not affect the fact that the electric motion arises from transformed chemical energy, but only affect the quantity of energy transformed. Electricians have devoted an endless amount of time and trouble decomposing the most diverse batteries and measuring their Electricians have devoted an endless amount of time and trouble decomposing the most diverse batteries and measuring their electromotive force. The experimental material thus accumulated contains very much of value, but certainly still more is valueless. For instance, what is the scientific value of experiments in which water is employed as the electrolyte, when, as has now been proved by F. Cole Rausch, water is the worst conductor and therefore also the worst electrolyte, and where, therefore, it is not the water but its unknown impurities that cause the process. And yet, for instance, almost half of all Fechner's experiments depend on such employment of water, even his experimentum crucis, by which he sought to establish the contact theory impregnably on the ruins of the chemical theory. As is already evident from this, in almost all such experiments, a few only accepted the chemical processes in the battery, which however form the source of the so-called electromotive force, remain practically disregarded. There are, however, a number of batteries whose chemical composition does not allow of any certain conclusion being drawn as to the chemical changes proceeding in them when the current circuit is closed. On the contrary, as Wiedemann says, it is not to be denied that we are by no means in all cases able to obtain an insight into the chemical attractions in the battery. Hence, from the ever more important chemical aspect, all such experiments are valueless insofar as they are not repeated with these processes under control. In these experiments it is indeed only quite by way of exception that any account is taken of the energy changes taking place in the battery. Many of them were made before the law of the equivalence of motion was recognized in natural science, but as a matter of custom they continue to be dragged from one textbook into another without being controlled or their value summed up. It has been said that electricity is no inertia, but this certainly cannot be said of the theory of electricity. So far, we have regarded the galvanic cell as all arrangements in which, in consequence of the contact relations established, chemical energy is liberated in some way for the time being unknown and converted into electricity. We have likewise described the decomposition cell as an apparatus in which the reverse process is set up, electric motion being converted into chemical energy and used. Of such, in so doing we had to put in the foreground the chemical side of the process that has been so much neglected by electricians, because this was the only way of getting rid of the lumber of notions handed down from the old contact theory and the theory of the two electric fluids. This once accomplished, the question was whether the chemical process in the battery takes place under the same conditions as outside it, or whether special phenomena make their appearance that are dependent on the electric excitation. In every science, incorrect notions are, in the last resort, apart from errors of observation, incorrect notions of correct facts. The latter remain even when the former are shown to be false. Although we have discarded the old contact theory, the established facts remain, of which they were supposed to be the explanation. Let us consider these, and with them the electric aspect proper of the process in the battery. It is not disputed that on the contact of heterogeneous bodies, with or without chemical changes, an excitation of electricity occurs which can be demonstrated by means of an electroscope or galvanometer. As we've already seen at the outset, it is difficult to establish in a particular battery the source of energy of these in themselves extremely limited phenomena of motion. It suffices that the existence of such an external source is generally conceded. In 1850-53, Cole Rausch published a series of experiments in which he assembled the separate components of the battery in pairs and tested the static electric stresses produced in each case. The electromotive force of the cell should then be composed of the algebraic sum of these stresses. Thus, taking the stress of ZnC equals 100, he calculates the relative strengths of the Daniell and Grove cells as follows. For the Daniell cell, ZnCu plus M log, ZnH so plus U so equals 100 plus 129 minus 21 equals 228. For the Grove cell, ZnPt plus M log, ZnH so plus Pt no equals 107 plus 129 plus 129 equals 405, which closely agrees with the direct measurement of the current strengths of these cells. These results, however, are by no means certain. In the first place, Wiedemann himself calls attention to the fact that Cole Rausch only gives the final result, but unfortunately no figures for the results of the separate experiments. In the second place, Wiedemann himself repeatedly recognizes that all attempts to determine quantitatively the electric excitation on contact of metals, and still more on contact of metal and fluid, are at least very uncertain on account of the numerous unavoidable sources of error. If, nevertheless, Lie repeatedly uses Cole Rausch's figures in his calculations, we shall do better not to follow him here, the more so as another means of determination is available which is not open to these objections. If the two exciting plates of the battery are immersed in liquid and then joined into a circuit by the terminals of a galvanometer, according to Wiedemann, the initial deflection of its magnetic needle, before chemical changes have altered the strength of the electric excitation, is a measure of the sum of electromotive forces in the circuit. Batteries of various strengths, therefore, give initial deflections of various strengths, and the magnitude of these initial deflections is proportional to the current strength of the corresponding batteries. It looks as if we had here tangibly before our eyes the electric force of separation, the contact force, which causes motion independently of any chemical action, and this in fact is the opinion of the whole contact theory. In reality, we are confronted here by a relation between electric excitation and chemical action that we have not yet investigated. In order to pass to this subject, we shall first of all examine rather more closely the so-called electromotive law. In so doing, we shall find that here also the traditional contact notions not only provide no explanation, but once again directly bar the way to an explanation. If in any cell consisting of two metals in a liquid, for example zinc, dilute hydrochloric acid, and copper, one inserts a third metal such as the platinum plate without connecting it to the external circuit by wire, then the initial deflection of the galvanometer will be exactly the same as without the platinum plate. Consequently, it has no effect on the excitation of electricity. But it is not permissible to express this so simply in electromotive language. Hence one reads: the sum of the electromotive forces of zinc and platinum copper now takes the place of the electromotive force of zinc and copper in the liquid. Since the path of the electricity is not perceptibly altered by the insertion of the platinum plate, we can conclude from the identity of the galvanometer rings in the two cases that the electromotive force of zinc and copper in the liquid is equal to that of zinc and platinum plus that of platinum and copper in the same liquid. This would correspond to Volta's theory of the excitation of electricity between the metals as such. The result, which holds good for all liquids and metals, is expressed by saying, under electromotive excitation by liquids, metals follow the law of the Voltaic series. This law is also given the name of the electromotive law. In saying that in this combination the platinum does not act at all as an exciter of electricity, one expresses what is simply a fact. If one says that it does act as an exciter of electricity, but in two opposite directions with equal strength so that the effect is neutralized, the fact is converted into a hypothesis merely for the sake of doing honor to the electromotive force. In both cases, the platinum plays the role of a fictitious person. During the first deflection, there is still no closed circuit. The acids, being undecomposed, do not conduct. They can only conduct by means of the ions. If the third metal has no influence on the first deflection, this is simply a result of the fact that it is still isolated. How does the third metal behave after the establishment of the constant current during the latter? In the Voltaic series of metals in most liquids, zinc lies after the alkali metals fairly close to the positive end of platinum with the negative end, copper being between the two. Hence, if platinum is put as above between copper and zinc, it is negative to them both. If the platinum had any effect at all, the current in the liquid would have to flow to the platinum both from the zinc and from the copper, that is away from both electrodes to the unconnected platinum, which would be a contradictio in ejectio. An unconnected, superfluous metal in the battery acts as a non-conductor. It could neither form ions nor allow them to pass through, and without ions we know of no conduction in electrolytes. Hence, it is not merely a fictitious person. It even stands in the way by forcing the ions to go around it. The same thing holds good if we connect the zinc and platinum, leaving the copper unconnected in the middle. Here, the latter, if it had any effect at all, would produce a current from the zinc to the copper and another from the copper to the platinum. Hence, it would have to act as a sort of. If we discard the traditional electromotive mode of expression, the case becomes extremely simple. As we have seen, the galvanic battery is an apparatus in which chemical energy is liberated and transformed into electricity. It consists as a rule of one or more liquids and two metals as electrodes, which must be connected together by a conductor outside the liquids. This completes the apparatus. Anything else that is unconnected into the exciting liquid, whether metal, glass, resin, or whatever you like, cannot participate in the chemical electric process taking place in the battery and the formation of the current, so long as the liquid is not chemically altered. It can and must end the process. Whatever the capacity for exciting electricity of a third metal dipped into the liquid may be, or that one or both electrodes of the battery, it cannot have any effect so long as this metal is not connected to the circuit outside the liquid. Consequently, not only is Weeman's derivation, as given above, of the so-called electromotive law false, but the interpretation which he gives to this law is also false. One can speak neither of a compensating electromotive activity of the unconnected metal, since the sole condition for such activity is cut off from the outset, nor can the so-called electromotive law be deduced from a fact which lies outside the sphere of this law. In 1845, old Hagendorff published a series of experiments in which he measured the electromotive force of various batteries, that is to say the quantity of electricity supplied by each of them in unit time. Of these experiments, the first 27 are of special value, in each of which three given metals were one after another connected in the same exciting liquid into three different batteries, and the latter investigated and compared as regards the quantity of electricity produced. As a good adherent to the contact theory, Hagendorff also put the third metal unconnected in the battery in each experiment, and so had the satisfaction of convincing himself that in all 81 batteries this third metal remained a pure and active element in the combination. But the significance of these experiments by no means consists in this fact, but rather in the confirmation and establishment of the correct meaning of the so-called electromotive law. Let us consider the above series of batteries in which zinc, copper, and platinum are connected together in pairs in dilute hydrochloric acid. Here Hagendorff found the quantities of electricity produced to be as follows, taking the Daniel cell as 100, zinc copper, 78.8 copper platinum, 74.3, total, 153.1, zinc platinum, 153.7. Thus, zinc in direct connection with platinum produced almost exactly the same quantity of electricity as zinc, copper, platinum. The same thing occurred in all other batteries, whatever liquids and metals were employed. When, from a series of metals in the same exciting liquid, batteries were formed in such a way that in each case, according to the Voltaic series value for this liquid, the second, third, fourth, etc., one after the other were made to serve as negative electrodes for the preceding one and as positive electrodes for that which followed. Then the sum of the quantities of electricity produced by all these batteries is equal to the quantity of electricity produced by a battery formed directly between the two end members of the whole metallic series. For instance, in dilute hydrochloric acid, the sum total of the quantities of electricity produced by the batteries zinc, iron, copper, silver, and silver platinum would be equal to that produced by the battery zinc platinum. A power formed from all the cells of the above series with other things being equal, be exactly neutralized by the introduction of a zinc platinum cell with a current of the opposite direction. In this form, the so-called electromotive law has a real and considerable significance. It reveals a new aspect of the interconnection between chemical and electrical action. Hitherto, on investigating mainly the source of energy of the galvanic current, this source, the chemical change, appeared as the active side of the process. The electricity was produced from it and therefore appeared primarily as passive. Now this is reversed. The electric excitation determined by the constitution of the heterogeneous bodies put into contact in the battery can neither add nor subtract energy from the chemical action. It can, however, according as the battery is made up, accelerate or slow down this action. If the battery, zinc dilute hydrochloric acid copper, produced in unit time only half as much electricity for the current as the battery, zinc dilute hydrochloric acid platinum. This means in chemical terms that the first battery produces in unit time only half as much zinc chloride and hydrogen as the second. Hence the chemical action has been doubled, although purely chemical conditions for this action have remained the same. The electric excitation has become the regulator of the chemical action. It appears now as the active side, the chemical action being the passive side. Thus, it becomes comprehensible that a number of processes previously regarded as purely chemical now appears electrochemical. Chemically pure zinc is not attacked at all by dilute acid, or only very weakly. Ordinary commercial zinc, on the other hand, is rapidly dissolved with formation of a salt and production of hydrogen. It contains an admixture of other metals and carbon, which make their appearance in unequal amounts at various places of the surface. Local currents are formed in the acid between them and the zinc itself, the zinc areas forming the positive electrodes, and the other metals the negative electrodes, the hydrogen bubbles being given off on the latter. Likewise, the phenomenon that when iron is dipped into a solution of copper sulfate, it becomes covered with a layer of copper is now seen to be an electrochemical phenomenon, one determined by the currents which arise between the heterogeneous areas of the surface of the iron. In accordance with this, we find also that the Voltaic series of metals and liquids corresponds on the whole to the series in which metals replace one another from their compounds with halogens and acid radicals. At the extreme negative end of the Voltaic series, we regularly find the metals of the gold group, gold, platinum, palladium, rhodium, which oxidize with difficulty, are little or not at all attacked by acids, and which are easily precipitated from their salts by other metals. At the extreme positive end are the alkali metals, which exhibit exactly the opposite behavior. They are scarcely to be split off from their oxides except with the greatest expenditure of energy. They occur in nature almost exclusively in the form of salts. And of all the metals, they have by far the greatest affinity for halogens and acid radicals. Between these two come the other metals in somewhat varying sequence, but such that on the whole electrical and chemical behavior correspond to one another. The sequence of the separate members varies according to the liquids and has hardly been finally established for any single liquid. It is even permissible to doubt whether there exists such an absolute Voltaic series of metals for any single liquid. Given suitable batteries and decomposition cells, two pieces of the same metal can act as positive and negative electrodes respectively. Hence, the same metal can be both positive and negative towards itself. In thermal gels which convert heat into electricity, with large temperature differences at the two junctions, the direction of the current is reversed. The previously positive metal becomes negative and vice versa. Similarly, there is no absolute series according to which the metals replace one another from their chemical compounds with a particular halogen or acid radical. In many cases, by supplying energy in the form of heat, we are able almost at will to alter and reverse the series valid for ordinary temperatures. Hence, we find here a peculiar interaction between chemical action and electricity. The chemical action in the battery, which provides the electricity with the total energy for current formation, is in many cases first brought into operation, and in all cases quantitatively regulated by the electric charges developed in the battery. If previously the processes in the battery seem to be chemical electric in nature, we see here that they are just as much electrochemical. From the point of view of formation of the constant current, chemical action appears to be the primary thing. From the point of view of excitation of current, it appears as secondary and accessory. The reciprocal action excludes any absolute primary or absolute secondary, but it is just as much a double-sided process which from its very nature can be regarded from two different standpoints. To be understood in its totality, it must even be investigated from both standpoints one after the other, before the total result can be arrived at. If, however, we adhere on-sidedly to a single standpoint as the absolute one in contrast to the other, or if we arbitrarily jump from one to the other according to the momentary needs of our argument, we shall remain entangled in the on-sidedness of metaphysical thinking. The interconnection escapes us and we become involved in one contradiction after another. We saw that, according to Weeman, the initial deflection of the galvanometer, immediately after dipping the exciting plates into the liquid of the battery and before chemical changes have altered the strength of the electric excitation, is a measure of the sum of electromotive forces in the circuit. So far we have become acquainted with the so-called electromotive force as a form of energy, which in our case was produced in an equivalent amount from chemical energy, and which in the further course of the process became reconverted into equivalent quantities of heat, mass motion, etc. Here we learn all at once that the sum of the electromotive forces in the circuit is already in existence before this energy has been liberated by chemical changes. In other words, that the electromotive force is nothing but the capacity of a particular cell to liberate a particular quantity of chemical energy in unit time and to convert it into electric motion. As previously in the case of the electric force of separation, so here also the electromotive force appears as a force which does not contain a single spark of energy. Consequently, Weeman understands by electromotive force two totally different things. On the one hand, the capacity of a battery to liberate a definite quantity of given chemical energy and to convert it into electric motion. On the other hand, the quantity of electric motion itself that is developed. The fact that the two are proportional, that one is a measure for the other, does not do away with the distinction between them. The chemical action in the battery, the quantity of electricity developed, and the heat in the circuit derived from it, when no other work is performed, are even more than proportional. They are equivalent, but that does not infringe the diversity between them. The capacity of a steam engine with a given cylinder bore and piston stroke to produce a given quantity of mechanical motion from the heat supplied is very different from this mechanical motion itself, however proportional to it may be. And while such a mode of speech was tolerable at a time when natural science had not yet said anything of the conservation of energy, nevertheless it is obvious that since the recognition of this basic law it is no longer permissible to confuse real active energy in any form with the capacity of an apparatus to impart this form to energy which is being liberated. This confusion is a corollary of the confusion of force and energy in the case of the electric force of separation. These two confusions provide a harmonious background for Weeman's three mutually contradictory explanations of the current, and in the last resort are the basis in general for all his errors and confusions in regard to so-called electromotive force. Besides the above considered peculiar interaction between chemical action and electricity, there is also a second point that they have in common, which likewise indicates a closer kinship between these two forms of motion. Both can exist only for an infinitesimal period. The chemical process takes place suddenly for each group of atoms undergoing it. It can be prolonged only by the presence of new material that continually renews it. The same thing holds for electric motion. Hardly has it been produced from some other form of motion before it is once more converted into a third form. Only the continual readiness of available energy can produce a constant current in which at each moment new quantities of the form of energy and lose it again. An insight into this close connection of chemical and electric action and vice versa will lead to important results in both spheres of investigation. Such an insight is already becoming more and more widespread. Among chemists, Lotharmeyer and after him Kekulé have plainly stated that the revival of the electrochemical theory in a rejuvenated form is impending. Among electricians also, as indicated especially by the latest works of F. Rausch, the conviction seems finally to have taken hold that only exact attention to the chemical processes in the battery and decomposition cell can help their science to emerge from the blind alley of old traditions. And in fact, one cannot see how else a firm foundation is to be given to the theory of galvanism and so secondary to the magnetism and static electricity, other than by chemically exact general revision of all traditional uncontrolled experiments made from an obsolete scientific standpoint, with exact attention to establishing the energy changes and preliminary rejection of all traditional theoretical notions about electricity. Notes. 1. For the factual material in this chapter we rely mainly on Weeman's layer of galvanismus and electromagnetismus, 2 vols, in 3 parts, 2nd edition, Braunschweig, 1874. In Nature, June 15, 1882, there is a reference to this admirable treatise, which in its forthcoming shape, with electrostatics added, will be the greatest experimental treatise on electricity in existence. 2. The central discovery was J. Thomson's discovery of the electron. 3. 4. See Appendix 2, b. 334. 7. The view that electrical energy was located in the ether was the basis of the experiments which gave us radio. It seemed in turn to have been negated by the discovery of electrons. However, the electron in turn is now regarded by many physicists as a system of waves rather than a well-defined particle. 8. Every broadcast is a confirmation of this theory today. 9. Now called dynamos. This is less open to objection as much as any possible confusion with the state of stress of electricity is here expressly excluded in advance. 11. Once more it must be remembered that this term was very loosely used 60 years ago and now has a definite meaning, not of course equivalent to any form of energy. 12. That is kinetic energy. 13. As we should now say, an electrolyte. 14. F. Rausch has recently calculated that immense forces are required to drive the ions through the water solvent. To cause 1 milligram to move through a distance of 1 millimeter requires an attractive force which for H equals 32,500 kilograms, for Cl equals 5,200 kilograms, hence for HCl equals 37,700 kilograms. Even if these figures are absolutely correct, they do not affect what has been said above, but the calculation contains the hypothetical factors hitherto inevitable in the sphere of electricity and therefore requires control by experiment. Such control appears possible. In the first place, these immense forces must reappear as a definite quantity of energy in the place where they are consumed, that is in the above case in the battery. Secondly, the energy consumed by them must be smaller than that supplied by the chemical processes of the battery, and there should be a definite difference. Thirdly, this difference must be used up in the rest of the circuit and likewise be quantitatively demonstrable there. Only after confirmation by this control can the above figures be regarded as final. The demonstration in the decomposition cell appears still more susceptible of realization. Actually, the hypothesis was incorrect. It is now believed that when HCl is dissolved in water, it is almost completely broken up into positive H ions and negative Cl ions, which do not require immense forces to drive them. Engels was fully justified in his skepticism. 15. It may be noted here once for all that Weeman employs throughout the old chemical equivalent values, writing O, ZnCl, etc. in my equations. The modern atomic weights are everywhere employed, putting, therefore, HO, ZnCl, etc. 16. As it stands, this is untrue. Probably part by weight is a slip of Engels down for equivalent by weight or some such phrase. 17. Again, this does not make sense as it stands. Presumably Engels meant to refer to hypothetical alcohol. 18. This quantity has now not only been determined but utilized. Thus, if the hydrogen is previously split into atoms, the ordinary oxyhydrogen flame can be made a great deal hotter. 19. It has since been proved experimentally. 20. This statement has been very fully confirmed by the progress of physics in the last 50 years. It is interesting to note that idealistic writers have used this disappearance of the notion of force as an argument that materialism is being refuted. 21. In all the following data relating to current strength, the Daniell cell is put equals 100. 22. A column of appears water prepared by Rausch 1 millimeter in length offered the same resistance as a copper conductor of the same diameter and length approximately that of the moon's orbit. Naumann, Aldemine, Chem E, B. 729. Appendix 2, B. 335. 23. This statement is in accord with theory 50 years ago, but incorrect. 24. This is, of course, not electromotive force in the modern sense of the term. 25. This is, of course, been very completely verified by the researchers of the last 50 years. Electrical theory was revolutionized by Thomson's study of electrical conduction in gases, which led to his discovery of electrons. And the whole of chemistry, including the chemistry of such unions as that between carbon and hydrogen, which at first sight is quite unconnected with electrical phenomena, has been restated in terms of electrons. 8. Tidal friction. Kant and Thomson take on the rotation of the Earth and lunar attraction. Thomson and Tate, Nat, Philos, I, B. 191. There are also indirect resistances, owing to friction impeding the tidal motions, on all bodies which, like the Earth, have portions of their free surfaces covered by liquid, which, as long as these bodies move relatively to neighboring bodies, must keep drawing off energy from their relative motions. Thus, if we consider, in the first place, the action of the moon alone on the Earth with its oceans, lakes, and rivers, we perceive that it must tend to equalize the periods of the Earth's rotation about its axis and of the revolution of the two bodies about their center of inertia. Because as long as these periods differ, the tidal action of the Earth's surface must keep subtracting energy from their motions. To view the subject more in detail, and, at the same time, to avoid unnecessary complications, let us suppose the moon to be a uniform spherical body. The mutual action and reaction of gravitation between her mass and the Earth's will be equivalent to a single force in some line through her center, and must be such as to impede the Earth's rotation as long as this is performed in a shorter period than the moon's motion around the Earth. It must, therefore, lie in some such direction as the line MQ in the diagram, which represents, necessarily with enormous exaggeration, its deviation, OQ, from the Earth's center. Now the actual force on the moon in the line MQ may be regarded as consisting of the force in the line Missouri towards the Earth's center, sensibly equal in amount to the whole force, and comparatively very small force in the line non-tangent perpendicular to MO. This latter is very nearly tangential to the moon's path, and is in the direction with her motion. Such a force, if suddenly commencing to act, would, in the first place, increase the moon's velocity, but after a certain time she would have moved so much farther from the Earth, in virtue of this acceleration, as to have lost, by moving against the Earth's attraction, as much velocity as she had gained by the tangential accelerating force. The effect of a continued tangential force, acting with a motion, but so small in amount as to make only a small deviation at any moment from the circular form of the orbit, is to gradually increase the distance from the central body, and to cause as much again as its own amount of work to be done against the attraction of the central mass by the kinetic energy of motion lost. The circumstances will be readily understood by considering this motion around the central body in a very gradual spiral path tending upwards, provided the law of force is the inverse square of the distance, the tangential component of gravity against the motion will be twice as great as the disturbing tangential force in the direction of the motion, and therefore one half of the amount of work done against the former is done by the latter, and the other half by kinetic energy taken from the motion. The integral effect on the moon's motion of the particular disturbing cause now under consideration is most easily found by using the principle of moments of momenta. Thus we see that as much moment of momentum is gained in any time by the motions of the centers of inertia of the moon and Earth relative to their common center of inertia as is lost by the Earth's rotation about its axis. The sum of the moments of momentum of the centers of inertia of the moon and Earth as moving at present is about 4.45 times the present moment of momentum of the Earth's rotation. The average plane of the former is the ecliptic, and therefore the axes of the two moments are inclined to one another at the average angle of 23 degrees 27. 5, which, as we are neglecting the sun's influence on the plane of the moon's motion, may be taken as the actual inclination of the two axes at present. The resultant, or whole moment of momentum, is therefore 5.38 times that of the Earth's present rotation, and its axis is inclined 19 degrees 13 to the axis of the Earth. Hence the ultimate tendency of the tides is to reduce the Earth and Moon to a simple uniform rotation with its resultant moment around this resultant axis, as if they were two parts of one rigid body, in which condition the moon's distance would be increased in the ratio 1:1. 46, being the ratio of the square of the present moment of momentum of the centers of inertia to the square of the whole moment of momentum, and the period of revolution in the ratio 1:1.77, being that the cubes of the same quantities. The distance would therefore be increased to 837,100 miles, and the period lengthened to 38.36 days. Were there no other body in the universe but the Earth and the Moon, these two bodies might go on moving thus forever, in circular orbits around their common center of inertia, and the Earth rotating about its axis in the same period, so as always to turn the same face to the Moon, and, therefore, to have all the liquids at its surface rest relatively to the solid. But the existence of the Sun would prevent any such state of things from being permanent. There would be solar tides twice high water and twice low water in the period of the Earth's revolution relatively to the Sun. This could not go on without loss of energy by fluid friction. It is not easy to trace the whole course of the disturbance in the Earth's and Moon's motions which this cause would produce, but its ultimate effect must be to bring the Earth, Moon, and Sun to rotate around their common center of inertia, like parts of one rigid body. Kant, in 1754, was the first to put forward the view that the rotation of the Earth is retarded by tidal friction, and that this effect will only reach its conclusion when its surface will be at relative rest in relation to the Moon. That is, when it will rotate on its axis in the same period that the Moon takes to revolve around the Earth, and consequently will always turn the same side to the latter. He held the view that this retardation had its origin in tidal friction alone, arising, therefore, from the presence of fluid masses on the Earth. If the Earth were a quite solid mass without any fluid, neither the attraction of the Sun nor of the Moon would do anything to alter its free axial rotation. For it draws with equal force both the eastern and western parts of the terrestrial sphere, and so does not cause any inclination either to one or to the other side, consequently allows the Earth full freedom to continue its rotation unhindered, as if there were no external influence on it. Kant could rest content with this result. All scientific prerequisites were lacking at that time for penetrating deeper into the effect of the Moon on the rotation of the Earth. Indeed, it required almost 100 years before Kant's theory obtained general recognition, and still longer before it was. This more general conception of the matter is just that which has been developed by Thomson and Tate. The attraction of the Moon and Sun affects not only the fluids of the terrestrial body or its surface, but the whole mass of the Earth in general in a manner that hinders the rotation of the Earth. As long as the period of the Earth's rotation does not coincide with the period of the Moon's revolution around the Earth, so long the attraction of the Moon, to deal with this alone, first of all has the effect of bringing the two periods closer and closer together. If the rotational period of the central body were longer than the period of revolution of the satellite, the former would be gradually lengthened. If it were shorter, as is the case for the Earth, it would be slowed down. But neither in the one case will kinetic energy be created out of nothing, nor in the other would be annihilated. In the first case, the satellite would approach closer to the central body and shorten its period of revolution. In the second, it would increase its distance from it and acquire a longer period of revolution. In the first case, the satellite by approaching the central body loses exactly as much potential energy as the central body gains in kinetic energy from the accelerated rotation. In the second case, the satellite, by increasing its distance, gains exactly the same amount of potential energy as the central body loses in kinetic energy of rotation. The total amount of dynamic energy, potential and kinetic, present in the Earth-Moon system remains the same. The system is fully conservative. It is seen that this theory is entirely independent of the physical-chemical constitution of the bodies concerned. It is derived from the general laws of motion of three heavenly bodies, the connection between them being produced by traction in proportion to their masses and inverse proportion to the square of the distances between them. The theory has obviously arisen as a generalization of Kant's theory of tidal friction, and is even presented here by Thomson, and takes as its substantiation on mathematical lines. But in reality, and remarkably enough, the authors have simply no inkling of this. In reality, it excludes the special case of tidal friction. Friction is hindrance to the motion of mass, and for centuries it was regarded as the destruction of such motion, and therefore of kinetic energy. We now know that friction and impact are the two forms in which kinetic energy is converted into molecular energy, into heat. In all friction, therefore, kinetic energy as such is lost in order to reappear, not as potential energy in the sense of dynamics, but as molecular motion in the definite form of heat. The kinetic energy lost by friction is, therefore, in the first place really lost to the dynamic aspects of the system concerned. It can only become dynamically effective again if it is converted from the form of heat into kinetic energy. How then does the matter stand in the case of tidal friction? It is obvious that here also the whole of the kinetic energy communicated to the masses of water on the Earth's surface by lunar attraction is converted into heat, whether by friction of the water particles among themselves in virtue of the viscosity of the water, or by friction at the rigid surface of the Earth and the comminution of rocks which stand up against the tidal motion. Of this heat there is rate converted into kinetic energy only the infinitesimally small part that contributes to evaporation of the surface of the water. But even this infinitesimally small amount of kinetic energy, leaving the total system Earth-Moon and the part of the Earth's surface, remains first of all subject to the conditions prevailing on the Earth's surface, and these conditions lead to all energy active reaching one and the same final destiny, final conversion into heat and radiation into space. Consequently, to the extent that tidal friction disputably acts in an impeding manner on the rotation of the Earth, the kinetic energy used for this purpose is absolutely lost to the dynamic system Earth-Moon. It can therefore not reappear within the system as dynamic potential energy. In other words, of the kinetic energy expended in impeding the Earth's rotation by means of the attraction of the Moon, only that part that acts on the solid mass of the Earth's body can entirely reappear as dynamic potential energy, and hence be compensated for by corresponding increase of the distance of the Moon. On the other hand, the part that acts on the fluid masses of the Earth can do so only insofar as it does not set these masses themselves into a motion opposite in direction to that of the Earth's rotation. For such a motion is wholly converted into heat and is finally lost to the system by radiation. What holds good for tidal friction at the surface of the Earth is equally valid for the so often hypothetically assumed tidal friction of the supposed fluid nucleus of the Earth's interior. The most peculiar part of the matter is that Thomson and Tate do not notice it in order to establish the theory of tidal friction. They are putting forward a theory that proceeds from the tacit assumption that the Earth is an entirely rigid body, and so exclude any possibility of tidal flow, and hence also of tidal friction. Notes. 1. This theory has since been greatly developed, and the actual rate at which tidal friction is lengthening the day has been approximately found. 2. A slip of the pen. The word should obviously be shortened. 3. There can be no doubt that Engels was right when he pointed out Thomson and Tate's error in saying that the changes in the length of the day and month could not go on without loss of energy by fluid friction. We now know that there are tides in the Earth as well as in the ocean, but Engels was wrong in supposing that the Moon could move away from the Earth without loss of energy. For in a system such as the Earth and Moon, the angular momentum remains constant unless it is diminished or increased by the tidal action of some external body. If both momentum and energy are conserved, no systematic slowing down can occur. This is readily seen in the simplified case where the Moon is supposed to go round in a circle in the plane of the Earth's equator. In this case, there are only two possible variables, the lengths of the day and month. But so long as the momentum and the energy of the system are unchanged, we have two equations to determine these quantities, and they are therefore fixed. 4. Although Engels formulated his criticism of Thomson and taken correctly, he was right in a fundamental point. The Earth-Moon system would evolve in such a way as to lengthen the day and month even if there were no ocean. For the Earth is a solid body, but not a rigid body in the sense in which this latter word is used in theoretical mechanics. That is to say, a body whose shape is unaltered by the forces on it. Of course, a rigid body is a mathematical abstraction, like a flat surface. There are no perfectly rigid bodies nor flat surfaces, and it has now been shown that the solid Earth bends slightly as the Moon's attraction varies. There are solid tides as well as liquid tides, though much smaller. These act in the same way as the tides in the ocean, though much more slowly. 9. The part played by labor in the transition from ape to man. Labor is the source of all wealth, the economist assert. It is its next to nature, which supplies it with the material that it converts into wealth. But it is also infinitely more than this. It is the primary basic condition for all human existence, and this to such an extent that, in a sense, we have to say that labor created man himself. Many hundreds of thousands of years ago, during an epoch, not yet definitely determined, of that period of the Earth's history, which geologists call the tertiary period, most likely towards the end of it. Especially highly developed race of anthropoid apes lived somewhere in the tropical zone, probably on a great continent that has now sunk to the bottom of the Indian Ocean. Darwin has given us an approximate description of these ancestors of ours. They were completely covered with hair, they had beards and pointed ears, and they lived in bands in the trees. Almost certainly as an immediate consequence of their mode of life, for inclining the hands fulfilled quite different functions from the feet, these apes when moving on level ground began to drop the habits of using their hands and to adopt a more and more erect posture in walking. This was a decisive step in the transition from ape to man. All anthropoid apes of the present day can stand erect and move about on their feet alone, but only in case of need and in a very clumsy way. Their natural gait is in a half erect posture and includes the use of the hands. The majority rest the knuckles of the fist on the ground and, with legs drawn up, swing the body through their long arms, much as a cripple moves with the aid of crutches. In general, we can today still observe among apes all the transition stages from walking on all fours to walking on two legs, but for none of them has the latter method become more than a makeshift. For erect gait among our hairy ancestors to have become first the rule, and in time necessity presupposes that in the meantime the hands became more and more devoted to other functions. Even among the apes there already prevails a certain separation in the employment of the hands and feet. As already mentioned, inclining the hands are used differently from the feet. The former serve primarily for collecting and holding food, as already occurs in the use of the forepaws among lower mammals. Many monkeys use their hands to build nests for themselves in the trees or even, like the chimpanzee, to construct roofs between the branches for protection against the weather. With their hands they seize hold of clubs to defend themselves against enemies, or bombard the latter with fruits and stones. In captivity, they carry out with their hands a number of simple operations copied from human beings, but it is just here that one sees how great is the gulf between the undeveloped hand of even the most anthropoid apes and a human hand that has been highly perfected by the labor of hundreds of thousands of years. The number and general arrangement of the bones and muscles are the same in both, but the hand of the whole savage can perform hundreds of operations that no monkey's hand can imitate. No simian hand has ever fashioned even the crudest stone knife. At first, therefore, the operations, for which our ancestors gradually learned to adapt their hands during the many thousands of years of transition from ape to man, could only have been very simple. The lowest savages, even those in whom regression to a more animal-like condition, with a simultaneous physical degeneration, can be assumed to have occurred, are nevertheless far superior to these transitional beings. Before the first flint could be fashioned into a knife by human hands, a period of time must probably have elapsed in comparison with which the historical period known to us appears insignificant. But the decisive step was taken. The hand became free and could henceforth attain greater dexterity and skill, and the greater flexibility thus acquired was inherited and increased from generation to generation. Thus, the hand is not only the organ of labor, it is also the product of labor. Only by labor, by adaptation to ever new operations, by inheritance of the resulting special development of muscles, ligaments, and, over longer periods of time, bones as well, and by ever renewed employment of these inherited improvements of new, more and more complicated operations, has the human hand attained a high degree of perfection that has enabled it to conjure into being the pictures of Raphael, the statues of Thor Wilson, the music of Paganini. But the hand did not exist by itself. It was only one member of an entire, highly complex organism. And what benefited the hand benefited also the whole body it served, and this in two ways. In the first place, the body benefited in consequence of the law of correlation of growth, as Darwin called it. According to this law, particular forms of the individual parts of an organic being are always bound up with certain forms of other parts that apparently have no connection with the first. Thus, all animals that have red blood cells without a cell nucleus, and in which the neck is connected to the first vertebra by means of a double articulation, also without exception possess like glands for suckling their young. Similarly, club hooves in mammals are regularly associated with the possession of multiple stomach for rumination. Changes in certain forms involve changes in the form of other parts of the body, although we cannot explain this connection. Perfectly white cats with blue eyes are always, or almost always, deaf. The gradual perfecting of the human hand and the development that keeps pace with it in the adaptation of the feet for erect gait has undoubtedly also, by virtue of such correlation, reacted on other parts of the organism. However, this action has as yet been much too little investigated for us to be able to do more here than to state the fact in general terms. Much more important is the direct, demonstrable reaction of the development of the hand on the rest of the organism. As already said, our simian ancestors were gregarious. It is obviously impossible to seek the derivation of man, the most social of all animals, from non-gregarious immediate ancestors. The mastery over nature, which begins with the development of the hand, with labor, widened man's horizon at every new advance. He was continually discovering new, hitherto unknown, properties of natural objects. On the other hand, the development of labor necessarily helped to bring the members of society closer together by multiplying cases of mutual support, joint activity, and by making clear the advantage of this joint activity to each individual. In short, men in the making arrived at the point where they had something to say to one another. The need led to the creation of its organ. The undeveloped larynx of the ape was slowly but surely transformed by means of gradually increased modulation, and the organs of the mouth gradually learned to pronounce one articulate letter after another. Comparison with animals proves that this explanation of the origin of language from and in the process of labor is the only correct one. The little that even the most highly developed animals need to communicate to one another can be communicated even without the aid of articulate speech. In a state of nature, no animal feels its ability to speak or to understand human speech. It is quite different when it has been tamed by man. The dog and the horse, by association with men, have developed such a good ear for articulate speech that they easily learn to understand any language within the range of their circle of ideas. Moreover, they have acquired a capacity for feelings, such as affection for men, gratitude, etc., which were previously foreign to them. Anyone who has had much to do with such animals will hardly be able to escape the conviction that there are plenty of cases where they now feel their inability to speak is a defect, although, unfortunately, it can no longer be remedied owing to their vocal organs being specialized in a definite direction. However, where the organ exists, within certain limits even this inability disappears. The vocal organs of birds are of course radically different from those of man, yet birds are the only animals that can learn to speak, and it is the bird with the most hideous voice, the parrot, that speaks best of all. It need not be objected that the parrot does not understand what it says. It is true that for the sheer pleasure of talking and associating with human beings, the parrot will chatter for hours at a time, continuing to repeat its whole vocabulary. But within the limits of its circle of ideas, it can also learn to understand what it is saying. Teach a parrot swear words in such a way that it gets an idea of their significance. On teasing it, one will soon discover that it knows how to use its swear words just as correctly as a Berlin costermonger. Similarly with begging for tidbits. First comes labor, after it, and then side by side with it, articulate speech. These were the two most essential stimuli of the influence of which the brain of the ape gradually changed into that of man, which while its similarity to the former is far larger and more perfect. Hand in hand with the development of the brain went the development of its most immediate instruments, the sense organs. Just as the gradual development of speech is inevitably accompanied by a corresponding refinement of the organ of hearing, so the development of the brain as a whole is accompanied by a refinement of all the senses. The eagle sees much farther than men, but the human eye sees considerably more in things than does the eye of the eagle. The dog has a far keener sense of smell than men, but it does not distinguish a hundredth part of the odors that for man are definite features of different things. And the sense of touch, which the ape hardly possesses in its crudest initial form, has been developed side by side with the development of the human hand itself through the medium of labor. The reaction of labor and speech of the development of the brain and its attendant senses, of the increasing clarity of consciousness, power of abstraction and of judgment, gave an ever renewed impulse to the further development of both labor and speech. This further development did not reach its conclusion when man finally became distinct from the monkey, but, on the whole, continued to make powerful progress, varying in degree and direction among different peoples and at different times, and here and there even interrupted by local or temporary regression. This further development has been strongly urged forward, on the one hand, and has been guided along more definite directions on the other hand, owing to an element which came into play with the appearance of fully fledged man, vice, society. Hundreds of thousands of years, of no greater significance in the history of the earth than 1 second in the life of man, certainly elapsed before human society arose out of a band of tree-climbing monkeys, yet it did finally appear. And what do we find once more as the characteristic difference between the band of monkeys and human society? Labor. The ape horde was satisfied to browse over the feeding area determined for it by geographical conditions or the degree of resistance of neighboring hordes. It undertook migrations and struggles to win new feeding grounds. But it was incapable of extracting from the area which supplied it with food more than the region offered in its natural state, except, perhaps, that the horde unconsciously fertilized the soil with its own excrements. As soon as all possible feeding grounds were occupied, further increase of the monkey population could not occur. The number of animals could at best remain stationary. But all animals waste a great deal of food, and, in addition, destroy in embryo the next generation of the food supply. Unlike the hunter, the wolf does not spare the doe which would provide it with young deer the next year. The goats in Greece, which raise down the young bushes before they can grow up, have eaten bare all the mountains of the country. This predatory economy of animals plays an important part in the gradual transformation of species by forcing them to adapt themselves to other than the usual food, thanks to which their blood acquires a different chemical composition and the whole physical constitution gradually alters, while species that were once established die out. There is no doubt that this predatory economy has powerfully contributed to the gradual evolution of our ancestors and men. In a race of apes that far surpass all others in intelligence and adaptability, this predatory economy could not help leading to a continual increase in the number of plants used for food and to the devouring of more and more edible parts of these plants. In short, it led to the food becoming more and more varied, hence also the substances entering the body, the chemical premises for the transition to man. But all that was not yet labor in the proper sense of the word. The labor process begins with the making of tools. And what are the most ancient tools that we find? The most ancient, judging by the heirlooms of prehistoric man that have been discovered, and by the mode of life of the earliest historical peoples, and of the most primitive of contemporary savages? They are hunting and fishing implements, the former at the same time serving as weapons. But hunting and fishing presuppose the transition from an exclusively vegetable diet to the concomitant use of meat, and this is an important step in the transition to man. A meat diet contains in an almost ready state the most essential ingredients required by the organism for its metabolism. It shortened the time required, not only for digestion, but also for the other vegetative bodily processes corresponding to those of plant life, and thus in further time, material, and energy for the active manifestation of animal life in the proper sense of the word. And the further that man in the making became removed from the plant kingdom, the higher he rose also over animals. Just as becoming accustomed to a plant diet side by side with meat has converted wild cats and dogs into the servants of man, so also adaptation to a flesh diet side by side with a vegetable diet has considerably contributed to giving bodily strength and independence to man in the making. The most essential effect, however, of a flesh diet was on the brain, which now received a far richer flow of the materials necessary for its nourishment and development, and which therefore could become more rapidly and perfectly developed from generation to generation. With all respect to the vegetarians, it has to be recognized that man did not come into existence without a flesh diet, and if the latter, among all peoples known to us, has led to cannibalism at some time or another, that is of no consequence to us today. A meat diet led to new advances of decisive importance for the mastery of fire and the taming of animals. The first still further shortened the digestive process, as it provided the mouth with food already as it was semi-digested. The second made meat more copious by opening up a new, more regular source of supply in addition to hunting, and moreover provided, in milk and its products, a new article of food at least as valuable as meat in its composition. Thus, both these advances became directly new means of emancipation from man. It will lead us too far to dwell here and detail on their indirect effects notwithstanding the great importance they have for the development of man and society. Just as man learned to consume everything edible, he learned also to live in any climate. He spread over the whole of the habitable world, being the only animal that by its very nature had the power to do so. The other animals that have become accustomed to all climates, domestic animals and vermin did not become so independently, but only in the wake of man. And the transition from the uniformly hot climate of the original home of man to colder regions, where the air is divided into summer and winter, created new requirements, shelter and clothing as protection against cold and damp, new spheres for labor and new forms of activity, which further and further separated man from the animal. By the cooperation of hands, organs of speech, and brain, not only in each individual, but also in society, human beings became capable of executing more and more complicated operations, and of setting themselves, and achieving higher and higher aims. With each generation, labor itself became different, more perfect, more diversified. Agriculture was added to hunting and cattle breeding, then spinning, weaving, metalworking, pottery, and navigation. Along with trade and industry, there appeared finally art and science. From tribes that developed nations and states, law and politics arose, and with them the fantastic reflection of human things in the human mind, religion. In the face of all these creations, which appeared in the first place to be products of the mind, and which seemed to dominate human society, the more modest productions of the working hand retreated into the background. The more so since the mind that plans the labor process already at a very early stage of development of society was able to have the labor that had been planned carried out by other hands in its own. All merit for the swift advance of civilization was ascribed to the mind, to the development and activity of the brain. Men became accustomed to explain their actions from their thoughts, instead of from their needs, and so there arose in the course of time the idealistic outlook on the world which, especially since the decline of the ancient world, has dominated men's minds. It still rules them to such a degree that even the most materialistic natural scientists of the Darwinian school are still unable to form any clear idea of the origin of man, because under this ideological influence they do not recognize the part that has been played therein by labor. Animals, as already indicated, change external nature by their activities just as man does, if not to the same extent, and these changes made by men in their environment, as we have seen, in turn react upon and change their originators. For in nature nothing takes place in isolation. Everything affects every other thing and vice versa, and it is usually because this many-sided motion and interaction is forgotten that our natural scientists are prevented from clearly seeing the simplest things. We have seen how goats have prevented the regeneration of forests in Greece. On the island of St. Helena, goats and pigs brought by the first arrivals have succeeded in exterminating almost completely the old vegetation of the island, and so have prepared the soil for the spreading of plants brought by later settlers and colonists. But if animals exert a lasting effect on their environment, it happens unintentionally, and, as far as the animals themselves are concerned, it is an accident. The further men become removed from animals, however, the more their effect on nature assumes the character of a premeditated, planned action directed towards definite ends known in advance. The animal destroys the vegetation of a locality without realizing what it is doing. Man destroys it in order to sow field crops on the soil thus released, or to plant trees or vines which he knows will yield many times the amount sown. He transfers useful plants and domestic animals from one country to another, and thus changes the flora and fauna of whole continents. More than this, under artificial cultivation, both plants and animals are so changed by the hand of man that they become unrecognizable. The wild plants from which our grain varieties originated are still being sought in vain. The question of the wild animal from which our dogs are descended, the dogs themselves being so different from one another, or our equally numerous breeds of horses, is still under dispute. In any case, of course, we have no intention of disputing the ability of animals to act in a planned and premeditated fashion. On the contrary, a planned mode of action exists in embryo, wherever protoplasm, living protein, exists and reacts, that is carries out definite, even if extremely simple, movements as a result of definite external stimuli. Such reaction takes place even where there is as yet no cell at all, far less a nerve cell. The manner in which insectivorous plants capture their prey appears likewise in a certain respect as a planned action, although performed quite unconsciously. In animals, the capacity for conscious, planned action develops side by side with the development of the nervous system, and among mammals it attains quite a high level. While fox hunting in England, one can daily observe how unwillingly the fox knows how to make use of its excellent knowledge of the locality in order to escape from its pursuers, and how well it knows in turn to account all favorable features of the ground that cause the scent to be interrupted. Among our domestic animals, more highly developed thanks to association with men, every day one can note upon on exactly the same level as those of children. For, just as the developmental history of the human embryo in the mother's womb is only an abbreviated repetition of a history, extending over millions of years, of the bodily evolution of our animal ancestors, beginning from the worm, so the mental development of the human child is only a still more abbreviated repetition of the intellectual development of these same ancestors, at least of the later ones. But all the planned action of all animals has never resulted in pressing the stamp of their will upon nature. For that, man was required. In short, the animal merely uses external nature, and brings about changes in it simply by its presence. Man by its changes makes it serve its ends, masters it. This is the final, essential distinction between man and other animals, and once again it is labor that brings about this distinction. Let us not, however, flatter ourselves overmuch on account of our human conquest over nature, for each such conquest takes its revenge on us. Each of them, it is true, has in the first place the consequences on which we counted, but in the second and third places it has quite different, unforeseen effects which only too often cancel out the first. The people who, in Mesopotamia, Greece, Asia Minor, and elsewhere, destroyed the forests to obtain cultivable land, never dreamed that they were laying the basis for the present devastated condition of these countries, by removing along with the forests the collecting centers and reservoirs of moisture. When, on the southern slopes of the mountains, the Italians of the Alps used up the pine forests so carefully cherished on the northern slopes, they had no inkling that by doing so they were cutting the roots of the dairy industry in their region. They had still less inkling that they were thereby depriving their mountain springs of water for the greater part of the year, with the effect that these would be able to pour still more furious flood torrents on the plains during the rainy seasons. Those who spread the potato in Europe were not aware that they were at the same time spreading the disease of scrofula. Thus at every step we are reminded that we by no means rule over nature like a conqueror over a foreign people, like someone standing outside nature, but that we, with flesh, blood, and brain, belong to nature and exist in its midst, and that all our mastery of it consists in the fact that we have the advantage over all other beings of being able to know and correctly apply its laws. And, in fact, with every day that passes we are learning to understand these laws more correctly and getting to know both the more immediate and the more remote consequences of our interference with the traditional course of nature. In particular, after the mighty advances of natural science in the present century, we are more and more getting to know, and hence control, even the more remote natural consequences at least of our more ordinary productive activities. But the more this happens, the more will men not only feel, but also know, their unity with nature, and thus the more impossible will become the senseless and anti-natural idea of a contradiction between mind and matter, man and nature, soul and body, such as arose in Europe after the decline of classic antiquity, and which obtained its highest elaboration in Christianity. But it has already required a labor of thousands of years for us to learn to some extent to calculate the more remote natural consequences of our actions aiming at production. It has been still more difficult in regard to the more remote social consequences of these actions. We mentioned the potato and the resulting spread of scrofula. But what is scrofula in comparison with the effect on the living conditions of the masses of the people in whole countries resulting from the workers being reduced to a potato diet, or in comparison with the famine which overtook Ireland in 1847 in consequence of the potato disease, and which put under the earth a million Irishmen nourished solely or almost exclusively on potatoes, and forced the emigration overseas of 2 million more? When the Arabs learned to distill alcohol, it never entered their heads that by so doing they were creating one of the chief weapons for the annihilation of the original inhabitants of the still undiscovered American continent. And when afterwards Columbus discovered America, he did not know that by doing so he was giving new life to slavery, which in Europe had long ago been done away with, and laying the basis for the Negro slave traffic. The men who in the 17th and 18th centuries labored to create the steam engine had no idea that they were preparing the instrument which more than any other was to revolutionize social conditions throughout the world. Especially in Europe, by concentrating wealth in the hands of the minority, the huge majority being rendered properties. This instrument was destined at first to give social and political domination to the bourgeoisie, and then, however, to give rise to a class struggle between bourgeoisie and proletariat, which can end only in the overthrow of the bourgeoisie and the abolition of all class contradictions. But even in this sphere, by long and often cruel experience, and by collecting and analyzing the historical material, we are gradually learning to get a clear view of the indirect, more remote, social effects of our productive activity. And so the possibility is afforded us of mastering and controlling these effects as well. To carry out this control requires something more than mere knowledge. It requires a complete revolution in our hitherto existing mode of production, and with our whole contemporary social order. All hitherto existing modes of production have aimed merely at achieving the most immediately and directly useful effect of labor. The further consequences, which only appear later on and become effective through gradual repetition and accumulation, were totally neglected. Primitive communal ownership of land corresponded, on the one hand, to a level of development of human beings in which their horizon was restricted in general to what lay immediately at hand, and presupposed, on the other hand, a certain surplus of available land, allowing a certain latitude for correcting any possible bad results of this primitive forced type of economy. When the surplus land was exhausted, communal ownership also declined. All higher forms of production, however, proceeded in their development to the division of the population into different classes, and thereby the contradiction of ruling oppressed classes. But thanks to this, the interest of the ruling class became the driving factor of production, insofar as the latter was not restricted to the barest means of subsistence of the oppressed people. This has been carried through most completely in the capitalist mode of production prevailing today in Western Europe. The individual capitalists, who dominate production and exchange, are able to concern themselves only with the most immediate useful effect of their actions. Indeed, even this useful effect, inasmuch as it is a question of the usefulness of the commodity that is produced or exchanged, retreats right into the background, and the sole incentive becomes the profit to be gained on selling. The social science of the bourgeoisie, classical political economy, is predominantly occupied only with the directly intended social effects of human actions connected with production and exchange. This fully corresponds to the social organization of which it is the theoretical expression. When individual capitalists are engaged in production and exchange for the sake of the immediate profit, only the nearest, most immediate results can be taken into account in the first place. When an individual manufacturer or merchant sells a manufactured or purchased commodity with only the usual small profit, he is satisfied, and he is not concerned as to what becomes of the commodity afterwards or who are its purchasers. The same thing applies to the natural effects of the same actions. What did the Spanish planters in Cuba, who burned down forests the slopes of the mountains and obtained from the ashes sufficient fertilizer for one generation of very highly profitable coffee trees, care that the tropical rainfall afterwards wash away the now unprotected upper spreading of the soil, leaving behind only bare rock? In relation to nature, as to society, the present mode of production is predominantly concerned only about the first, tangible success, and then surprises expressed that the more remote effects of actions directed to this end turn out to be of quite a different, mainly even quite an opposite character. That the harmony of demand and supply becomes transformed into their polar opposites, as shown by the course of each 10 years industrial cycle, and of which even Germany has experienced a little preliminary in the crash. That private ownership based on individual labor necessarily develops into the propertylessness of the workers, while all wealth becomes more and more concentrated in the hands of non-workers. That notes. 1. This is rather unlikely. A broad ridge across the Indian Ocean has been found in the region indicated, but if it represents a sunken continent, this probably sank before our ancestors had evolved so far. 2. It has been suggested that this process was speeded up by the dying out of forests in Central Asia, so that our ancestors were forced to run after their prey. 3. Chimpanzees can carry out some operations on their own initiative. 4. The connection can now be explained in a few cases. Thus why onions are more susceptible to molds than the colored forms, because they lack an antiseptic substance as well as coloring matter. The antiseptic is a necessary stage in building up the pigment. 5. This is doubtful. A dog cannot distinguish between smells which are distinct to man, but the converse is also true. 6. A leading authority in this respect, Sir W. Thomson, has calculated that little more than 100 million years could have elapsed since the time when the Earth had cooled sufficiently for plants and animals to be able to live on it. This time has been greatly extended by the discovery of radioactivity. The correct figure is probably about 1500 million years. 7. It is very doubtful whether evolution occurs as a result of this process. 8. Engels' belief in the meat diet is by no means shared universally by students of biochemistry, although it must be remembered that most so-called vegetarians partake of milk or its products. 9. This is probably an exaggeration. A study of Stone Age techniques suggests that periods of stagnation lasted for scores or hundreds of generations. Of course, the time occupied by human evolution is much longer than Engels thought possible. 10. They are now, in many cases, known with fair certainty. 11. At the time when Engels wrote it was widely believed in medical circles that scrofula was due to eating potatoes. There is a causal connection in the sense that it is a disease of inadequately fed people, including those who live on a diet mainly of potatoes, but there is no real evidence that potatoes, as such, play any part in causing it. 12. The manuscript here breaks off abruptly. Natural science in the spirit world. The dialectics that has found its way into popular consciousness finds expression in the old saying that extremes meet. In accordance with this, we should hardly ever looking for the most extreme degree of fantasy, credulity, and superstition, not in the trend of natural science which, like the German philosophy of nature, tries to force the objective world into the framework of its subjective thought, but rather in the opposite trend, which, relying on mere experience, treats thought with sovereign disdain and really has gone to the furthest extreme in enviness of thought. This school prevails in England. Its father, the much lauded Francis Bacon, already advanced the demand that this new empirical inductive method should be pursued to attain by its means, above all, longer life, rejuvenation, to a certain extent, alteration of stature and features, transformation of one body into another, the production of new species, power over the air and the production of storms. He complains that such investigations have been abandoned, and in his natural history he actually gives recipes for making gold and performing various miracles. Similarly, Isaac Newton in his old age greatly busied himself with expounding the revelation of St. John, so as not to be wondered if in recent years English empiricism in the person of some of its representatives, and not the worst of them, should seem to have fallen a hopeless victim to the spirit wrapping and spirit seeing imported from America. The first natural scientist belonging here is the very eminent zoologist and botanist, Alfred Russel Wallace, the man who simultaneously with Darwin put forward the theory of the evolution of species by natural selection. In his little work on miracles and modern spiritualism, London, Burns, 1875, he relates to his first experiences in this branch of natural knowledge day from 1844, when he attended the lectures of Mr. Spencer Hall on mesmerism, and as a result carried out similar experiments on his pupils. I was extremely interested in the subject and pursued it with ardor. He not only produced magnetic sleep together with the phenomena of articular rigidity and local loss of sensation, he also confirmed the correctness of Bell's map of the skull, because on touching any one of Bell's organs the corresponding activity was aroused in the magnetized patient and exhibited by appropriate and lively gestures. Further, he established that his patient, merely by being touched, partook of all the sensations of the operator. He made him drunk with a glass of water as soon as he told him that it was brandy. He could make one of the young men so stupid, even in the waking condition, that he no longer knew his own name, a feat, however, that other schoolmasters are capable of accomplishing without any mesmerism, and so on. Now it happens that I also saw this Mr. Spencer Hall in the winter of 1843 in Manchester. He was a very mediocre charlatan who traveled the country under the patronage of some parsons and undertook magnetical phrenological performances with a young girl in order to prove thereby the existence of God, the immortality of the soul, and the incorrectness of the materialism that was being preached at that time by the Owenites in all big towns. The lady was sent into a magnetic sleep, and then, as soon as the operator touched any part of the skull corresponding to one of Bell's organs, she gave a bountiful display of theatrical, demonstrative gestures and poses representing the activity of the organ concerned. For instance, for the organ of filial genitalness she fondled and kissed an imaginary baby, etc. Moreover, the good Mr. Hall had enriched Bell's geography of the skull with a new island of Brataria. Right at the top of the skull he had discovered an organ of veneration, on touching which his hypnotic miss sank onto her knees, folded her hands in prayer, and depicted to the astonished Philistine audience an angel wrapped in veneration. That was the climax and conclusion of the exhibition. The existence of God had been proved. The effect on me and one of my acquaintances was exactly the same as on Mr. Wallace. The phenomena interested us and we tried to find out how far we could reproduce them. A wide-awake young boy of 12 years old offered himself as subject. Gently gazing into his eyes, or stroking, sent him without difficulty into the hypnotic condition. But since we were rather less credulous than Mr. Wallace and said to work with rather less fervor, we arrived at quite different results. Apart from muscular rigidity and loss of sensation, which were easy to produce, we found also a state of complete passivity of the will bound up with a peculiar hypersensitivity of sensation. The patient, when aroused from his lethargy by any external stimulus, exhibited very much greater liveliness than in the waking condition. There was no trace of any mysterious relation to the operator. Anyone else could just as easily set the sleeper into activity. To set Bell's cranial organs into action was the least that we achieved. We went much further. We could not only exchange them to one another, or make their seat anywhere in the whole body, but we also fabricated any amount of other organs. Organs of singing, whistling, piping, dancing, boxing, sewing, cobbling, tobacco smoking, etc. And we could make their seat wherever we wanted. Wallace made his patients drunk on water, but we discovered in the great tone organ of drunkenness, which only had to be touched in order to cause the finest drunken comedy to be enacted. But it must be well understood, no organ showed a trace of action until the patient was given to understand what was expected of him. The boy soon perfected himself by practice to such an extent that the merest indication sufficed. The organs produced in this way then retained their validity for later occasions of putting to sleep, as long as they were not altered in the same way. The patient had even a double memory, one for the waking state and a second quite separate one for the hypnotic condition. As regards the passivity of the will and its absolute subjection to the will of a third person, this loses all its miraculous appearance when we bear in mind that the whole condition begins with the subjection of the will of the patient to that of the operator and cannot be restored without it. The most powerful magician of a magnetizer in the world will come to the end of his research as soon as his patient laughs him in the face. While we with our frivolous skepticism thus founded the basis of magnetical phrenological charlatanry lay in a series of phenomena which for the most part differ only in degree from those of the waking state and require no mystical interpretation, Mr. Wallace's ardor led him into a series of self-deceptions, in virtue of which he confirmed Bell's map of the skull and all its details, and noted a mysterious relation between operator and patient. Everywhere in Mr. Wallace's account, the sincerity of which reaches the degree of naivete, it becomes apparent that he was much less concerned in investigating the factual background of charlatanry than in reproducing all the phenomena at all costs. Only this frame of mind is needed for the man who was originally a scientist to be quickly converted into an adept by means of simple and facile self-deception. Mr. Wallace ended up with faith in magnetical phrenological miracles, and so already stood with one foot in the world of spirits. He drew the other foot after him in 1865. On returning from his 12 years of travel in the tropical zone, experiments and table turning introduced him to the society of various mediums. How rapid his progress was, and how complete his mastery of the subject, is testified by the above-mentioned booklet. He expects us to take for good coin not only all the alleged miracles of home, the brothers Davenport, and other mediums, who all more or less exhibit themselves for money and who have for the most part been frequently exposed as impostors, but also a whole series of allegedly authentic spirit histories from early times. The Pythonesses of the Greek oracle, the witches of the Middle Ages, were all mediums, and Jan Blancas in his divination already described quite accurately the most astonishing phenomena of modern spiritualism. Just one example to show how likely Mr. Wallace deals with the scientific corroboration and authentication of these miracles. It is certainly a strong assumption that we should believe that the aforesaid spirits should allow themselves to be photographed, and we have surely the right to demand that such spirit photographs should be authenticated in the most indubitable manner before we accept them as genuine. Now Mr. Wallace recounts on p.187 in March 1872, a leading medium, Mrs. Guppy, nine Nichols, had herself photographed together with her husband and small boy at Mr. Hoskins in Notting Hill, and on two different photographs a tall female figure, finely draped in white gauze robes, with somewhat eastern features, was to be seen behind her in a pose, as of giving a benediction. Here, then, one of two things are absolutely certain. Either there was a living intelligent, but invisible being present, or Mr. and Mrs. Guppy, the photographer, and some fourth person planned a wicked imposture, and have maintained it ever since. Knowing Mr. and Mrs. Guppy so well as I do, I feel an absolute conviction that they are as incapable of an imposture of this kind as any earnest inquirer after truth in the department of natural science. Consequently, either deception or spirit photography. Quite so. And, if deception, either the spirit was already on the photographic plates, or four persons must have been concerned, or three if we leave out as weak-minded or dull Mr. Guppy, who died in January 1875, at the age of 84. The photographer could obtain a model for the spirit without difficulty does not need to be argued. And if anyone still does not believe in the genuineness of spirit photography, there's no helping him. The second eminent adept among English natural scientists is Mr. William Crookes, the discoverer of the chemical element thallium and of the radiometer. Mr. Crookes began to investigate spiritualistic manifestations about 1871, and employed for this purpose a number of physical and mechanical appliances, spring balances, electric batteries, etc. Whether he brought to his task the main apparatus required, a skeptically critical mind, or whether he remained to the end in a fit state for a working, we shall see. At any rate, within a not very long period, Mr. Crookes was just as completely captivated as Mr. Wallace. For some years, he relates, a young lady, Miss Florence Cook, has exhibited remarkable mediumship, which latterly culminated in the production of an entire female form purporting to be of spiritual origin, and which appeared barefooted in white flowing robes, while she lay entranced in dark clothing and securely bound in a cabinet or adjoining room. This spirit, which called itself Katie, and which looked remarkably like Miss Cook, was one evening suddenly seized round the waist by Mr. Volkman, the present husband of Mrs. Guppy, and held fast in order to see whether it was not indeed Miss Cook in another edition. The spirit proved to be a quite sturdy damsel. It defended itself vigorously. The onlookers intervened. The gas was turned out, and when, after some scuffling, peace was reestablished and the room relit, the spirit had vanished and Miss Cook lay bound and unconscious in her corner. Nevertheless, Mr. Volkman is said to maintain up to the present day that he had seized hold of Miss Cook and nobody else. In order to establish this scientifically, Mr. Vary, a well-known electrician, on the occasion of a new experiment, arranged for the current from a battery to flow through the medium, Miss Cook, in such a way that she could not play the part of the spirit without interrupting the current. Nevertheless, the spirit made its appearance. It was, therefore, indeed a being different from Miss Cook. To establish this further was the task of Mr. Crooks. His first step was to win the confidence of the spiritualistic lady. This confidence, so he says himself in the spiritualist, June 5, 1874, increased gradually to such an extent that she refused to give a seance unless I made the arrangements. She said that she always wanted me to be near her in the neighborhood of the cabinet. I found that, when this confidence had been established and she was sure that I would not break any promise made to her, the phenomena increased considerably in strength, and there was freely forthcoming evidence that would have been unobtainable in any other way. She frequently consulted me in regard to the persons present at the seances and the places to be given them, for she had recently become very nervous as a result of certain ill-advised suggestions that, besides other more scientific methods of investigation, force also should be applied. The spirit lady rewarded this confidence, which was as kind as it was scientific, in the highest measure. She even made her appearance, which can no longer surprise us, in Mr. Crooks' house, played with his children and told them anecdotes from her adventures in India, treated Mr. Crooks to an account of some of the bitter experiences of her past life, allowed him to take her by the arm so that he could convince himself of her evident materiality, allowed him to take her pulse and count the number of her respirations per minute, and finally allowed herself to be photographed next to Mr. Crooks. This figure, says Mr. Wallace, after she had been seen, touched, photographed, and conversed with, vanished absolutely out of a small room from which there was no other exit than an adjoining room filled with spectators, which was not such a great feat, provided that the spectators were polite enough to show as much faith in Mr. Crooks, in whose house this happened, as Mr. Crooks did in the spirit. Unfortunately, these fully authenticated phenomena are not immediately credible even for spiritualists. We saw how the very spiritualistic Mr. Volkman permitted himself to make a very material rap. And now a clergyman, a member of the committee of the British National Association of Spiritualists, has also been present at a seance with Miss Cook, and he established the fact without difficulty that the room through the door of which the spirit came and disappeared communicated with the outer world by a second door. The behavior of Mr. Crooks, who was also present, gave the final death blow to my belief that there might be something in the manifestations. And, over and above that, it came to light in America how Katie's were materialized. A married couple named Holmes held seances in Philadelphia, in which likewise a Katie appeared and received bountiful presents from the believers. However, one skeptic refused to rest until he got on the track of the said Katie, who, anyway, had already gone on strike once because of lack of pay. He discovered in the boarding house as a young lady of unquestionable flesh and bone, and in possession of all the presents it had been given to the spirit. Meanwhile, the continent also had its scientific spirits, a scientific association at St. Petersburg. I do not know exactly whether the university, or even the academy itself, charged the counselor of state, Aksakoff, and the chemist, Butlerov, to examine the basis of the spiritualistic phenomena, but it has not seemed that very much came of this. On the other hand, if the noisy announcements of the spiritualists are to be believed, Germany has now also put forward its man in the person of Professor Zollner at Leipzig. For years, as is well known, Herr Zollner has been hard at work on the fourth dimension of space, and has discovered that many things that are impossible in a space of 3 dimensions are a simple matter of course in a space of 4 dimensions. Thus, in the latter kind of space, a closed metal sphere can be turned inside out like a glove, without making a hole in it. Similarly, a nut can be tied in an endless string, or one which is both ends fastened, and 2 separate closed rings can be interlinked without opening either of them. And many more such feats. According to the recent triumphant reports from the spirit world, it is said now that Professor Zollner has addressed himself to one or more mediums in order with their aid to determine more details of the locality of the 4th dimension. The success is said to have been surprising. After the session, the arm of the chair, on which he rested his arm, while his hand never left the table, was found to have become interlocked with his arm. A string that had both ends sealed to the table was found tied into 4 knots, and so on. In short, all the miracles of the 4th dimension are said to have been performed by the spirits with the utmost ease. It must be borne in mind, relator Pharaoh, I do not vouch for the correctness of the spirit bulletin, and if it should contain any inaccuracy, Herr Zollner ought to be thankful that I am giving him the opportunity to make a correction. If, however, it reproduces the experiences of Herr Zollner without falsification, then it obviously signifies a new era both in the science of spiritualism and of mathematics. The spirits prove the existence of the 4th dimension, just as the 4th dimension vouches for the existence of spirits, and this once established, an entirely new, immeasurable field is open to science. All previous mathematics and natural science will be only a preparatory school for the mathematics of the 4th and still higher dimensions, and for the mechanics, physics, chemistry, and physiology of the spirits dwelling in these higher dimensions. Has not Mr. Crooks scientifically determined how much weight is lost by tables and other articles of furniture under passage into the 4th dimension, as we may now well be permitted to call it, and does not Mr. Wallace declare proven that fire there is no harm to the human body? And now we have even the physiology of the spirit bodies. They breathe, they have a pulse, therefore lungs, heart, and a circulatory apparatus, and in consequence are at least as admirably equipped as our own in regard to the other bodily organs. For breathing requires carbohydrates which undergo combustion in the lungs, and these carbohydrates can only be supplied from without, hence, stomach, intestines, and their accessories, and if we once establish so much, the rest follows without difficulty. The existence of such organs, however, implies the possibility of their falling a prey to disease, hence it may still come to pass that Herr Virchow will have to compile a cellular pathology of the spirit world. And since most of these spirits are very handsome young ladies, who are not to be distinguished in any respect whatsoever from terrestrial damsels, other than by their supermundane beauty, it could not be very long before they come into contact with men who feel the passion of love. And since, as established by Mr. Crooks from the beat of the pulse, the female heart is not of sin, natural selection also has opened before it the prospect of a 4th dimension, one in which it has no longer any need to fear of being confused with wicked social democracy. Enough. Here it becomes palpably evident, which is the most certain path from natural science to mysticism. It is not the extravagant theorizing of the philosophy of nature, but the Schauist empiricism that spurns all theory and distrusts all thought. It is not a priori necessity that proves the existence of spirits, but the empirical observations of Mr. Wallace, Crooks, and company. If we trust the spectrum analysis observations of Crooks, which led to the discovery of the metal thallium, or the which zoological discoveries of Wallace in the Malay archipelago, we are asked to place the same trust in the spiritualistic experiences and discoveries of these 2 scientists. And if we express the opinion that, after all, there is a little difference between the 2, namely, that we can verify the one but not the other, then the spirit seers retort that this is not the case, and that they are ready to give us the opportunity of verifying also the spirit phenomena. Indeed, dialectics cannot be despised with impunity. However great one's contempt for all theoretical thought, nevertheless one cannot bring 2 natural facts into relation with one another, or understand the connection existing between them, without theoretical thought. The only question is whether one's thinking is correct or not, and contempt of theory is evidently the most certain way to think naturalistically, and therefore incorrectly. But, according to an old and well-known dialectic law, incorrect thinking, carried to its logical conclusion, inevitably arrives at the opposite of its point of departure. Hence, the empirical contempt of dialectics on the part of some of the most sober empiricists is punished by their being led into the most barren of all superstitions, into modern spiritualism. It is the same with mathematics. The ordinary metaphysical mathematicians boast with enormous pride of the absolute irrefutability of the results of their science. But these results include also imaginary magnitudes, which thereby acquire a certain reality. When one has once become accustomed to ascribe some kind of reality outside of our minds to -1, or to the 4th dimension, then it is not a matter of much importance if one goes a step further and also accepts the spirit world of the mediums. It is as Kepler said about Dallinger, the man has defended so much nonsense in his life, he really could have accepted infallibility into the bargain. In fact, mere empiricism is incapable of refuting the spiritualists. In the first place, the higher phenomena always show themselves only when the investigator concerned is already so far in the toils that he now only sees what he is meant to see or wants to see, as Crooks himself describes with such an inimitable naivete. In the second place, however, the spiritualist cares nothing if hundreds of alleged facts are exposed as imposture, and dozens of alleged mediums as ordinary tricksters. As long as every single alleged miracle has not been explained away, they have still room enough to carry on, as indeed Wallace says clearly enough in connection with the falsified spirit photographs. The existence of falsifications proves the genuineness of the genuine ones. And so empiricism finds itself compelled to refute the importunate spirit seers not by means of empirical experiments, but by theoretical considerations, and to say, with Huxley, the only good that I can see in the demonstration of the truth of spiritualism is to furnish an additional argument against suicide. Better lie a crossing sweeper than die be made to talk twaddle by medium. Hired again is Notes. 1. From a manuscript of Engels probably written in 1878, and first published in the illustrator Newly Well calendar for R 1898. 2. As already said, the patients perfect themselves by practice. It is therefore quite possible that, when the subjection of the will has become habitual, the relation of the participants becomes more intimate. Individual phenomena are intensified and are reflected weekly even in the waking state. 3. See Appendix 2, p. 368. 4. The spirit world is superior to grammar. A joker once caused the spirit of the grammar in Lincoln Murray to testify. To the question whether he was there, he answered, I are. The medium was from America. 5. See Appendix 2, p. 369. 6. See Appendix 2, p. 377. A Catholic scholar who did not accept the dogma of papal infallibility. 8. See Appendix 2, p. 370. Notes. The successive development of the separate branches of natural science should be studied. First of all, astronomy, which, if only on account of the seasons, was absolutely indispensable for pastoral and agricultural peoples. Astronomy can only develop with the aid of mathematics, hence this also had to be tackled. Further, at a certain stage of agriculture in certain regions, and especially with the origin of towns, big building structures and the development of handicrafts, mechanics also arose. This was soon needed also for navigation and war. Moreover, it requires the aid of mathematics, and so promotes the latter's development. Thus, from the very beginning, the origin and development of the sciences has been determined by production. Throughout antiquity, scientific investigation probably remained restricted to these three branches, and indeed in the form of exact, systematic research it occurs for the first time in the post-classical period, in physics and chemistry, which were as yet hardly separated in men's minds. In botany, zoology, human and animal anatomy, it had only been possible until then to collect facts and arrange them as systematically as possible. Physiology was sheer guesswork as soon as one went beyond the most tangible things, for example, digestion and excretion, and it could not be otherwise when even the circulation of the blood was not known. At the end of the period, chemistry makes its appearance in the primitive form of alchemy. If, after the dark night of the Middle Ages was over, the science of suddenly arose anew with undreamt of force, developing at a miraculous rate, once again we owe this miracle to production. In the first place, following the Crusades, industry developed enormously and brought to light a quantity of new mechanical, chemical, and physical facts, and this not only gave enormous material for observation, but also itself provided quite other means for experimenting than previously existed, and allowed the construction of new instruments. It can be said that really systematic, experimental science now became possible for the first time. Secondly, the whole of West and Middle Europe, including Poland, now developed in a connected fashion, even though Italy was still ahead owing to its old inherited civilization. Thirdly, geographical discoveries, made purely for the sake of gain and, therefore, in the last resort, of production, opened up an infinite and hitherto inaccessible amount of material of a meteorological, zoological, botanical, and physiological bearing. Fourthly, there was the printing press. Now, apart from mathematics, astronomy, and mechanics, which were already in existence, physics becomes definitely separate from chemistry. Boyle put chemistry on a stable basis as a science. Harvey did the same for physiology by the discovery of the blood circulation. Zoology and botany remained at first collecting sciences, until paleontology appeared on the scene, Cuvier, and shortly afterwards came the discovery of the cell and the development of organic chemistry. Therewith comparative morphology and physiology became possible, and from then on both are true sciences. Geology was founded at the end of the last century, and recently anthropology, badly so-called, enabling the transition from the morphology and physiology of man and human races to history. This to be studied further in detail and to be developed. The ancient outlook on nature. Of the first philosophers, Aristotle says that they assert that which all things consist, from which they first come and into which they are ultimately resolved, of which the essence persists although modified by its affections. This is the element and principle of all being. Hence they believe that nothing is either generated or destroyed, since this kind of primary entity always persists. Here, therefore, is already the whole original spontaneous materialism which at its beginning quite naturally regards the unity of the infinite diversity of natural phenomena as a matter of course, and seeks it in something definitely corporeal, a particular thing, as Phil does in water. Cicero says, Phil's of Miltos, declared that water is the basis of things, and God that mind that forms everything out of water. Hegel quite rightly declares that this is an addition of Cicero's, and says, however, we are not concerned here with this question whether, in addition, Phil's believed in God. It is not a matter here of supposition, belief, popular religion, and even if he spoke of God as having created all things from the water, we would not thereby know anything more of this being. It is an empty word without its idea. p. 209. The oldest Greek philosophers were at the same time investigators of nature. Phil's, a geometrician, fixed the year at 365 days, and is said to have predicted a solar eclipse. Anaximander constructed a sun clock, a kind of map of land and sea, and various astronomical instruments. Pythagoras was a mathematician. Anaximander of Miltos, according to Plutarch, makes man come from a fish, emerging from the water onto the land. p. 213. For him the arch cast also onto a pyre, without determining his air, water, or anything else. This is correctly reproduced by Hegel. p. 215, as undetermined matter. Anaximander of Miltos takes air as principal and basic element, declaring it to be infinite and that everything arises from it, and everything is again dissolved. Here air equals pneuma. Just as our soul, which is air, holds us together, so also a spirit and air hold the whole world together. Spirit and air have the same meaning. So air conceived as a general medium. Aristotle already says that these ancient philosophers put the primordial essence in the form of matter, air and water, later air applied as in fire, but not on earth on account of its multiple composition metaphysics. 8. Aristotle correctly remarks of all of them that they leave the origin of motion unexplained. Pythagoras the same as number is the basic principle. That number is the essence of all things, and the organization of the universe as a whole and its determinations is a harmonious system of numbers and their relations. Hegel justly points out the audacity of such language, which at one blow strikes down all that is regarded by the imagination as being most essential, and any who lacks the sensuous essence, and puts the essence in the thought determination, even if it is a very restricted and one-sided one. Just as number is subject to definite laws, so also the universe. Hereby its obedience to law was expressed for the first time. To Pythagoras is ascribed the reduction of musical harmonies to mathematical relations. Likewise, the Pythagoreans put fire in the center, but the earth is a star which revolves in a circle around its central body. p. 265. This fire, however, is not the sun. Nevertheless, this is the first inkling that the earth moves. Hegel on the planetary system. The harmonious element, which determines the distances, all mathematics has still not been able to give any basis for it. The empirical numbers are accurately known, but it is all the appearance of chance, not of necessity. And approximate regularity of the distances is known, and thus luck planets between Mars and Jupiter have been guessed at, where later series, Vesta, Pallas, etc. were discovered. But astronomy still did not find a consistent series in which there was any sense, any reason. Rather, it looks with contempt on the regular representation of this series. For itself, however, it is an extremely important point which must not be surrendered. For all the naive materialism of the total outlook, the kernel of the later split is already to be found among the ancient Greeks. For Phils, the soul is already something special, something different from the body. For Anaximenes it is air. For the Pythagoreans it is already immortal and migratory, the body being purely incidental to it. For the Pythagoreans, also, the soul is a chip of the ether, where the cold ether is the air, the dense ether of the sea, and moisture. Aristotle correctly reproaches the Pythagoreans also. With their numbers they do not say how motion comes into being, and how, without motion and change, there's coming into being and passing away, or states and activities of heavenly things. Pythagoras is supposed to have discovered the identity of the morning and evening star, that the moon gets its light from the sun, and finally the Pythagorean theorem. Pythagoras is said to have slaughtered the hecatome on discovering this theorem, and however remarkable it may be that his joy went so far on that account as to order a great feast, to which the rich and the whole people were invited. It was worth the trouble. It is joyousness, joy of the spirit, at the expense of the oxen. The Eleatics. Leucippus and Democritus. Leucippus, however, and his disciple Democritus hold that the elements are the full and the void, calling the one what ice and the other what is no. Of these they identify the full or solid with what ice and the void or rare with what is no. Hence they hold that what is not is no less real than what is, and they say that these are the material causes of things. And just as those who make the underlying substance of unity generate all other things by means of its modifications, so these thinkers hold that the differences are the causes of everything else. These differences, they say, are three: shape, arrangement, and position. Thus, for example, a differs from n in shape and from n in arrangement, and z from n in position. Leucippus was the first to set up atoms as general principles, and these he calls elements. Out of them arise the worlds unlimited in number, and into them they are dissolved. This is how the worlds are formed. In a given section, many atoms of all manner of shapes are carried from the unlimited into the vast empty space. These collict together and form a single vortex, in which they jostle against each other and, circling round in every possible way, separate off by like atoms joining like. And the atoms being so numerous that they can no longer revolve in equilibrium, the like ones pass into the empty space outside, as if they were being winnowed. The remainder keep together and, becoming entangled, go on their circuit together, and form a primary spherical system. The following about Epicurus. The atoms are in continual motion through all eternity. Further, he says below the atoms move with equal speed, since the void makes way for the lightest and heaviest alike. Atoms have no quality at all except shape, size, and weight. They are not at any and every size. At any rate, no atom has ever been seen the arsons. When they are traveling through the void and meet with no resistance, the atoms must move with equal speed. Neither will heavy atoms travel more quickly than small and light ones, so long as nothing meets them. Nor will small atoms travel more quickly than large ones, provided they always find a suitable passage, and provided also that they meet with no obstruction. Thus it is clear that in every kind the one is of a definite nature, and that in none of them is this, the one, at its nature. Aristarchus of Samos, 270 BC, already held the Copernican theory of the Earth and Sun. Democritus had already surmised that the Milky Way shines on us the combined light of innumerable small stars. Difference between the situation at the end of the ancient world, California 300 and at the end of the Middle Ages minus 1453. 1. Instead of a thin strip of civilization along the coast of the Mediterranean, stretching its arms sporadically into the interior and as far as the Atlantic coast of Spain, France, and England, which could thus easily be broken through and rolled back by the Germans and Slavs from the north, and by the Arabs from the southeast, there was now a closed area of civilization, the whole of West Europe with Scandinavia, Poland, and Hungary as outposts. 2. Instead of the contrast between the Greeks, or Romans, and the barbarians, there were now 6 civilized peoples with civilized languages, not counting the Scandinavian, etc. All of whom had developed to such an extent that they could participate in the mighty rise of literature in the 14th century and guarantee a far more diversified culture than that of the Greek and Latin languages, which were already in decay and dying out at the end of ancient times. 3. An infinitely higher development of industrial production and trade, created by the burghers of the Middle Ages. On the one hand, production more perfected, more varied and on a larger scale, and, on the other hand, commerce much stronger. Navigation being infinitely more enterprising since the time of the Saxons, Frisians, and Normans, and on the other hand also an amount of inventions and importation of Oriental inventions, which not only for the first time made possible the importation and diffusion of Greek literature, the maritime discoveries, and the bourgeois religious revolution, but also gave them a quite different and quicker range of action. In addition, they produced a mass of scientific facts, although as yet unsystematized, such as antiquity never had, the magnetic needle, printing, type, flax paper used by the Arabs and Spanish Jews since the 12th century, cotton paper gradually making its appearance since the 10th century, and already more widespread in the 13th and 14th centuries, papyrus quite obsolete in Egypt since the Arabs, gunpowder, spectacles, mechanical clocks, great progress both of chronology and of mechanics. In addition, material provided by travels. General education, even though still bad, much more widespread owing to the universities. With the rise of Constantinople and the fall of Rome, antiquity comes to an end. The end of the Middle Ages is indissolubly linked with the fall of Constantinople. The New Age begins with the return to the Greeks, negation of the negation. Historical material, inventions. BC, fire hose, water block, to 200 BC street paving, parchment, to 160 AD, water mills and Moselle, to 340, in Germany in the time of Charles the Great. First signs of glass windows, street lighting in Antioch, to 370. Silkworms from China, to 550 in Greece. Quill pens in the 6th century. Cotton paper from China to the Arabs in the 7th century, in the 9th in Italy. Water-powered organs in France in the 8th century. Silver mines and airs worked since the 10th century. Windmills, about 1000. Notes, Guido de Rizzo's musical scale, about 1000. Sericulture introduced in Italy, about 1100. Clocks with wheels, ditto. Magnetic needle from the Arabs to the Europeans, 1180. Street paving in Paris, 1184. Spectacles in Florence. Glass mirrors, second half of 13th century. Hair insulting. Sluices, striking clocks. Cotton paper in France. Rag paper, beginning of 14th century. Bills of exchange, middle of ditto. First paper mill in Germany, 1390. Street lighting in London, beginning of 15th century. Post in Venice, ditto. Woodcuts and printing, ditto. Copper engraving, middle ditto. Horse post in France, 1464. Silver mines in the Saxon Burge, 1471. Pedal clockwork invented, 1472. Pocket watches, air guns, flintlock, end of 15th century. Spinning wheel, 1530. Diving bell, 1538. Historical. Modern natural science, the only one which can come into consideration sciences against the brilliant intentions of the Greeks and the sporadic and connected investigations of the Arabs begins with the mighty epoch when feudalism was smashed by the burghers. In the background of the struggle between the burghers of the towns and the feudal nobility, this epoch showed the peasant in revolt, and behind the peasant the revolutionary beginnings of the modern proletariat, already red flag in hand and with communism on its lips. It was the epoch which brought into being the great monarchies in Europe, broke the spiritual dictatorship of the Pope, evoked the revival of Greek antiquity, and with the highest artistic development of the New Age, broke through the boundaries of the old world, and for the first time really discovered the world. It was the greatest revolution that the world had so far experienced. Natural science also flourished in this revolution, was revolutionary through and through, advanced hand in hand with the awakening modern philosophy of the great Italians, and provided its martyrs for the stake and the prisons. It is characteristic that Protestants and Catholics vied with one another in persecuting it. The former burned Servetus, the latter Giordano Bruno. It was a time that called for giants and produced giants, giants in learning, intellect, and character, a time that the French correctly called the Renaissance in Protestant Europe with one-sided prejudice called that of the Reformation. At that time, natural science also had its declaration of independence, though it is true it did not come right at the beginning, any more than Luther was the first Protestant. What Luther's burning of the papal bull was in the religious field, in the field of natural science was the great work of Copernicus, in which he, although timidly, after 36 years hesitation, and so to say on his deathbed, threw down a challenge to ecclesiastical superstition. From then on, natural science was in essence emancipated from religion, although the complete settlement of accounts in all details has gone on to the present day, and in many minds is still far from being complete. But from then on, the development of science went forward with giant strides, increasing, so to speak, proportionately to the square of the distance in time from its point of departure, as if it wanted to show the world that the motion of the highest product of organic matter, the human mind. The law that holds good is the reverse of that of the motion of inorganic matter. The first period of modern natural science ends in the inorganic sphere with Newton. It is the period in which the available subject matter was mastered. It performed great work in the fields of mathematics, mechanics and astronomy, statics and dynamics, especially owing to Kepler and Galileo, from whose work Newton drew the conclusions. In the organic sphere, however, there was no progress beyond the first beginnings. The investigation of the forms of life historically, succeeding one another and replacing one another, as well as the changing conditions of life corresponding to them, for low-ontology and geology did not yet exist. Nature was not at all regarded as something that developed historically. That had a history in time. Only extension in space was taken into account. The various forms were grouped not one after the other, but only one beside the other. Natural history was valid for all periods. Like the elliptical orbits of the planets. For any closer analysis of organic structure, both the immediate bases were lacking, viz. Chemistry and knowledge of the essential organic structure, the cell. Natural science, at the outset revolutionary, was confronted by an out and out conservative nature, in which everything remained today as it was at the beginning of the world, and in which right to the end of the world everything would remain as it had been in the beginning. It is characteristic that this conservative outlook on nature both in the inorganic and in the organic sphere. Astronomy, geology, physics, mechanics, paleontology, chemistry, mathematics, mineralogy, plant physiology, therapeutics, animal physiology, diagnostics, anatomy. The first breach, animal place. The second, geology and paleontology. The third, organic chemistry, which prepares organic bodies and shows the validity of chemical laws for living bodies. The fourth, 1842, mechanical heat, Grove. The fifth, Darwin, Lamarck, the cell, etc. The sixth, the comparative elements in anatomy, climatology, animal and plant geography, physical geography in general, the assembling of the material and its interconnection. Morphology. The old teleology has gone to the devil, but it is now firmly established that matter and its eternal cycle moves according to laws which at a definite stage, now here, now there, necessarily give rise to a thinking mind in organic beings. The normal existence of animals is given by the contemporary conditions in which they live and to which they adapt themselves. Those of man, as soon as he differentiates himself from the animal in the narrower sense, have as yet never been present, and are only to be elaborated by the ensuing historical development. Man is the sole animal capable of working his way out of the mere animal state. His normal state is one appropriate to his consciousness, one that has to be created by himself. Omitted from Feuerbach 127. All the advances made by natural science since then served them merely as fresh arguments against the belief in the creator of the universe, and in fact the further development of theory was quite outside their line of business. Idealism was hard hit, owing to 1848, but materialism in this renovated form of it sank still lower. Feuerbach was absolutely right in repudiating responsibility for this materialism, only he had no right to confuse the doctrine of the itinerant creatures with materialism in general. At about the same time, however, empirical natural science made such an advance and arrived at such brilliant results that not only did it become possible to overcome completely the mechanical one-sidedness of the 18th century, but also natural science itself, owing to the proof of the interconnections existing in nature itself between the various fields of investigation, was transformed from an empirical into a theoretical science and, by generalizing the results achieved, into a system of the materialist knowledge of nature. The mechanics of gases, newly created organic chemistry, which stripped the last remnants of incomprehensibility from one so-called organic compound after another by preparing them from inorganic substances, scientific embryology dating from 1818, geology and paleontology, comparative anatomy of plants and animals, all these furnished new material in an unprecedented measure. Three great discoveries, however, were of decisive importance. The first was the proof of the transformation of energy arising out of the discovery of the mechanical equivalent of heat. All the innumerable acting causes in nature, which had hitherto led mysterious, inexplicable existence as so-called forces, mechanical force, heat, radiation, electricity, magnetism, chemical force of association and dissociation, have now been proved to be special forms, modes of existence of one and the same energy, that is, motion. We can not only demonstrate its conversion from one form into another, which continually takes place in nature, but we can carry out this conversion in the laboratory and in industry, and indeed in such a way that a given quantity of energy in one form always corresponds to a given quantity of energy in some other form. Thus we can express a unit of heat in kilogram meters and the units or any quantity of electrical or chemical energy once more in heat units and vice versa. We can likewise measure the energy consumption and energy intake of a living organism and express it in any desired unit. For example, in heat units, the unity of all motion in nature is no longer a philosophical assertion, but a natural scientific fact. The second discovery, earlier in point of time, was that of the organic cell by Schwann and Schleiden as being the unit out of which, by its multiplication and differentiation, all organisms with the exception of the lowest are formed and develop. This discovery for the first time gave a firm basis to the investigation of the organic, living products of nature, both comparative anatomy and physiology, and embryology. The origin, growth, and structure of organisms were deprived of their mysterious character. The hitherto incomprehensible miracle was merged in a process which takes place according to a law that is essentially identical for all multicellular organisms. But an essential gap still remained. If all multicellular organisms, both plants and animals, including man, in each case grow out of a single cell according to the law of cell division, what then is the source of the infinite diversity of these organisms? This question was answered by the third great discovery, the theory of evolution, which for the first time was comprehensively worked out and substantiated by Darwin. However, many transformations this theory will still undergo as regards details. In the main, it has already solved the problem in a more than adequate manner. The evolutionary series of organisms from a few simple forms to increasingly multifarious and complicated ones, as it confronts us today, and extending right up to man, has been established as far as its main features are concerned. Thanks to this, not only has it become possible to explain the existing stock of organic products of nature, but the basis has also been provided for the prehistory of the human mind, for tracing the various stages of its development, from the simple protoplasm, structureless but sensitive to stimuli, of the lowest organisms right up to the thinking human brain. Without this prehistory, however, the existence of the thinking human brain remains a miracle. By means of these three great discoveries, the main processes of nature were explained and referred to natural causes. One thing still remains to be done here, to explain the origin of life from inorganic nature. At the present stage of science, it implies nothing less than the preparation of protein bodies from inorganic substances. Chemistry is approaching closer and closer to the solution of this task, but it is still a long way from it. If, however, we bear in mind that it was only in 1828 that Waller prepared the first organic body, urea, from inorganic materials, and what an innumerable number of so-called organic compounds are now artificially prepared without any organic materials, we shall not be inclined to be at chemistry halt when confronted by protein. So far, chemistry has been able to prepare every organic substance, the composition of which is accurately known. As soon as the composition of the protein bodies becomes known, chemistry would be able to set about the preparation of living protein. But to demand that it should achieve overnight what nature itself succeeds in doing only under very favorable circumstances on a few cosmic bodies after millions of years would be to demand a miracle. Thus, the materialist outlook on nature rests today on much firmer foundation than it did in the previous century. At that time, only the motion of heavenly bodies and of terrestrial solid bodies and the influence of gravity was at all exhaustively understood. Almost the entire field of chemistry and the whole of organic nature remained mysterious and not understood. Today, the whole of nature lies spread out before us as a system of interconnections and processes that, at least in its main features, has been explained and understood. At all events, the materialist outlook on nature means nothing more than the simple conception of nature just as it is, without alien addition, and hence among the Greek philosophers it was originally understood in this way as a matter of course. But between those ancient Greeks and us lie more than 2,000 years of an essentially idealist outlook on the world, and so the return to self-evident understanding is more difficult than it appears to be at first sight. For it is by no means a matter of simply throwing overboard the entire thought content of those 2,000 years, but of criticism of it, of extracting the results that had been one within a form that was false and idealistic, but which was inevitable for its time and for the course of evolution itself from this transitory form. And how difficult that is proved for us by those numerous natural scientists who are inexorable materialists within their science, but outside it are not merely idealists, but even pious and indeed orthodox Christians. All these epoch-making advances of natural science passed Feuerbach by without affecting him in any essential respect. This was not so much his fault as that of the miserable German conditions, owing to which the university chairs were occupied by envy-hated, eclectic hair splitters, while Feuerbach, who towered high above them, was compelled almost to rustic and lonely village isolation. That is why, on the subject of nature, he wastes so much labor, except for a few brilliant generalizations, on empty beltristic writing. Thus he says, life is, of course, not the product of a chemical process, nor in general is it the product of an isolated natural force or phenomenon, to which the metaphysical materialist reduces it. It is a result of the whole of nature. That life is a result of the whole of nature in the way contradicts the fact that protein, which is the exclusive independent bearer of life, arises under definite conditions determined by the whole interconnection of nature, but arises precisely as a product of a chemical process. To the same solitariness must be ascribed the fact that Feuerbach loses himself in a circle of barren speculations on the relation of thought to the thinking organ, the brain, a sphere in which Stark follows him willingly. Enough, Feuerbach revolts against the name materialism, and not entirely without reason, for he never completely ceases to be an idealist. In the field of nature he is a materialist, but in the human field, God is nowhere treated worse than by natural scientists who believe in him. Materialists simply explain the facts, without making use of such phrases. They do this first when important and pious believers try to force God upon them, and then they answer correctly, either like a place, sire, Jan of Ace, etc. Or more rudely in the manner of the Dutch merchants who, when German commercial travelers press their shoddy goods on them, are accustomed to turn them away with the words, it can dissect and ruin, and that is the end of the matter. But what God has had to suffer at the hands of his defenders. In the history of modern natural science, God is treated by his defenders as Frederick William Free was treated by his generals and officials in the Jena campaign. One division of the army after another lays down its arms, one fortress after another capitulates before the march of science, until at last all infinite realm of nature is conquered by science, and there is no place left in it for the Creator. Newton still allowed in the first impulse, but forbade him any further interference in his solar system. Father Secchi bows him out of the solar system altogether, with all canonical honors it is true, but nonetheless categorically for all that, and he only allows him a creative act as regards the primordial nebula, and so in all spheres. In biology, his last breakdown Quixote, a gaseous, even ascribes positive nonsense to him. He is supposed to have created not only the actual animals, but also abstract animals, the fish as such. And finally, Tyndall totally forbids him any entry into nature and relegates him to the world of emotional processes, only admitting him because, after all, there must be somebody who knows more about all these things than John Tyndall. What a distance from the old God, the creator of heaven and earth, the maintainer of all things, without whom not a hair can fall from the head. Tyndall's emotional need proves nothing. The Chevalier d'Évry also had an emotional need to love and possess Marion Lescott, who sold herself and him over and over again. For her sake he became a crutch sharper and pimp, and if Tyndall wants to reproach him, he would reply with his emotional need. God equals Nescio, but ignorantia non est argumentum. Notes. 119. G.W.F. Hegel, work, B.D. 13, Berlin, 1833. 120. Regarding the word Placidus philosopher, it was subsequently proved that it did not come from Plutarch, but some other unknown author. It derives from Oedipus, who lived in about the year 100 of our era. 121. Genesis, chapter 2, verse 7. 122. This note is written in Marx's handwriting and consists of quotations in Greek from Aristotle's Metaphysica and from the compilatory work of Diogenes Laertius, Lives and Opinions of Famous Philosophers. The note dates from before June 1878, since it contains quotations about Epicurus, which were used by Engels in the old preface to Düring. All the italicized words in the quotations are Marx's. 123. In the latest editions of Metaphysica, Book 9 is called Book X 124. R. Wolf, Geschichte der Astronomie, Munchen, 1877. For Madler's book, see note 22. 125. This fragment constitutes the original outline of the introduction. 126. The Declaration of Independence, adopted on July 4, 1776, at the Philadelphia Congress of Delegates from 13 English colonies in North America, proclaimed the secession of these colonies from England and the establishment of an independent republic, the United States of America. 127. This is the heading of the fragment given in the list of contents of the second folder of materials for dialectics of nature. The fragment consists of 4 pages of the original manuscript of Feuerbach, number 16, 17, 18, and 19. At the top of page 16 is written in Engels' handwriting, Ausweg with Feuerbach. This fragment was part of the second chapter of Feuerbach was intended to follow immediately after the description of the 3 principal limitations of the French materialists of the 18th century. On finally revising the manuscript of Feuerbach, Engels removed these 4 pages and replaced them by another text, but the basic contents of these pages left out of the second chapter were reproduced in an abbreviated form in the 4th chapter of Feuerbach. Since Engels' Feuerbach was originally printed in the April and May issues of the magazine Die News for 1886, it can be considered that this fragment dates from the first quarter of 1886. On the first page of the fragment, the text begins in the middle of a sentence. The beginning of the sentence, restored according to the text of Feuerbach printed in Die News is given in square brackets. 128. This quotation is given in Stark's book of Feuerbach, Stuttgart, 1885, on pages 154-55. It is taken from Feuerbach's work Dialectics Fridge from Standpoint Anthropology, which was written in 1846. 129. Engels has in mind Feuerbach's aphorisms published posthumously in Gagron, Ludwig Feuerbach and Sein Brief Wechsel, Unbeklärt Salient seiner philosophischen Charakter and Ludwig Feuerbach in his Correspondence and Legacy, as well as in his philosophical development, B.D. 2. Leipzig on Heidelberg, 1874, S. 308. The aphorisms are quoted on p. 166 of Stark's book. Confer Fredrich Engels, Ludwig Feuerbach and the End of Classical German Philosophy, Chapter 2. 130. Sire, Jan of Hypothesis, decent hypotheses, the words will place an answer to Napoleon's question why he had made no mention of God in his work on celestial mechanics. 131. Engels is referring to Tyndall's opening speech at the 34th meeting of the British Association for the Advancement of Science in Belfast, August 19, 1874. In a letter to Marx dated September 21, 1874, Engels gives a more detailed characterization of his speech. 132. Ignorance is no argument, since Spinoza in his Ethics, as he opposes the exponents of the clerical teleological view on nature, who gave the will of God as the causes of all phenomena and had no other argument left them but the assertion that they knew no other causes. Buckner. Rise of the tendency, the passing of German philosophy into materialism, control over science abolished, outbreak of shallow materialist popularization, in which the materialism had to make up for the lack of science. Its flourishing at the time of the deepest degradation of bourgeois Germany and official German science minus 1850 to 60. Vogt, Maleshot, Buckner. Mutual assurance. New impulse by the coming into fashion of Darwinism, which was immediately monopolized by these gentlemen. One could let them alone and leave them to their not unpraiseworthy, if narrow occupation of teaching atheism, etc. By the German Philistine, but 4. 1. Abuse directed against philosophy. Buckner is acquainted with philosophy only as a dogmatist, just as he himself is a dogmatist of the Schlau's reflection of the German would be enlightenment, which missed the spirit and movement of the great French materialists, just as equally he had that of Voltaire. Blessings dead dogs Spinoza, note by Engels, which in spite of everything is the glory of Germany, and 2. The presumption of applying the theories about nature to society and reforming socialism. Thus it compels us to take note of them. First of all, what do they achieve in their own sphere? Quotations. 2. Turning point, pages 170-171, whence is some Hegelianism, transition to dialectics. 2. Philosophical tendencies, the metaphysical with fixed categories, the dialectical with fluid categories, the proofs that these fixed opposites of basis and consequence, cause and effect, identity and difference, appearance and essence are untenable. That analysis shows one pole already present in the otherness, that at a definite point the one pole becomes transformed into the other, and that all logic develops only from these progressing contradictions. This, mystical in Hegel himself, because the categories appear as pre-existing and the dialectics of the real world as their mere reflection. In reality it is the reverse. The dialectics of the mind is only the reflection of the forms of motion of the real world, both of nature and of history. Until the end of the last century, indeed until 1830, natural scientists could manage pretty well with the old metaphysics, because real science did not go beyond mechanics, terrestrial and cosmic. Nevertheless, confusion had already been introduced by higher mathematics, which regards the eternal truth of lower mathematics as a superseded point of view, often asserting the contrary, and putting forward propositions which appear sheer nonsense to the lower mathematician. The rigid categories disappeared here. Mathematics arrived at a field where even such simple relations as those of mere abstract quantity, bad infinity, assumed a completely dialectical form and compelled the mathematicians to become dialectical, unconsciously and against their will. There is nothing more comical than the twistings, subterfuges, and expedients employed by the mathematicians to solve this contradiction, to reconcile higher and lower mathematics, to make clear their understanding that what they had arrived at as an undeniable result is not sheer nonsense, and in general rationally to explain the starting point, method, and result of the mathematics of the infinite. Now, however, everything is quite different. Chemistry, the abstract divisibility of physical things, bad infinity, atomistics, physiology, the cell, the organic process of development, both of the individual and of species, by differentiation, the most striking test of rational dialectics, and finally the identity of the forces of nature and their mutual comparability, which put an end to all fixity of categories. Nevertheless, the bulk of natural scientists are still held fast in the old metaphysical categories and helpless when these modern facts, which so to say prove the dialectics in nature, have to be rationally explained and brought into relation with one another. And here thinking is necessary. Atoms and molecules, etc., cannot be observed under the microscope, but only by the process of thought. Compare the chemists and cellular pathology, where in the end the helplessness is to be concealed by general phrases. Dialectics divested of mysticism becomes an absolute necessity for natural science, which has forsaken the field where rigid categories sufficed, which represent as it were the lower mathematics of logic, its everyday weapons. Philosophy takes its revenge posthumously on natural science for the latter having deserted it. And yet the scientists could have seen even from the successes in natural science achieved by philosophy that the latter possessed something that was superior to them even in their own special sphere. Leibniz, the founder of the mathematics of the infinite, in contrast to whom the inductive ass Newton appears as a plagiarist and corrupter. Kant, the theory of the origin of the universe before the place. Again, the first in Germany to accept the theory of evolution. Hegel, whose comprehensive treatment and rational grouping of the natural sciences is a greater achievement than all the materialistic nonsense put together. On Buckner's claim to pronounce judgment on socialism and political economy on the basis of the struggle for existence. Hegel, on topic. On politics and socialism, the understanding for which the world has waited. B. 11. Separation, coexistence, and succession. Hegel, Encyclopedia, B. 35. As determination of the sensuous, of the idea. Hegel, Encyclopedia, B. 40. Natural phenomena, but in Buckner, not thought about, merely copied out, hence it is superfluous. Page 42. Someone's laws were produced out of his head. Buckner is able to do the same for modern society. Page 45. Metaphysics, the science of things, not of movements. Page 53. In experience, everything depends upon the mind we bring to bear upon actuality. A great mind is great in its experience, and the might play a phenomena at once perceives the point of real significance. Page 56. The parallelism between the human individual and history. The parallelism between embryology and paleontology. Just as Fourier is a mathematical poem and yet still used, so Hegel a dialectical poem. The incorrect theory of porosity is presented by Hegel as a pure figment of the mind. Hegel, Encyclopedia, I, pages 205-206, a prophetic passage on atomic weights in contrast to the physical views of the time, and on atoms and molecules as thought determinations, on which thinking has to decide. If Hegel regards nature as a manifestation of the eternal idea, it is alienation, and if this is such a serious crime, what are we to say of the morphologist Richard Owen? The archetypal idea was manifested in the flesh under diverse modifications upon this planet, long prior to the existence of those animal species that actually exemplify it. If that is said by a mystical natural scientist, who means nothing by it, it is calmly allowed to pass, but if a philosopher says the same thing, and one who means something by it, and indeed finds something correct, although in inverted form, then it is mysticism and a terrible crime. Natural scientific thought. A gaseous plan of creation, according to which God proceeded in creation from the general to the particular and individual, first creating the vertebrate as such, then the mammal as such, the animal of prey as such, the cat as such, and only finally the lion, etc. That is to say, first of all abstract ideas in the shape of concrete things and then concrete things. In Ockham the nonsense that has arisen from the dualism between natural science and philosophy is evident. By the path of thought, Ockham discovers protoplasm and the cell, but it does not occur to anyone to follow up the matter along the lines of natural scientific investigation. It is to be accomplished by thinking. And when protoplasm and the cell were discovered, Ockham was in general disrepute. Hoffman cites the philosophy of nature. A quotation from Rosencrantz, the Belfast, whom no real Hegelian recognizes. To make the philosophy of nature responsible for Rosencrantz is as foolish as Hoffman making the Hans Lorentz responsible for Margaret's discovery of beet sugar. Theory and empiricism. The lateness of the earth was theoretically established by Newton, the Cassinis, and other Frenchmen maintained a long time afterwards, on the basis of their empirical measurements, that the earth is ellipsoidal and the polar axis the longest one. The content of the empiricists of the Greeks receives a peculiar illustration if one reads, for instance, T.H. Thomson, or people like Davy, and even Faraday grope in the dark, and make experiments that quietly mind one of the stories of Aristotle and Pliny about physical chemical phenomena. It is precisely in this new science that the empiricists entirely reproduce the blind groping of the ancients, and when Faraday with his genius gets on the right track, the Philistine Thomson has to protest against it. Hegel, Anthropogeny, p. 707. According to the materialist outlook on the world, matter or substance was present earlier than motion or vis viva, matter created force. This is just as false as that force created matter, since force and matter are inseparable. Where does he get his materialism from? Quasi-finals and efficiency transformed by Hegel into purposively acting and mechanically acting causes, because for him chaos finalist equals God. Likewise for him mechanical, adapted out of hand from Kant, equals monistic, not equals mechanical in the sense of mechanics. With such confusion of language, nonsense is inevitable. What Hegel says here, Kant's critique of Hurtau's graph does not agree with Hegel. Another example of polarity in Hegel, mechanism equals monism, and vitalism or teleology equals dualism. Already in Kant and Hegel, purpose is a protest against dualism. Mechanism applied to life is a helpless category. At the most we could speak of Schmism, if we do not want to renounce all understanding of names. Purpose, Hegel, v. p. 205. Thus mechanism manifests itself as a tendency of totality in that it seeks to seize nature for itself as a whole which requires no other for its notion, a totality which is not found in it, and the extra mundane understanding which is associated therewith. The point is, however, that mechanism does not get away from abstract necessity, and hence not from chance either. That matter evolves out of itself. The thinking human brain is from mechanism of pure accident, although necessarily determined, step by step, where it happens. But the truth is that it is the nature of matter to advance to the evolution of thinking beings, hence this always necessarily occurs wherever the conditions for it are present. Further, Hegel, v. p. 206. Consequently, in its connection of external necessity, this principle offers the consciousness of infinite freedom as against teleology, which sets up as something absolute whatever it contains that is trivial or even contemptible. And here a more universal thought can only feel infinitely cramped or even nauseated. Here, again, the colossal waste of matter in motion in nature. In the solar system there are perhaps 3 planets at most on which life and thinking beings could exist under present conditions, and the whole enormous apparatus for their sake. The inner purpose of the organism, according to Hegel, operates through impulse. Trop form. Impulse is supposed to bring the single living being more or less into harmony with the idea of it. From this is seen how much the whole inner purpose is itself an ideological determination, and yet Lamarck is contained in this. Natural scientists believe that they free themselves from philosophy by ignoring or abusing it. They cannot, however, make any headway without thought, and for thought they need thought determinations. But they take these categories unreflectingly from the common consciousness of so-called educated persons, which is dominated by the relics of long obsolete philosophies, or from a little bit of philosophy compulsory to listen to at the university, or from uncritical non-systematic reading of philosophical writings of all kinds. Hence they are no less in bond to philosophy, but unfortunately in most cases to the worst philosophy, and those who abuse philosophy most are slaves to precisely the worst vulgarized relics of the worst philosophies. Natural scientists may adopt whatever attitude they please, they are still under the domination of philosophy. It is only a question whether they want to be dominated by bad, fashionable philosophy, or by form of theoretical thought which rests on acquaintance with the history of thought and its achievements. Physics, beware of metaphysics, is quite right, but in a different sense. Natural scientists allow philosophy to prolong an illusory existence by making shift with the dregs of the old metaphysics. Only when natural and historical sciences become imbued with dialectics will all the philosophical rubbish, other than the pure theory of thought, be superfluous, disappearing in positive science. Notes. 133. The fragment-headed Buckner was written before the other parts of Dialectics of Nature. It is the opening note of the first folder of the manuscript. The fragment is apparently a synopsis of a work planned by Engels against Buckner as an exponent of vulgar materialism and social Darwinism. Judging by the content of the fragment and by Engels' marginal notes in his copy of Buckner's book remains since the London Printer, a second edition of which appeared late in 1872, Engels proposed to criticize primarily this work of Buckner's. The laconical comment we find in W. Leibniz's letter to Engels dated February 8, 1873 as for Buckner, go ahead, seems to suggest that Engels had just informed Leibniz of his plan. It is therefore safe to assume that this fragment was written early in 1873. 134. Engels is quoting the following passage from the preface to the second edition of Hegel's Encyclopedia of the Philosophical Sciences. Lessing said in his time that people treat Spinoza like a dead dog. Hegel had in mind a conversation between Lessing and Jacobi on June 7, 1780, during which Lessing had said, why, people still talk off Spinoza as if he were a dead dog. C.F.A. Jacobi, work, B.D. IV, apt. I. Leipzig, 1819, S68. Hegel deals in detail with the French materialists in Volume 3 of his History of Philosophy. 135. The references to L. Buckner, Der Mensch und Saint-Stefan. In the Natur und Vergangenheit, Gegenwart und Zukunft, 2, Otto, Leipzig, 1872. On pages 170-171 of his book, Buckner says that as mankind gradually develops, there arrives the moment when nature and man becomes aware of itself and when man stops submitting passively to the blind laws of nature to become their master, that is, when quantity becomes quality, to use Hegel's phrase. In his copy of Buckner's book, Engels marked this passage with a stroke and commented, Umschlag. 136. Engels has in mind the limitation of Newton's philosophical views, his one-sided overestimation of the method of induction, and his negative attitude to hypotheses, expressed by him in the well-known words hypotheses non fingo. See note 15. 137. At the present time it is considered to be beyond doubt that Newton arrived at the discovery of the differential and integral calculus independently of it earlier than Leibniz, but Leibniz, who made this discovery also independently, gave it a more perfect form. Already within 2 years of writing the present fragment, Engels expressed a more accurate view on this question. 138. Engels has in mind the following passage from Hegel's Legitimate Encyclopedia of Philosophy, Wissenschaft, 5. Note, everybody allows that to know any other science you must have first studied it, and that you can only claim to express a judgment upon it in virtue of such knowledge. Everybody allows it to make a shoe you must have learned and practiced the craft of the shoemaker. For philosophy alone, it seems to be imagined. Such study, care, and application are not in the least requisite. 139. Hegel, Encyclopedia of the Philosophical Sciences, 6. Observation. This divorce between idea and reality is especially dear to the analytic understanding which looks upon its own abstractions, dreams though they are, as something true and real, and prides itself on the imperative odd, which it takes a special pleasure in prescribing even on the field of politics, as if the world had waited on it to learn how it ought to be, and was not. 140. Ibid. Observation to 20. 131. Ibid. Addendum to 21. 132. The references to Hegel's argument on the transition from an naively unsophisticated state to a state of reflection, both in the history of society and in the development of the individual, but the truth is that the awakening of consciousness follows from the very nature of men, and the same history repeats itself in every son of Adam. 133. A mathematical poet is the term applied by W. Thomson to the book of the French mathematician Jean-Baptiste Joseph Fourier Theory Analytique de Paris, 1822. See the appendix to the book of Thomson and take treatise on natural philosophy by Oxford, 1867, p. 715. In the synopsis of this book made by Engels, this passage is copied out and underlined. 134. Hegel, Encyclopedia of the Philosophical Sciences, 130. Observation. Science of Logic, Book 2, Section 11, Chapter 1, Note on the Porosity of Matter. 135. Hegel, Encyclopedia of the Philosophical Sciences, 103. Addendum. Here Hegel is polemizing with those physicists who explain the differences of the specific gravity of bodies by saying that a body with a specific gravity twice that of another contains within the same space twice as many material parts as the other. 136. R01 on the Nature of Limbs, London, 1849, p. 86. 137. E. Hegel, Geschichte 4. Otto, Berlin, 1873. 138. On page 26 of his book, Hoffmann gives the following quotation from Rosenkranz's book System der Wissenschaft. Hein Philosophische Zentralien, Königsberg, 1850. Platinum is basically only a paradox of silver, wishing to occupy already the highest stage of metallicity. This belongs only to gold. Hoffmann speaks of the services of the Prussian King Fredrich William III in organizing the sugar beet industry on pages 5-6 of his book. 139. In Engels' manuscript, the surname Cassini is given in the plural. 4 astronomers named Cassini are known in the history of French science. 1. Giovanni Domenico Cassini, first director of the Paris Observatory, who emigrated from Italy. 2. His son Jacques Cassini. 3. The son of the last named, Cesar Francois Cassini. And 4. His son Jacques Dominique Cassini. All 4 consecutively held the office of director of the Paris Observatory. The first 3 upheld incorrect anti-Newtonian notions of the shape of the Earth, and only the last was compelled, under the influence of more accurate measurements of its volume and shape, to admit that Newton was correct in inferring that the globe is compressed along the axis of its rotation. 150. Th. Thomson, An Outline of the Sciences of Heat and Electricity, 2nd edition, London, 1840. 151. E. Hegel, Anthropologie oder Beziehungsgeschichte der Menschen, Leipzig, 1874. 707-08. 152. Hegel stresses the contradiction and consequent off the teleological faculty of judgment between the mechanical methods of explanation and teleology, Hegel depicting the latter, in opposition to Kant, as the doctrine of external aims, of external expediency. Hegel, however, who examines this same critique of the teleological faculty of judgment in his History of Philosophy, Volume 3, Part 3, Chapter 4, Paragraph on Kant, put in the foreground Kant's conception of inner expediency, according to which an organic being is everything's purpose, and reciprocally also means. 153. Hegel, Science of Logic, Book 3, Section 2, Chapter 3. In working on dialectics of nature, Engels used the edition G.W.F. Hegel, work, B.D. V. 2, Otto, Berlin, 1841. 154. Ibid. Section 3, Chapter 1. 155. That is, taking metaphysics not in its old meaning, not as Newton did, for example, who regarded it as philosophical thought in general, but in its modern meaning, that is, as the metaphysical method of thought. Dialectics. A general questions of dialectics. The fundamental laws of dialectics. Dialectics, so-called objective dialectics, prevails throughout nature, and so-called subjective dialectics, dialectical thought, is only a reflection of the motion through opposites which asserts itself everywhere in nature, and which by continual conflict of the opposites and their final passage into one another, or into higher forms, determines the life of nature, attraction and repulsion. Polarity begins with magnetism. It is exhibited in one and the same body. In the case of electricity, it distributes itself over 2 or more bodies which become oppositely charged. All chemical processes reduce themselves to processes of chemical attraction and repulsion. Finally, in organic life, the formation of the cell nucleus is likewise to be regarded as a polarization of the living protein material, and from the simple cell onwards, the theory of evolution demonstrates how each advance up to the most complicated plant on the one side, and up to man on the other, is affected by the continual conflict between heredity and adaptation. In this connection, it becomes evident how little applicable to such forms of evolution are categories like positive and negative. One can conceive of heredity as the positive, conservative side, adaptation as the negative side that continually destroys what has been inherited, but one can just as well take adaptation as the creative, active, positive activity, and heredity as the resisting, passive, negative activity. But just as in history progress makes its appearance as a negation of the existing state of things, so here also, on purely practical grounds, adaptation is better conceived as negative activity. In history, motion through opposites is most markedly exhibited in all critical epochs of the foremost peoples. At such moments, a people has only the choice between the 2 horns of a dilemma, either or, and indeed, the question is always put in a way quite different from that in which the Philistines, who dabble in politics in every age, would have liked it put. Even the liberal German Philistine of 1848 found himself in 1849 suddenly, unexpectedly, and against his will confronted by the question, a return to the old reaction and intensified form, or continuance of the revolution up to the republic, perhaps even one indivisible republic with a socialist background. He did not spend long in reflection and helped to create the Mendeifel reaction as the flower of German liberalism. Similarly, in 1851, the French bourgeois, when faced with a dilemma which he certainly did not expect, a caricature of the empire, Praetorian rule, and the exploitation of France by a gang of scoundrels, or a social democratic republic, and he bowed down before the going of scoundrels, so as to be able, under their protection, to go on exploiting the workers. Hard and fast lines are incompatible with the theory of evolution. Even the border line between vertebrates and invertebrates is now no longer rigid, just as little as that between fishes and amphibians, while that between birds and reptiles dwindles more and more every day. Between compsognathus and archaeopteryx only a few intermediate links are wanting, and birds of beaks with teeth crop up in both hemispheres. Either or becomes more and more inadequate. Among lower animals, the concept of the individual cannot be established at all sharply. Not only is it whether a particular animal is an individual or a colony, but also where in development one individual ceases and the other begins. For a stage in the outlook on nature, where all differences become merged in intermediate steps, and all opposites pass into one another through intermediate links, the old metaphysical method of thought no longer suffices. Dialectics, which likewise knows no hard and fast lines, no unconditional, universally valid either or, and which bridges the fixed metaphysical differences. And besides either or, recognizes also in the right place both this and that, and reconciles the opposites, is the sole method of thought appropriate in the highest degree to the stage. Of course, for everyday use, for the small change of science, the metaphysical categories retain their validity. The transformation of quantity into quality equals mechanical world outlook, quantitative change alters quality. The gentleman never suspected that. The character of mutual opposites belonging to the thought determinations of reason, polarization. Just as electricity, magnetism, etc., become polarized and move in opposites, so do thoughts. Just as in the former it is not possible to maintain any one-sidedness, and a natural scientist would think of doing so, so also in the latter. The true nature of the determinations of essence is expressed by Hegel himself. In essence, everything is relative. Part and whole, for instance, are already categories which become inadequate in organic nature. The ejection of seeds, the embryo, and the newborn animal are not to be conceived as a part that is separated from the whole. That would give a distorted treatment. It becomes a part only in a dead body. Simple and compound categories which even in organic nature likewise lose their meaning and become inapplicable. An animal is expressed neither by its mechanical composition from bones, blood, gristle, muscles, tissues, etc., nor by its chemical composition from the elements. Hegel, the organism is neither simple nor compound, however complex it may be. Abstract identity is likewise inapplicable in organic nature. The plant, the animal, every cell is at every moment of its life identical with itself and yet becoming distinct from itself by absorption and excretion of substances, by respiration, by cell formation and death of cells, by the process of circulation taking place. In short, by a sum of incessant molecular changes which make up life and the sum total of whose results is evident to our eyes in the phases of life: embryonic life, youth, sexual maturity, process of reproduction, old age, death. The further physiology develops, the more important for it become these incessant, infinitely small changes, and hence the more important for it also the consideration of difference within identity, and the old abstract standpoint of formal identity, that an organic being is to be treated as something simply identical with itself, as something constant, becomes out of date. In the margin of the manuscript occurs the remark, apart, moreover, from the evolution of species. Nevertheless, the mode of thought based thereon, together with its categories, persists. But even in organic nature, identity as such is in reality non-existent. Every body is continually exposed to mechanical, physical, and chemical influences, which are always changing and modifying its identity. Abstract identity, with its opposition to difference, is in place only in mathematics, an abstract science which is concerned with creations of thought, even though they are reflections of reality, and even though it is continually being subdivided. Hegel, Encyclopedia, I.P. 235. The fact that identity contains difference within itself is expressed in every sentence, where the predicate is necessarily different from the subject. The lily is a plant, the rose is red, where either in the subject or in the predicate. There is something that is not covered by the predicate or the subject. Hegel, p. 231. That from the outset identity with itself requires difference from everything else as its complement is self-evident. Continual change, that is, sublation of abstract identity with itself, is also found in so-called inorganic nature. Geology is its history. On the surface, mechanical changes, chemical changes. Internally, mechanical changes, heat, chemical. On the large scale, upheavals, earthquakes, etc. The slate of today is fundamentally different from the use from which it is formed, the chalk from the loose microscopic shells that compose it, even more so limestone, which indeed according to some is of purely organic origin, and sandstone from the loose sea sand, which again is derived from disintegrated granite, etc., not to speak of coal. The law of identity in the old metaphysical sense is the fundamental law of the old outlook, equals A. Each thing is equal to itself. Everything was permanent. The solar system, stars, organisms. This law has been refuted by natural science bit by bit in each separate case, but theoretically it still prevails and is still put forward by the supporters of the old in opposition to the new. A thing cannot simultaneously be itself and something else. And yet the fact that true, concrete identity includes difference, change, has recently been shown in detail by natural science. Abstract identity, like all metaphysical categories, suffices for every dialectic where small dimensions or brief periods of time are in question. The limits within which it is usable differ in almost every case and are determined by the nature of the object. For a planetary system, where in ordinary astronomical calculation the ellipse can be taken as a basic form for practical purposes without error, they are much wider than for an insect that completes its metamorphosis in a few weeks. For natural science in its comprehensive role, however, even in each single branch, abstract identity is totally inadequate, and although on the whole it has now been abolished in practice, theoretically it still dominates people's minds. And most natural scientists imagine that identity and difference are reconcilable opposites, instead of one-sided poles which represent the truth only in the reciprocal action, and the inclusion of difference within identity. Identity and difference, necessity and chance, cause and effect, the two main opposites in the manuscript, divide and how begin such. Engels is in mind, the antithesis of identity and difference, and the antithesis of cause and effect. The words necessity and chance were written between the lines afterwards, which, treated separately, become transformed into one another. And then first principles must help. Positive and negative can also be given the reverse names in electricity, etc. North and south ditto. If one reverses this and alters the rest of the terminology accordingly, everything remains correct. We can call west east and east west. The sun rises in the west, and planets revolve from east to west, etc. The names alone are changed. Indeed, in physics we call the real south pole of the magnet, which is attracted by the north pole of the Earth's magnetism, the north pole, and it does not matter. That positive and negative are equivalent, irrespective of which side is positive and which negative, not only in analytical geometry, but still more in physics. Polarity. A magnet, on being cut through, polarizes the neutral middle portion, but in such a way that the old poles remain. On the other hand, a worm, on being cut into two, retains the receptive mouth at the positive pole and forms a new negative pole at the other end with expiratory anus. But the old negative pole now becomes positive, becoming a mouth. And a new anus or negative pole is formed at the cut end. Voila, transformation of positive into negative. Polarization. For J. Grimm it was still a firmly established law that a German dialect must be either High German or Low German. In this he totally lost sight of the Frankish dialect. Because the written Frankish of the later Carlovingian period was High German, he imagined that Frankish passed in one place into Old High German, in another place into French. It then remained absolutely impossible to explain the source of the Netherland dialect in the ancient Salic regions. Frankish was only rediscovered after Grimm's death, solid in its rejuvenation as the Netherland dialect, reverberating in the Middle and Lower Rhine dialects, which in part have been shifted to various stages of High German, and in part have remained Low German. So the Frankish is a dialect that is both High German and Low German. Chance and necessity. Another opposition in which metaphysics is entangled is that of chance and necessity. What can be more sharply contradictory than these two thought determinations? How is it possible that both are identical, that the accidental is necessary, and the necessary is also accidental? Common sense, and with the majority of natural scientists, treats necessity and chance as determinations that exclude each other once for all. A thing, a circumstance, a process is either accidental or necessary, but not both. Hence both exist side by side in nature. Nature contains all sorts of objects and processes, of which some are accidental, the others necessary, and it is only a matter of not confusing the two sorts with each other. Thus, for instance, one assumes the decisive specific characters to be necessary, other differences between individuals of the same species being termed accidental, and this holds good of crystals as it is for plants and animals. Then again, the lower group becomes accidental in relation to the higher, so that it is declared to be a matter of chance how many different species are included in a genus Felis or games, or how many genera and orders there are in the class, and how many individuals of each of these species exist, or how many different species of animals occur in a given region, or what in general the fauna and flora are like. And then it is declared that the necessary is the sole thing of scientific interest, and that the accidental is a matter of indifference to science. That is to say, what can be brought under laws, hence what one knows is interesting, what cannot be brought under laws, and therefore what one does not know is a matter of indifference and can be ignored. The bioscience comes to an end, for it is to investigate precisely that which we do not know. That is to say, what can be brought under general laws is regarded as necessary, and what cannot be so brought as accidental. Anyone can see that this is the same sort of science as that which proclaims natural what it can explain, and ascribes what it cannot explain to supernatural causes. Whether I turn the cause of the inexplicable chance, or whether I turn to God, is a matter of complete indifference as far as the thing itself is concerned. Both are only equivalents for I do not know, and therefore do not belong to science. The latter ceases where the requisite connection is wanting. In opposition to this view there is determinism, which passed from French materialism into natural science, and which tries to dispose of chance by denying it altogether. According to this conception, only simple, direct necessity prevails in nature. The particular pea pod contains 5 peas and not 4 or 6. The particular dog's tail is 5 inches long and not a whit longer, or sure that this year a particular clover flower was fertilized by bee and another not. And indeed by precisely one particular bee and a particular time. The particular wind-blown dandelion seed has sprouted and another not. That last night I was bitten by a flea at 4 o'clock in the morning, and not 3 or 5 o'clock. And on the right shoulder and not on the left calf. These are all facts which have been produced by a irrevocable concatenation of cause and effect, by an unshakable necessity of such a nature indeed that the gaseous sphere, from which the solar system was derived, was already so constituted that these events had to happen thus and not otherwise. With this kind of necessity we likewise do not get away from the theological conception of nature. Whether with Augustine and Calvin we call it the eternal decree of God, or Kismet as the Turks do, or whether we call it necessity, is all pretty much the same. For science, there is no question of tracing the chain of causation in any of these cases. So we are just as wise in one as in another. The so-called necessity remains an empty phrase, and with it, chance also remains what it was before. As long as we are not able to show on what the number of peas in the pod depends, it remains just a matter of chance, and the assertion that the case was foreseen already in the primordial constitution of the solar system does not get us a step further. Still more, a science which was set about the task of following back the sketches of this individual people and its consequent concatenation would be no longer science but pure trifling, for the same people alone has an addition of numeral other individual, accidentally appearing qualities, shade of color, thickness and hardness of the pod, size of the piece, not to speak of the individual peculiarities revealed by the microscope. The one P pod, therefore, would already provide more causal connections for following up than all the botanists in the world could solve. Hence chance is not here explained by necessity, but rather necessity is degraded to the production of what is merely accidental. If the fact that a particular P pod contains 6 P's, and not 5 or 7, is of the same order as the law of motion of the solar system, or the law of the transformation of energy, then as a matter of fact chance is not elevated to necessity, but rather necessity degraded to chance. Furthermore, however much the diversity of the organic and inorganic species and individuals existing side by side in a given area may be asserted to be based on irrefutable necessity, for the separate species and individuals it remains what it was before, a matter of chance. For the individual animal it is a matter of chance, where it happens to be born, what environment it finds for living, what enemies and how many of them threaten it. For the mother plant it is a matter of chance whether the wind scatters its seeds, and, for the daughter plant, where the sea finds soil for germination, and to assure us that here also everything rests on irrefutable necessity is a poor consolation. The jumping together of natural objects in a given region, still more in the whole world, for all the primordial determination from eternity, remains what it was before, a matter of chance. In contrast to both conceptions, Hegel came forward with the hitherto quite unheard of propositions that the accidental has a cause because it's accidental, and just as much also as no cause because it's accidental, that the accidental is necessary, that necessity determines itself as chance. And, on the other hand, this chance is rather absolute necessity. Natural science has simply ignored these propositions as paradoxical trifling, as self-contradictory nonsense, and, as regards theory, has persisted on the one hand in the biorhythms of thought of Wolffian metaphysics, according to which the things either accidental or necessary, but not both at once. Or, on the other hand, in the hardly less thoughtless mechanical determinism which in words denies chance in general only to recognize it in practice in each particular case. While natural science continued to think in this way, what did it do in the person of Darwin? Darwin in his epic making work set out from the widest existing basis of chance. Precisely the infinite, accidental differences between individuals within a single species, differences which become accentuated until they break through the character of the species, and whose immediate causes even can be demonstrated only in extremely few cases. Compelled into question the previous basis of all regularity in biology, viz. The concept of species and its previous metaphysical rigidity and unchangeability. Without a concept of species, however, all science was nothing. All its branches needed the concept of species as basis: human anatomy and comparative anatomy, embryology, zoology, paleontology, botany, etc. What were they without the concept of species? All the results were not only put in question, but directly set aside. Chance overthrows necessity, as conceived hitherto. The previous idea of necessity breaks down. To retain the means dictatorially to impose on nature as a law of human arbitrary determination that is in contradiction to itself and to reality, it means to deny the bio necessity in living nature. It means generally to proclaim the chaotic kingdom of chance to be the sole law of living nature. Cried out quite logically the biologists of all schools. Darwin, Hegel, logic, voila. Nothing that is opposed to something, the nothing of any something, is a determinate nothing. In view of the mutually determinate connection of the whole, metaphysics could make the assertion that if the least grain of dust were destroyed, all the universe must collapse. Negation, main passage, introduction, p. 38. That the self-contradictory resolves itself not fundamentally into abstract nothingness, but essentially only in tough negation of its particular content, etc. Negation of the negation, phenomenology, preface, b. 4. Body, flower, fruit, etc. b. Dialectical logic and the theory of knowledge, on the limits of knowledge. Unity of nature and mind. To the Greeks it was self-evident that nature could not be unreasonable, but even today the stupid as empiricists prove by reasoning that they are convinced from the outset that nature cannot be unreasonable or reason contrary to nature. The evolution of a concept, or the conceptual relation in the history of thought, is related to its development in the mind of the individual dialectician, just as the evolution of an organism in paleontology is related to its development in embryology. But this is so first discovered for concepts by Hegel. In historical development, chance plays its part, which in dialectical thinking, as in the development of the embryo, is summed up in necessity. Abstract and concrete, the general law of the change of form of motion is much more concrete than any single concrete example of it. Understanding and reason, this Hegelian distinction, according to which only dialectical thinking is reasonable, has a definite meaning. We have in common with animals all activity of the understanding, induction, deduction, and hence also abstraction, analysis of unknown objects, synthesis, and, as the union of both, experiment. In their nature all these modes of procedure, hence all means of scientific investigation that ordinary logic recognizes, are absolutely the same in men and higher animals. They differ only in degree of the basic features of the method of the same lead to the same results in men and animals, so long as both operate or makeshift, merely with these elementary methods. On the other hand, dialectical thought, precisely because it presupposes investigations of the nature of concepts themselves, is only possible for men, and for him only at a comparatively high stage of development, and it attains its full development much later still from modern philosophy, and yet with the colossal results already among the Greeks, which by far anticipate investigation. On the classification of judgments, dialectical logic, in contrast to the old, merely formal logic, is not, like the latter, content with enumerating the forms of motion of thought, that is, the various forms of judgment and conclusion, and placing them side by side without any connection. On the contrary, it derives these forms out of one another, it makes one subordinate to another instead of putting them on an equal level, it develops the higher forms out of the lower. Faithful to his division of the whole of logic, Hegel groups judgments as 1. Judgment of inherence, the simplest form of judgment, in which a general property is affirmatively or negatively predicated of a single thing. 2. Judgment of subsumption, in which a relation determination is predicated of the subject. 3. Judgment of necessity, in which its substantial determination is predicated of the subject. 4. Judgment of the notion, in which is predicated of the subject how far it corresponds to its general nature, or, as Hegel says, to the notion of it as a problematic judgment. This house is bad. Problematic judgment. If a house is constituted in such and such a way, it is good. Poietic judgment. The house that is constituted in such and such a way is good. 1. Individual judgment. 2 and 3. Special. 4. General. However dry this sounds here, and however arbitrary and precise this classification of judgments may here and there appear, yet the inner truth and necessity of this grouping will become clear to anyone who studies the brilliant exposition in Hegel's larger logic. To show how much this grouping is based not only on the laws of thought, but also on the laws of nature, we should like to put forward here a very well-known example outside this connection. That friction produces, he was already known practically to prehistoric men, who discovered the making of fire by friction perhaps more than 100,000 years ago, and who still warm cold parts of the body by rubbing. But from that to discover that friction is in general a source of heat, who knows how many thousands of years elapsed? Enough that the time came when the human brain was sufficiently developed to be able to formulate the judgment. Friction is a source of heat, a judgment of inherence, and indeed a positive one. Still further thousands of years passed until, in 1842, Mayer, Joule, and Pauling investigated this special process and its relation to other processes of similar kind that had been discovered in the meantime, that is, as regards its immediate general conditions, and formulated the judgment. All mechanical motion is capable of being converted into heat by means of friction. So much time and an enormous amount of empirical knowledge were required before we could make the advance in knowledge of the object from the above positive judgment of inherence to this universal judgment of subsumption. But from now on things went quickly. Only 3 years later, Mayer was able, at least in substance, to raise the judgment of subsumption to the level at which it now stands. Any form of motion, under conditions fixed for each case, is both able and compelled to undergo transformation, indirectly, as any other form of motion, a judgment of the notion, and moreover an apodeictic one, the highest form of judgment altogether. What, therefore, in Hegel appears as the development of the thought form of judgment as such, confronts us here the development of our empirically based theoretical knowledge of the nature of motion in general. This shows, however, that laws of thought and laws of nature are necessarily in agreement with one another, if only they are directly known. We can regard the first judgment as the individuality, the isolated fact that friction produces heat is registered. The second judgment is the particularity, a special form of motion, mechanical motion, exhibits its property under special conditions of passing into another special form of motion, viz. Heat. The third judgment is that of universality, any form of motion proves able and compelled to undergo transformation into any other form of motion. In this form the law attains its final expression. By new discoveries we can give new illustrations of it, we can give it a new and richer content, but we cannot add anything to the law itself as here formulated. In its universality, equally universal in form and content, is not susceptible of further extension. It is an absolute law of nature. Unfortunately, we are in difficulty about the form of motion of protein in its life, so long as we are not able to make protein. Above, however, it has also been proved that to make judgments involves not merely Kant's power of judgment, but A. Individuality, particularity, universality, these are the three determinations in which the whole doctrine of the notion moves. Under these heads, progression from the individual to the particular, and from the particular to the universal takes place not in one but in many modalities, and this is often enough exemplified by Hegel as the progression, individual, species, genus. And now the Hegels come forward with their induction and front, but it is a great fact against Hegel that progression must be from the individual to the particular, and then to the universal, from the individual to the species, and then to the genus, and then from it deduct the conclusions which are supposed to lead further. These people have gotten into such a deadlock over the opposition between induction and deduction that they reduce all logical forms of conclusion to these two, and in so doing do not notice that they unconsciously employ quite different forms of conclusion under those names. Deprive themselves of all wealth of forms of conclusion insofar as it cannot be forced under these two, and thereby convert both forms, induction and deduction, into sheer nonsense. Induction and deduction. Hegel, b. 75 at seek, where both draws the inductive conclusion that man, who does not normally have a maxillary bone, must have one, hence by incorrect induction arrives at something correct. Hegel's nonsense, induction against deduction, as if it were not the case that deduction equals conclusion, and therefore induction is also a deduction. This comes from polarization. Hegel struck pages 76-77, the conclusion polarized into induction and deduction. By induction it was discovered 100 years ago that crayfish and spiders were insects, and all lower animals were worms. By induction it has now been found that this is nonsense, and there exist X classes, wherein then lies the advantage of the so-called inductive conclusion, which can be just as false as the so-called deductive conclusion, the basis of which is nevertheless classification. Induction can never prove that there will never be a mammal without lacular glands. Formerly nipples were the mark of a mammal, but the platypus has none. The whole swindle of induction from the Englishman, way well, inductive sciences, comprising the purely mathematical, and so the antithesis to deduction invented. Logic, old or new, knows nothing of this. All forms of conclusion that start from the individual are experimental and based on experience. Indeed, inductive conclusion even starts from you, I.B. It is also characteristic of the thinking capacity of our natural scientists that fanatically champions induction at the very moment when the results of induction, the classifications, are everywhere put in question, and alien facts are being discovered which overthrow the entire previous classification by induction. What a beautiful confirmation of Hegel's thesis that the inductive conclusion is essentially a problematic one. Indeed, owing to the theory of evolution, even the whole classification of organisms has been taken away from induction and brought back to deduction. To descent, one species being literally deduced from another by descent, and it is impossible to prove the theory of evolution by induction alone, since it is quite inductive. The concepts with which induction operates, species, genus, class, have been rendered fluid by the theory of evolution, and so have become relative, but one cannot use relative concepts for induction. To the pan-inductionist, with all the induction in the world, we would never have got to the point of becoming clear about the process of induction. Only the analysis of this process could accomplish this. Induction and deduction belong together as necessarily as synthesis and analysis. Instead of one side relying one to the skies at the expense of the other, we should seek to apply each of them in its place, and that can only be done by bearing in mind that they belong together, that they supplement each other. According to the inductionist, induction is an infallible method. It is so little so that its apparently surest results are every day overthrown by new discoveries. Like corpuscles and caloric were results of induction. Where are they now? Induction taught us that all vertebrates have a central nervous system differentiated into brain and spinal cord, and that the spinal cord is enclosed in particularly certain bony vertebrae, whence indeed the name is derived. Then Amphioxus was revealed as a vertebrate with an undifferentiated central nervous strand without vertebrae. Induction established that fishes are those vertebrates which throughout life breathe exclusively by means of gills. Then animals come to life whose fish character is almost universally recognized, but which, besides gills, have also well-developed lungs, and it turns out that every fish carries a potential lung in the swim bladder. Only by audacious application of the theory of evolution did Hegel rescue the inductionists, who were feeling quite comfortable in these contradictions. If induction were really so infallible, whence come the rapid successive revolutions and classification of the organic world? They are the most characteristic product of induction, and yet they annihilate one another. Induction analysis, a striking example of how little induction can claim to be the sole, or even the predominant form of scientific discovery, occurs in thermodynamics. The steam engine provided the most striking proof that one can impart heat and obtain mechanical motion. 100,000 steam engines did not prove this more than one, but only more and more forced the physicists into the necessity of explaining it. Sadie Connett was the first seriously to set about the task, but not by induction. He studied the steam engine, analyzed it, and found that the process which matter does not appear in pure form, but is concealed by all sorts of subsidiary processes. He did away with these subsidiary circumstances that have no bearing on the essential process, and an ideal steam engine, which is true, is as little capable of being realized as, for instance, a geometrical line or surface, but in its way performs the same service as these mathematical abstractions. It presents the process in a pure, independent, and unadulterated form. And he came right up against the mechanical equivalent of heat, which he only failed to discover and see because he believed in caloric. Here also proof of the damage done by false theories. The empiricism of observation alone can never adequately prove necessity. Post hoc but not propter hoc. This discovery correctly does not follow from the continual rising of the sun in the morning that will rise again tomorrow, and in fact we know now today. Time will come when one morning the sun will not rise, but the proof of necessity lies in human activity, in experiment, in work. If I am able to make that post hoc, it becomes identical with the propter hoc. Causality. The first thing that strikes us in considering matter in motion is the interconnection of the individual motions of separate bodies that are being determined by one another. But not only do we find that the particular motion is followed by another, we find also that we can evoke a particular motion by setting up the conditions in which it takes place in nature, that we can even produce motions which do not occur at all in nature, at least not in this way, and that we can give these motions a predetermined direction and extent. In this way, by the activity of human beings, the idea of causality becomes established. The idea that one motion is the cause of another. True, the regular sequence of certain natural phenomena can by itself give rise to the idea of causality, the heat and light that come with the sun, but this effort is no proof, and to the extent human skepticism was correct in saying that a regular post hoc can never establish a propter hoc. But the activity of human beings forms its stuff and make them by proof that heat comes from the sun. If we bring together in a rifle deployment the explosive charge and the bullet and then fire it, we count upon the effect known in advance from previous experience, because we can follow in all its details the whole process of ignition, combustion, explosion by the sun, conversion into gas, and pressure of the gas on the bullet. And here the skeptic cannot even say that because of previous experience it does not follow that it will do the same next time. For, as a matter of fact, it does sometimes happen that it is not the same, that the priming of the gunpowder fails to work, that the barrel bursts, etc. But surely this which proves causality instead of refuting it, because we can find out the cause of each such deviation from the rule by appropriate investigation, chemical decomposition of the priming, dampness, etc. of the gunpowder, defect in the barrel, etc., etc. So that here the test of causality is so to say a double one. Natural science, like philosophy, has hitherto entirely neglected the influence of activity on their thought. Both know only nature on the one hand and thought on the other. But it is precisely the alteration of nature by man, not solely nature as such, which is most essential and immediate basis of human thought, and it is in the measure that man has learned to change nature that his intelligence has increased. The naturalistic conception of history has found, for instance, to a greater or lesser extent than Draper and other scientists, as if nature exclusively reacts on man, and natural conditions everywhere exclusively determine his historical development, is therefore one-sided and forgets that man also reacts on nature, changing and creating new conditions of existence for himself. There is devilishly little left of nature as it was in Germany at the time when the Germanic peoples integrated into it. The earth's surface, climate, vegetation, fauna, and human beings themselves have infinitely changed, and all this owing to human activity, while the changes of nature in Germany, which have occurred in this period of time without human interference, are incalculably small. Reciprocal action is the first thing that we encounter when we consider matter in motion as a whole from the standpoint of modern natural science. We see a series of forms of motion: mechanical motion, heat, light, electricity, magnetism, chemical union and decomposition, transitions of states of aggregation, organic life, all of which, if at present we still make an exception of organic life, pass into one another, mutually determine one another, are in one place cause and in another effect, the sum total of the motion in all its changing forms remaining the same. Mechanical motion becomes transformed into heat, electricity, magnetism, light, etc., and vice versa. Thus natural science confirms what Hegel has said, that reciprocal action is the true causal finalist of things. We cannot go back further than to knowledge of this reciprocal action, for the very reason that there is nothing behind to know. If we know the forms of motion of matter, then we know matter itself, and therewith our knowledge is complete. Only from this universal reciprocal action do we arrive at the real causal relation. In order to understand the separate phenomena, we have to tear them out of the general interconnection and consider them in isolation, and then the changing motions appear, one as cause and the other as effect. For one who denies causality every natural law's hypothesis, among others also the chemical analysis of heavenly bodies by means of the prismatic spectrum, what shallowness of thought to remain at such a viewpoint? On Nageli's incapacity to know the infinite Nageli, pages 12 to 13. Nageli first of all says that we cannot know real qualitative differences, and immediately afterwards says that such absolute differences do not occur in nature. Firstly, every quality has infinitely many quantitative gradations, for example, shades of color, hardness and softness, length of life, etc., and these, although qualitatively distinct, are measurable and knowable. Secondly, qualities do not exist but only things with qualities, and indeed with infinitely many qualities. Two different things always have certain qualities in common, others differ in degree, while still others may be entirely absent in one of them. If we consider two such extremely different things, for example, a meteorite and a man, in separation, we get very little out of it. At most, the heaviness and other general properties of bodies are common to both. But an infinite series of other natural objects and natural processes can be put between the two things, permitting us to complete the series from meteorite to man, and to allocate to each its place in the interconnection of nature and thus to know them. Nageli himself admits this. Thirdly, our various senses might give us impressions differing absolutely as regards quality. In that case, properties which we experience by means of sight, hearing, smell, taste, and touch would be absolutely different. But even here, the differences disappear with the progress of investigation. Smell and taste have long ago been recognized as the light senses belonging together, which receive conjoined and identical properties. Sight and hearing both receive wave oscillations. Touch and sight supplement each other to such an extent that from the appearance of an object we can often enough predict its tactile properties. And, finally, it is always the same light that receives and elaborates all these different sense impressions, that therefore comprehends them into unity, and likewise these various impressions are provided by the same thing, appearing as its common properties, and therefore helping us to know it. To explain these different properties accessible only to different senses, to bring them into connection with one another, is precisely the task of science, which so far has not complained because we have not a general sense in place of the five special senses, or because we are not able to see or hear, taste, and smells. Wherever we look, nowhere in nature are there to be found such qualitatively or absolutely distinct fields. B. 12, which are alleged to be incomprehensible. The whole confusion springs from the confusion about quality and quantity. In accordance with the prevailing mechanical view, Nageli regards all qualitative differences as explained only insofar as they can be reduced to quantitative differences, or because quality and quantity are for him absolutely distinct categories. Metaphysics. We can know only the finite, etc. This is quite correct insofar as only finite objects enter the sphere of our knowledge, but the proposition needs to be supplemented by this. Fundamentally, we can know only the infinite. In fact, all real, exhaustive knowledge consists solely in raising the individual thing and thought from individuality into particularity, and from this of the universality in seeking and establishing the infinite and the finite, the eternal and the transitory. The form of universality, however, is the form of self-completeness, hence of infinity. It is the comprehension of the many finites and the infinite. We know that chlorine and hydrogen, within certain limits of temperature and pressure, and under the influence of light, combine with an explosion to form hydrochloric acid gas. And as soon as we know this, we know also that this takes place everywhere and at all times, where the above conditions are present, and it can be a matter of indifference whether this occurs once or repeated a million times, or on how many heavenly bodies. The form of universality in nature is law, and no one talks more of the eternal character of the laws of nature than the natural scientists. Hence, when he says that the finite is made impossible to understand by not desiring to investigate merely this finite, but instead adding something eternal to it, then he denies either the possibility of knowing the laws of nature or their eternal character. All true knowledge of nature is knowledge of the eternal, the infinite, and hence essentially absolute. But this absolute knowledge has an important drawback. Just as the infinity of knowable matter is composed of the purely finite things, so the infinity of the thought which knows the absolute is composed of an infinite number of finite human minds, working side by side and successively at this infinite knowledge, committing practical and theoretical blunders, setting out from erroneous, one-sided, and false premises, pursuing false, tortuous, and uncertain paths, and often not even finding what is right when they run their noses against it. The cognition of the infinite is therefore beset with double difficulty, and from its very nature can only take place in an infinite asymptotic progress, and that fully suffices us in order to be able to say the infinite is just as much knowable as unknowable, and it is all that we need. Curiously enough, Nadia says the same thing. We can know only the finite, but we can know all the finite that comes. It's the sphere of our sensuous perception. The finite that comes into the sphere, etc., constitutes in some precisely the infinite, for it is just from this that Nadia has derived his idea of the infinite. Without this finite, etc., he would have indeed no idea of the infinite. Before this investigation of infinity comes the following: the insignificant sphere in regard to space and time, the probably defective development of the sense organs. That we only know the finite, changing, transitory, only what is different in degree and relative, because we can only transfer mathematical concepts to natural objects and judge the latter only by measures obtained from them themselves. We have notions for all that is infinite or eternal, for all that is permanent, for all absolute differences. We know exactly the meaning of an hour, a meter, a kilogram, but we do not know what time, space, force and matter, motion and rest, cause and effect are. It is the old story. First of all, one makes sensuous things into abstractions, and then one wants to know them through the senses, to see time and smell space. The empiricist becomes so steeped in the habit of empirical experience that he believes that he is still in the field of sensuous experience when he is operating with abstractions. We know what an hour is, or a meter, but not what time and space are, as if time was anything other than just hours, and space anything but just cubic meters. The two forms of existence of matter are naturally nothing without matter, empty concepts, abstractions which exist only in our minds. But, of course, we are supposed not to know what matter and motion are. Of course not, for matter is such a notion as such had not yet been seen or otherwise experienced by anyone. Only the various existing material things and forms of motions. Matter is nothing but the totality of material things from which this concept is abstracted, and motion as such nothing but the totality of all sensuously perceptible forms of motion. Words like matter and motion are nothing but abbreviations in which we comprehend many different sensuous perceptible things according to their common properties. As matter and motion can be known in no other way than by investigation of the separate material things and forms of motion, and by knowing these, we also pretend to know matter and motion as such. Consequently, in saying that we do not know what time, space, matter, motion, cause and effect are, Nadia merely says that first of all we make abstractions of the real world to our minds, and then cannot know these self-made abstractions because they are creations of thought and not sensuous objects, while all knowing is sensuous measurement. This is just like the difficulty mentioned by Hegel. We can eat cherries and plums, but not fruit, because no one has so far eaten fruit as such. When Nadia asserts that there are probably a whole number of forms of motion in nature which we cannot perceive by our senses, that is a poor apology, equivalent to suspension, at least for our knowledge of the law of the unagreeability of motion, for they could certainly be transformed into motion perceptible to us. That would be an easy explanation of, for instance, contact electricity. At most immediately, impossibility of conceiving the infinite. When we say that matter and motion are not created or indestructible, we are saying that the world exists as infinite progress, that is, in the form of bad infinity, and why we have understood all of this process that is to be understood. At the most, the question still arises whether this process is an eternal repetition in great cycles, or whether the cycles have descending and ascending branches. Bad infinity. True infinity was already correctly put by Hegel in full space and time, in the process of nature and history. The whole of nature also is now merged in history, and history is only differentiated from natural history as the evolutionary process of self-conscious organisms. This infinite complexity of nature and history is within the infinity of space and time. Bad infinity only is a sublime factor, essential but not predominant. The extreme limit of our natural science until now has been our universe, and we do not need the infinitely numerous universes outside it to have knowledge of nature. Indeed, only a single sun among millions, with its solar system, forms the essential basis of our astronomical researches. For terrestrial mechanics, physics, and chemistry we are more or less restricted to our little Earth, and for organic science entirely so. Yet this does not do any essential injury to the practically infinite diversity of phenomena and natural knowledge, any more than history is hardened by the similar, even greater limitations to a comparatively short period and small portion of the Earth. 1. According to Hegel, infinite progress is a barren waste because it appears only as eternal repetition of the same thing, 1 plus 1 plus 1, etc. 2. In reality, however, it is no repetition, but a development, an advance or regression, and thereby becomes a necessary form of motion. This apart from the fact that it is not infinite, the end of the Earth's lifetime can already be foreseen. But then, the Earth is not the whole universe. In Hegel's system, any development was excluded from the temporal history of nature, otherwise nature would not be the being beyond self and spirit. But in human history, infinite progress is recognized by Hegel as the sole true form of existence of spirit, except that fantastically its development is assumed to have an end in the production of Hegelian philosophy. 3. There is also infinite knowing, quest infinity of nihilo progresso, la anno giro. Thus the law of the change of form of motion is an infinite one, including itself and itself. Such infinities, however, are in their turn smitten with finiteness, and only occur piecemeal. So also 1 or 2. The eternal laws of nature also become transformed more and more into the spiritual ones. That water is fluid from 0 degrees 100 degrees Celsius is an eternal law of nature, but for it to be valid, there must be water, the given temperature, normal pressure. On the moon there is no water, and the sun only its elements, and the law does not exist for these two heavenly bodies. The laws of meteorology are also eternal, but only for the Earth, or for a body of the size, density, axial inclination, and temperature of the Earth, and on condition that it has an atmosphere of the same mixture of oxygen and nitrogen, and with the same amounts of water being evaporated and precipitated. The moon has no atmosphere, the sun one of glowing metallic vapors. The former has no meteorology, that of the latter is quite different from ours. Our whole official physics, chemistry, and biology are exclusively geocentric, calculated only for the Earth. We are still quite ignorant of the conditions of electric and magnetic tensions on the sun, fixed stars, and nebulae, even on the planets of a different density from ours. On the sun, owing to high temperature, the laws of chemical combination of the elements are suspended or only momentarily operative at the limits of the solar atmosphere, the compounds becoming associated again on approaching the sun. The chemistry of the sun is just in process of rising, and is necessarily quite different from that of the Earth, not overthrowing the latter but standing outside it. In the perhaps there do not exist even those of the 65 elements which are possibly themselves of compound nature. Hence, if we wish to speak of general laws of nature that are uniformly applicable to all bodies, from the nebula to men, we are left only with rarely and perhaps the most general form of the theory of the transformation of energy, vulgar mechanical theory of heat. But, on its general, consistent application to all phenomena of nature, this theory itself becomes converted into a historical presentation of the successive changes occurring in the system of the universe from its origin to its passing away, hence into a history in which at each stage different laws, that is, different phenomenal forms of the same universal motion, predominant, and so nothing remains as absolutely universally valid except motion. The geocentric standpoint in astronomy as prejudice has rightly been abolished, but as we go deeper in our investigations, it comes more and more into its own. The sun, etc., serve the Earth. Anything other than geocentric physics, chemistry, biology, meteorology, etc., is impossible for us, and these sciences lose nothing by saying that they only hold good for the Earth, and are therefore only relative. If one takes it seriously and demands a simple science, one puts a stop to all science. It suffices us to know that under the same conditions everywhere the same must take place, at a distance to the right or the left of us that is a million times as great as the distance from the Earth to the sun. Cognition and eyes different from ours. They can see chemical light rays, but as regards knowledge of these rays that are invisible to us, we are considerably more advanced than the ants, and the very fact that we are able to demonstrate that ants can see things invisible to us, and that this proof is based solely on perceptions made with our eyes, shows that the special construction of the human eye sets no absolute barrier to human cognition. In addition to the eye, we have not only the other senses, but also our thought activity. With regard to the latter, matter stamped exactly as with the eye. To know what can be discovered by our thinking, it is no use, 100 years after Kant, to try and find out the range of thought from the critique of reason or the investigation of the instrument of knowing. It is as little use as when Helmholtz uses the imperfection of our sight, and the construction of our eye, which restricts sight to definite limits and even so does not yet quite direct reproduction, as proof that the eye acquaints us indirectly or unreliably with the nature of what is seen. What can be discovered by our thought is more evident from what has already discovered and is every day still discovering, and that is already enough both with regards to quantity and quality. On the other hand, the investigation of the forms of thought, the thought determinations, is very profitable and necessary, and since Aristotle this has been systematically undertaken only by Hegel. In any case, we shall never know how chemical rays appear to ants. Anyone who is distressed by this is simply beyond help. The form of development of natural science, insofar as it thinks, is a hypothesis. A new fact is observed which makes impossible the previous method of explaining the facts belonging to the same group. From this moment onwards, new methods of explanation are required, at first based on only a limited number of facts and observations. Further observational material weeds out these hypotheses, doing away with some and correcting others, until finally the law is established in a pure form. If one should wait until the material for the law was in a pure form, it would mean suspending the process of thought and investigation until then, and if only for this reason, the law would never come into being. The number and succession of hypotheses supplanting one another, given the lack of logical and dialectical education among natural scientists, easily gives rise to the idea that we cannot know the essence of things. This is not peculiar to natural science, since all human knowledge develops in a much twisted curve, and in the historical sciences also, including philosophy, theories displace one another, from which, however, nobody concludes that formal logic, for instance, is nonsense. The last form of this outlook is the thing itself in the first place. This assertion that we cannot know the thing itself passes out of the realm of science into the fantasy. Secondly, it does not add a word to our scientific knowledge, for if we cannot occupy ourselves with things, they do not exist for us. And thirdly, it is a mere phrase and is never applied. Taken in the abstract, it sounds quite sensible. But suppose one applies it. What would one think of a zoologist who said, a dog seems to have 4 legs, but we do not know whether in reality it has 4 million legs or not at all? or the mathematician who first of all defines a triangle as having three sides, and then declares that he does not know whether it might not have 25? That minus 22 seems to be 4, but scientists take care not to apply the phrase about a thing in itself in natural science. They permit themselves this only in passing into philosophy. This is the best proof how little seriously they take it and what little value it has itself. If they did take it seriously, what would be the good of investigating anything? Taken historically, the thing would have a certain meaning we can only know under conditions of our epoch, and as far as these allow. The thing itself, Hegel, Logic, 2, b. 10, also later a whole section on it. Skepticism did not dare to affirm it. Modern idealism did not dare to regard cognition as knowledge of the thing itself in the margin of the manuscript as a remark, confer encyclopedia, 1, b. 252. But at the same time, skepticism admitted manifold determinations of its show, or rather its show had for content all the manifold riches of the world. In the same manner, the appearance of idealism comprehends all range of these manifold determinances. The content may then have no basis in any. Being written anything nor thing itself, for itself it remains as it is. It has only been translated from being into show. Hegel, therefore, is here much more resolute materialist than the modern natural scientist. Valuable self-criticism of the Kantian thing itself, which shows that Kant suffers shipwreck also on the thinking ego, and likewise discovers it in unknowable thing in itself. Notes. 156. Compsognathus, an extinct animal of the order of dinosaurs, belonging to the class of reptiles, but according to the structure of the pelvis and index remaining closely related to the birds. Under the operates, see note 18. 157. Engels is referring to multiplication by budding or division among colinverts. 158. Hegel, Encyclopedia of the Philosophical Sciences. 135. Addendum, the limbs and organs, for instance, of an organic body are not merely parts of it. It is only in their unity that they are what they are, and they are unquestionably affected by that unity, as they also in turn affect it. These limbs and organs become mere parts only when they pass under the hands of the anatomist, whose occupation, be it remembered, is not with the living body but with the corpse. 159. Opposite. 126. Addendum. 160. Opposite. 117. Addendum. 161. Opposite. 115. Note. Here Hegel says that the very form of judgment speaks of the distinction between the subject and the predicate. 162. This refers in all probability to the book by Clausius Dynamic or Theory. 2 T. Yumter by Gofflage. 1. Van Braunschweig, 1876. Pages 87-88 of this book speak of the positive and negative quantities of heat. 163. Engels is in mind J. Grumskirch Bedeutend Sprech, 4. Oppel, Leipzig, 1880. First published in Leipzig in 1848. He speaks of the Frankish dialect in greater detail in his work The Frankish Dialect, written in 1881 to 82. This note must have been written about 1881. 164. Kismet, in Muslim, chiefly Turkish, usage, means destiny or fate. 165. This refers to Darwin's The Origin of Species by Means of Natural Selection. 166. A quotation from Heine's satirical poem Disputation, which depicts a medieval dispute between a Catholic Capuchin monk and a learned Jewish rabbi, who in the course of the dispute appeals to the Jewish religious book Tostes John Dov. The Capuchin's reply is to send Tostes John Dov to the devil. Thereupon the indignant rabbi cries out in a frenzy, Gilt nix murder Tostes John Dov, or Saul Yelden, Zer, Zer. 167. G.W.F. Hegel, work, B.D. 3, 2, Oppel, Berlin, 1841. The underscoring in the quotations is by Engels. 168. The references to the following passage from Hegel's reference to phenomenology de Geist, the bud disappears when the blossom breaks through, and we might say that the former is refuted by the latter. In the same way, when the fruit comes, the blossom may be explained to be a false form of the plant's existence, for the fruit appears as its true nature in place of the blossom. Engels is quoting from G.W.F. Hegel, work, B.D. 2, Oppel, Berlin, 1841. 169. Dido, the name of Engels' dog, which he mentioned in his letters of March 8, April 16, 1865, and August 10, 1866. 170. Hegel explains the correspondence between the division of logic into three parts, and the four-member classification of judgments as follows. The different species of judgment derive their features from the universal forms of the logical idea itself. If we follow this clue, it will supply us with three chief kinds of judgment parallel to the stages of being, essence and notion. The second of these kinds, as required by the character of essence, which is the stage of differentiation, must be double. 171. Here the definition singular, particular and universal stand for individual, particular, and universal in the sense of formal logic, as distinct from the dialectical categories of zones, was in the Sandel minds. 172. Engels gives the pages of the whole chapter on judgment in the third book of Hegel's Science of Logic. 173. The whole of the third part of Hegel's Science of Logic. 174. On pages 75-77 of the fourth edition of his Natural History of Creation, Hegel relates how Goethe discovered the existence of the intermaxillary bone in man. In Hegel's opinion, Goethe arrived first of all at the inductive proposition, whole mammals have an intermaxillary bone, from which he drew the deductive conclusion. Therefore, man also has such a bone. Following which this conclusion was confirmed by experimental data. Engels says that the induction of which Hegel speaks is incorrect because it was contradicted by the proposition. Considered correct that mammal man has no intermaxillary bone. 175. Engels is obviously referring to the two main works of Whewell, History of the Inductive Sciences and Philosophy of the Inductive Sciences. The manuscript has Die Bloss Mathematische Fest. The word unfest is used here obviously in the sense of comprising the purely mathematical sciences, which, according to Whewell, are sciences of pure reason that investigate the conditions of all theory, and in this sense occupy, as it were, a central position in the geography of the intellectual world. In philosophy of the inductive sciences, Whewell gives a brief outline of the philosophy of the pure sciences regarding geometry, theoretical arithmetic, and algebra as its main components. In his history of the inductive sciences, Whewell counterposes the inductive sciences to the deductive sciences. 176. In the formula UIP, he denotes the universal, I, the individual, P, the particular. This formula is used by Hegel in analyzing the logical essence of inductive conclusions. See Hegel, Science of Logic, Book 3, Section 1, Chapter 3, Paragraph, the syllogism of induction. Hegel's proposition, mentioned by Engels further down, that inductive conclusion is in effect problematic, occurs in the same place. 177. H. A. Nicholson, A Manual of Zoology, 5th ed., Edinburgh and London, 1878, pages 283-85, 363-70, 481-84. 178. Hegel, Encyclopedia of the Philosophical Sciences, 39. Mere experience, efforts, perceptions of changes succeeding each other. But it presents the necessary connection. 179. Spinoza, Ethics, Part 1, Definitions 1 and 3, and Theorem 6, 180. See Note 16. 181. This heading is given in the list of contents drawn up by Engels for the second folder of materials for dialectics of nature. This note is devoted to a critical analysis of the basic thesis put forward by the botanist Medelia in his lecture to the Munich Congress of German Natural Scientists and Physicians on September 20, 1877. Medelia's lecture was entitled Die Schranken der Naturwissenschaftlichen Erkenntnis. Engels quoted according to the appendix to the Congress report. This edition was supplied to Engels in all probability by K. Schroeder, who attended the Congress. 182. Engels is referring to the discovery of oxygen in 1774 by Joseph Priestley, who did not even guess that he had discovered a new chemical element and that this discovery would lead to a revolution in chemistry. Engels speaks in more detail about this discovery in his preface to the second volume of Marxist Capital. 183. Confer Hegel, Encyclopedia of the Philosophical Sciences, 13. Note, when the universal is made a mere form and coordinated with the particular, it sinks into a particular itself. Even common sense in everyday matters is above the absurdity of setting the universal beside their particulars. Would anyone who wished for fruit reject cherries, pears, and grapes on the ground that they were cherries, pears, or grapes, and not fruit? 184. This reference is to Hegel's Science of Logic in the section on quantity. Hegel mentions astronomy and says it is admirable not because of the bare infinity of the measurable distances, time and the immeasurable multitude of stars, but rather because of those relations of measure and those laws which reason recognizes in these objects. Clearly the infinity of reason and those others the infinity of unreason. Hegel, Science of Logic, Vol 1, Part 2, Chapter 2, Note, High Opinion of Infinite Progress. 185. This is a quotation, slightly modified by Engels, from the treatise De Economia of the Italian economist Galliani. This same quotation was used by Marx in Volume A of Capital. Marx and Engels used the Gusto editions for Tori Classici Italiani di Economia Politica, Part Modern, Tomo 3, Milano, 1803, p. 156. 186. The words so also 1 or 2 were added subsequently by Engels. It is possible that Engels has in mind the number p, which has a quite definite meaning, but which cannot be expressed by a finite decimal or an ordinary fraction. If the area of a circle is taken as 1, the formula p r2 equals 1 gives p equals 1 r2. 187. Engels is referring to the following passage in Hegel's Philosophy of Nature. The sun serves the planet, just as in general sun, moon, comets, stars are mere significations of the earth. 188. Engels is referring to George Romani's review of Sir John Lubbock's book Ants, Bees, and Wasps, London, 1882. The review appeared in the British Journal Nature No. 658 of June 8, 1882. The passage which interested Engels, the downs are very sensitive to the ultraviolet rays, occurs on page 122 of Volume 6 VI of Nature. 189. Engels is referring to Lev von Haller's poem Fallschlag der menschlichen Tugenden, in which Haller asserted, in the mortal mind can nature's inner secrets tell, too happy only if he knows the outer shell. Goethe, in his poem Outer Rings, opposes Haller's assertion, pointing out that nature is a single unity and cannot be divided, as is done by Haller, Hegel and Noah, inner kernel, and an outer shell accessible to man. Hegel mentions this argument between Goethe and Haller twice in his Encyclopedia of the Philosophical Sciences. 190. Hegel, Science of Logic, Book 2, Section I, Chapter 1, Paragraph Show, and Section 2 which contains a special paragraph on thing itself and an observation. 191. Hegel, Encyclopedia of the Philosophical Sciences, 124, Observation and Addendum. 192. Hegel, Science of Logic, Book 3, Section 3, Chapter 2. Council of finalists, matter and inherent motion. This matter is no abstraction. Even in the sum of different substances